Hey, Pedro here, otherwise known as Mr. Ducey, Mr. Thucydides. I hope you enjoyed this interview that I had the pleasure of doing with my good friend Kian Mansour. He is an organic chemist, but you'll quickly see that you cannot box Kian in this idea of just a chemist. He has a very vast knowledge base that you can pull from, and you'll see that in the interview with the many topics we talk about that stretch from biology, medicine, physics, and elsewhere. There are a lot of technicalities in this video, a lot of in-depth scientific discussions, and we do try to simplify things at the end. We have a synthesized summary version for the concepts we talk about so that you aren't lost. And I do understand that some of it can be ambiguous at first, but I am hopeful that it gets you interested in some of the things we talk about. A lot of the concepts in medicine that you'll hear us talk about, such as the polyunsaturated fats, you probably will not have heard the perspective we bring elsewhere. And I'm hoping that this also pushes in the direction of understanding things from a more chemical and physical perspective, because it's not enough to look at things from top down. We got to look at things from bottom up as well to get a really good idea of what's really going on. There are intermissions, about two or three in there, which have to do with technicalities that occurred with video development and the recording. Essentially, we got cut off a couple of times, so I had to add in some bits in there that were mostly coming from me. And there are a little bit of issues with video, and you'll see it black out a couple of times, but the audio will be perfect throughout the entire video. I do hope that you can bear through it. I hope that you enjoy. I know it's a long one. Maybe cut it up to 1 hour sections per day. Some of them are heavy, so you might want to sit down and take some notes. And that's it. Keon, thanks for coming on, man. And I'll catch you soon. And how do I end this? Like, I want to say something nice, but you just don't know what to say when you're making these recordings. There's no script here. I'm just gonna cut it off.
Welcome back to the Thucydides channel. I guess we're not skipping all that. My guest today is Kian Mansour. Am I pronouncing that right, Kian?
Yeah, I guess good enough. Kian Mansour is how I say it
Mansour,
usually.
understood. And he is a chemist out of University of Ottawa, and also one of the best, most coolest dudes I've ever met. He's a Chad through and through. And today we're going to talk about some pretty crazy stuff, chemistry related, biochemistry, and otherwise, to see if you guys get interested in learning chemistry and understanding why some of this stuff really matters in relation to health, disease, and in general, the outlook on life. So, I guess we should start it off with first going over who you are, Kian, and what got you into chemistry, what made you interested in the first place, and what are you studying now?
Yeah, for sure. So I think before we get into that, I'd like to say some words as well. Pedro, first of all,
Yeah,
thank you so much for inviting me on the podcast. I think you're actually the coolest Chad jacked genius guy I know. So again,
appreciate that, man.
appreciate the opportunity to get on the podcast or channel or you know how it is.
Yeah,
Second, let's pull an Andrew Huberman and go neither of our views represent the institutions we're at or our future institutions. These are our individual views. And so I get that out of the way, might as well. But yeah, I guess we'll get into me, who I am. So, as Pedro mentioned, my name is Kian Mansour, and I'm an organic chemist at the University of Ottawa. I'm currently a research associate. I completed my undergraduate degree, my honors bachelor's last year in biomedical science with specialization in medicinal chemistry. Outside of organic chemistry, my passions include powerlifting, both lifting and coaching, as well as Rubik's Cube speed solving, which is a little more niche of a hobby, but it's something that has been with me for quite a while. And how I got into chemistry, well, it's been a bit of a winding, twirling path, but I kind of identified an initial passion for it early in high school. It was kind of the topic that spoke to me most and which I was most passionate about reading on my own. But I kind of never really capitalized on it or pursued it further or really thought much of it since I had other passions as well, like math, physics, and biology as
hmm
well. And it took me a couple of years of university to re-identify or re-clarify that chemistry was, kind of my favorite science and that I would pursue it further.
very interesting. I've had similar experiences too when I would take a biology class that I really liked or physics class where I thought, okay, which one do I really want to pursue? And what
Hmm.
always brings me back to chemistry is the applicability, where it's so broad. You can use chemistry for petroleum design, fuel design, chemical engineering, medicine, etc. Chemistry is just everywhere, whether we realize it or not.
Yeah, exactly. I agree with you on that. I think another thing I really like about it is how it kind of connects the fundamental theory up right up to the application. I feel like in terms of physics and math, you spend a lot of time in the theory and not as much in the application. Whereas biology is mostly application. There's you don't get
Hmm.
that much exposure to the fundamentals. Whereas chemistry, and especially organic chemistry, in my opinion, takes you right down from quantum theory, thermodynamics, all the way up to just like affecting biological systems.
Yeah, that's a very good point. What was one of the things that you learned when you were learning, for example, physical organic chemistry or quantum theory that stood out to you? Anything in particular?
In terms of physical organic chemistry, I'd say the thing that stood out to me most was how impactful stereoelectronic effects are. For those that don't
Hmm.
know, stereoelectronic effects are the effects of orbitals that are dependent on the geometry of the atoms that connect the molecule together. So essentially, different conformations or ways the molecule can be oriented in space affect the energetic interactions between the orbitals, and that has widespread implications for reactivity and in biology as well.
This is interesting because I don't think a lot of people realize, especially when they look at molecules, they look at reaction. If they even had done some orgo, if they hadn't, you can just think of reactions happening kind of spontaneously. But really, a lot of things have to come together. And the most important is the 3D model of how those atoms work in space. And that is a big factor in a lot of synthetic chemistry, I'm sure.
Yeah, definitely. The more complicated the molecule gets, the more steric impacts and the 3D conformation comes into play. And again, those orbitals have to be aligned, otherwise it's not going to go.
Yeah. What was life like growing up for you? What was it like growing up in Canada? Things that got that you were interested in early on. Did you start Rubik's cubing when you were young?
Yeah, so growing up, my parents moved here from Iran. They were immigrants. They came here with
Hmm.
not so much. They worked pretty hard to make a lot of sacrifices to give me the best life they could. I don't have any siblings, so I'm an only child. They kind of always wanted me to go into medicine and be a doctor, but I was kind of more just curious about learning things in general. I'd always read on my own, whether it was textbooks or like even just fiction books. I was always kind of reading. Even when I watch TV, I'd rather it be some like Discovery Channel or even Magic School Bus when I was younger. Just something to keep the brain
Yeah.
stimulated. And then other than that, I was one of the weird kids who like enjoyed school and doing homework and that type of thing.
Mm.
Was pretty active with soccer and tennis growing up. Uh, got into playing quite a bit of video games in middle school, and then kind of left off of my active habits. Gained a little bit of weight there. Healthy habits weren't at their best. But then come high school, a lot of that changed. I got back into doing exercise, going for runs, playing tennis, and then eventually
Mm.
lifting. As for Rubik's Cube solving, that's something that I picked up right after eighth grade, so right before high school. And pretty much immediately, I knew that this was something that I was going to end up being incredibly passionate about. And I've been at it for something like, what's that, 2014? It's like 9 years now. It's pretty
Yeah.
crazy. Yeah.
Yeah. It shows you. I mean, seeing you solve the Rubik's cube with one hand in a couple of seconds, I'm like, there's no way, man. That is really impressive stuff. Awesome, dude.
Thank you, sir. Yeah. Took a lot of years of
What?
practice that some
Yeah.
people say could have been put to better use, but I don't know. At some points in life, you just gotta do what you enjoy. And looking back, there's no other period in life where I think I would have had the opportunity to do that, other than just early teenager, where
Yeah.
kind of had just the freedom to explore my hobbies.
One of the questions I have here is in relation to that later, but I figured it might be better if I ask now. In relation to Rubik's Cube solving, do you feel like that has helped you in any way with chemistry? Because I know with disparate hobbies, sometimes they connect in ways that you can never imagine unless you actually do them.
Yeah, so I think I wrote down a couple notes on this. There's a couple kind of distant connections that I think I've made between Rubik's Cube solving and chemistry. The first is kind of the pathway towards improvement. I'd say for Rubik's Cube solving, I identified pretty early that it's really important to have a consistent practice schedule and consume as much kind of informative content as I could to improve my technique, improve my solving abilities. And I kind of had the same approach towards chemistry once I decided that it was something I was going to pursue seriously. I just essentially would schedule in each day how much I was going to study, what I was going to study, what I was going to read, started pursuing whatever I could find on YouTube, textbooks, papers, just completely immersed myself in this topic. And I think that experience of kind of the obsessive desire to learn from Rubik's Cube solving helped me later in chemistry to realize that, oh, this is the same. It feels the same. I just have to do the same thing and I'll get good at it. The other thing I think that's helped is kind of my ability to visualize things in 3 dimensions and plan kind of complicated sequences that are a little bit difficult to see. So when you're solving the cube, obviously it's a 3-dimensional object and you're trying to put together pieces to get closer to the solved state. And sometimes you have to do things that don't really make much sense in the moment. You might have to do 2 or 3 moves or even up to 5 where it looks like you're not really doing much, but they were all with kind of the premeditation that they're going to make something improve later down the line. And kind of in natural product synthesis or synthesis of any complex molecule in general, sometimes the reaction you want to do isn't like immediately simplifying, in that it doesn't get you anywhere closer to your target directly, but it's kind of a setup step for what you're going to do next. So I think that sort of planning and visualization has helped me a little bit. It might be a bit of a chicken and egg there, whether I was kind of good at that or innately predisposed to be good at that, and I ended up being good at both, or if developing it from cubing lended itself more to already having a head start sort of when I started doing chemistry, but that's to be debated.
Yeah, that's very interesting stuff. I do see a lot of synthetic chemistry as almost like you're building a Lego piece, and you just have to know which pieces fit together, and then that comes down to solving physics, math stuff of reactivity and selection parameters, all that stuff. So, in a sense, I can see exactly how Rubik's Cube solving would help you with that, especially visualizing all of the steps that you know you need to achieve for synthesis. It's like, okay, there's some variability here. How can I go about it a different way? Really interesting stuff.
Yeah, exactly. It's funny you bring up the
Cool.
Legos.
So, why
A
did you
lot of
choose?
sorry,
Go
yeah,
ahead.
I was just gonna say a lot of prominent chemists refer to building molecules as kind of like putting Legos together.
Yeah, I've heard that before as well. I think that I stole it from somebody. I don't remember where. Okay, next question. Why did you choose organic chemistry over some of the other chemical routes that you could have possibly chosen?
Yeah, so I think I have two. There's 2 major reasons why I settled on organic chemistry. I think the predominant reason was kind of the way it was taught and the exposure I had in the Department of Chemistry here at the University of Ottawa. I feel like everything from the introductory courses up to the more advanced courses in organic chemistry was taught incredibly well. They did a really good job at kind of introducing the fundamentals, and as I said, showing how those theories can be applied to different things in biology, medicine, just a lot of industrially and societally relevant applications. Whereas I didn't feel that in my other chemistry classes at the start, whether it was physical chemistry or analytical, especially in the earlier courses, it was kind of more separated from the real world. But then as I went on, obviously, to more higher year courses, I felt that, analytical and inorganic and physical theoretical chemistry started to make a lot more sense with respect to where they could be applied. So in terms of analytical chemistry, I don't think I ever would have picked it, even knowing what I know now. It seems a little bit too empirical for me, and I don't think it's as reliant on fundamental theories. Obviously, it's crucial for every field you do, whether it's biochemistry, organic chemistry, physical chemistry. You're going to need analytical methods to identify things, characterize them, all of that. But I feel like it's just I don't see it as kind of a unique field. It kind of takes from everywhere. So I don't think I'd ever be like a pure analytical chemist. Obviously, I'd have to bridge with another topic to kind of make it something I'd be interested in. As for the computational theoretical route, I actually do have a bit of experience in that field. That was actually my first ever research experience, was in a computational lab, and I actually like it quite a bit since it's pretty easy to go from idea to testing it out. You just run a computation for a day or half a day or something, and then it works or it doesn't work, and you can try something again. However, I do like doing wet experiments in the lab, so that is something that I wouldn't like about being a pure computationalist. Also, there's quite a bit of kind of critique of computational chemistry in that it's always just going to be a computation and it's not always going to be correct. So you could go through the most rigorous computations and then run an experiment that kind of disproves all of it if you missed a parameter or you didn't account for the effects of solvent or different ions. So at the end of the day, I feel like, as with analytical chemistry, the computations are just another tool to supplement the experimental work to aid our understanding of it and kind of guide what we do. But at the end of the day, I feel like the experiments are kind of the most rooted in reality. And lastly, in terms of other fields and why I didn't go that way, is inorganic chemistry. So I think if I hadn't picked organic, I would have gone the inorganic route. It's kind of the same in terms of breadth, from basic fundamental theories of thermodynamics, bonding, all the way up to applications in catalysis, industry, that sort of thing. Especially with inorganic chemistry, I think there's a lot of potential for societally relevant contributions, whether it's in like materials, sustainability, sensors, solar energy, energy conversion, carbon dioxide capture. There's a lot of emerging fields now. So I honestly, if I hadn't been exposed to chemistry in kind of the order I did, whether like I essentially took the most advanced organic courses before I took kind of the medium level inorganic courses. So if I feel like if that would have been reversed, I would have gone the other way.
Right. A couple of things I noticed from that were, first, I see that's a diss towards computational chemists. Works with me because I feel the same way. Obviously, you want to be able to prove this experimentally. That is the end all be all. I don't care what your models show. If they're not accurate, it doesn't matter at all. This is something that my buddy Devin, who's working with me on this mitochondria project, he hates the idea of hydrogen-based metal organic frameworks, where they're essentially computationally modeling what it'd be like to have a hydrogen-based organic framework. But theoretically, although it's solid, it's never been shown experimentally because it's easy for hydrogen to diffuse out, and so the organic framework itself can never be really built, at least with the limitations at the moment with laboratory processes. So he's like, so what's the purpose of it? You're just having this computational model that will never really be produced in real life. But then I do realize, like what you said about inorganic chemistry, other industrial applications exist where these computational models have proven valid, like metal organic frameworks for capturing hydrogen and oxygen from the air in like deserts and converting it to pure water so that you can make water in the desert. And that first developed as a computational model. Then they went and tried to synthesize it, and now they proved that it's feasible, the process in general. So I do agree. There's limits to computation, and there's so much that you can consider when making an appropriate computation, but it has to be experimentally valid. And I like that you mentioned how you went from the simple organic chemistry 1 and 2, and you even went ahead and did physical organic chemistry as an undergrad, right? Which is something that
Yeah.
most people don't do until like second year of masters in chemistry. What was that like for you, seeing the difference between the lower level organic chemistry and then realizing, oh, synthesis is, you have to do retroductive analysis, retrosynthetic analysis. You have to consider all of the activation energy and all of that stuff. What was that like when you first were exposed to it?
Yeah, I'll get into that, but I want to mention one more thing related to computations before we get absolutely flamed by the computational chemists. So I agree that the experiment's the be all end all, but I think computations are improving a lot recently, and I think the two major benefits of doing computations are, one, providing a rationale for what's observed experimentally when experiments don't allow you to do that. So a lot of
Mm-hmm.
times, mechanistic analysis by experiment isn't fully able to elucidate what's going on, especially with complex organometallics. So at that point, resorting to computations can help provide another piece to the puzzle to explain a certain selectivity or reaction outcome. And the other area I think it helps in is reducing the number of experiments you have to run before you do something productive. So let's say
Yeah.
running, I don't know, 50 computations is faster than running 100 experiments. You might as well run those 50 first and then set up the experiments afterwards. Just reducing the kind of breadth of things you have to run and testing those that are computationally viable first, whether it's in catalysis or in medicinal chemistry, kind of like docking studies to see certain ligand's going to bind to a certain enzyme. If you're able to screen conditions or ligand structures or drug structures rapidly through computations, and it's something that's worked in the past with similar systems, then I'd say in that case, yeah, it's definitely worth running the computations first, taking the best of the series, and then trying to see what works experimentally.
Awesome.
But yeah, going on to your,
Very
unless you
interesting
want to add
stuff.
to that again.
Yeah, I mean, no, nothing to add except wet lab supremacy here. Just saying.
Yeah, I don't disagree there if that's one statement we had to make. But yeah, going back to your question on physical organic chemistry. So yeah, it was pretty interesting how that happened. I actually took the third year organic course, and then the professor teaching that mentioned that he's teaching the graduate level physical organic course the next semester. And kind of the way it works at my school is that there's not that many kind of fourth year science courses. Pretty much half of them are mixed undergrad grad classes where it's 2 grad classes but 1 undergrad class in the same lecture. So the grad students will do like the first 6 weeks or the second 6 weeks, and the undergrads will do the whole semester. So that's how I was exposed to that in my. So I essentially took a fourth year course in my third year that was a bridged graduate class, and I think that was really eye opening to understand the driving forces behind reactivity and selectivity as well as mechanism, since we started from the fundamentals of
Mhm.
the thermodynamics of chemical bonds, stereoelectronic effects, stability, and then moved into uh, catalysis, kinetics, and free activation energies, mechanistic studies, the way those work. And I think it was really eye opening and has kind of opened my eyes to a whole field of literature.
Nice. Just one quick part. By any chance, do you have like a keyboard in front of you? I hear like this sound. I just want to make sure that the sound sounds good. Or is
Keyboard.
it like, or anything
Is
like
it?
click, just in case? Just so.
I'm not hearing anything clicking. So
Okay, gotcha. All right,
yeah.
just want to make sure we're good. All right. So next question I have for you, your health journey, because you've mentioned to me that there was a point in your life where things weren't really good with your health. What was that about? How did you have this coming together in terms of your health and understanding why, for example, the polyunsaturated fat discussion matters? And I think you mentioned gluten was a big factor in this as well, right?
Yeah, so I can either give you the long version of the story or the kind of abbreviated version. So it's really up to you how we go about this.
Go ahead, give me the long version. We have plenty
All
of
right,
time.
long version it is. So I think I mentioned, I don't know, maybe 10 minutes ago that gained a little weight in middle school, wasn't so active, wasn't eating the best, was playing video games
Mhm.
all day with my friends. But then once I got to high school, things got better, started working out. Um, we had like a fitness class in gyms where older students would teach us how to lift weights. So that's kind of how I started. Started getting into powerlifting with some friends at school, and then we kind of just grew into that in our last couple of years of high school. University came around, and the whole freshman 15 and disgusting toxic lifestyle of university cafeteria food hit me, and I did gain quite a bit of weight there as well, but wasn't all terrible. There was a quite a bit of muscle there that was supported by the lifting. um, and then I guess I was kind of like cruising with like kind of medium health habits. I was definitely on top of my sleep and kind of macro counting for lifting performance reasons. But a lot of my dietary choices weren't the best. I was eating kind of like just Nutella and bagels for breakfast, some like processed ham sandwiches for lunches. My dinners were pretty clean in terms of like beef, chicken, rice, but I'd say about half of what I ate wasn't the best quality food. But I still felt pretty good. I was able to do everything I needed to do in the gym and in terms of academically as well. And third year is when the um, pandemic came about. So moved back home, and essentially that year is when I started getting into chemistry as well, specialized into the medicinal chemistry option of my program. And at that point, I was essentially studying 12 to 14 hours a day. So to cut back on the lifting, but again, my food and sleep were pretty good at this point. I was back to eating home cooked meals since I was living with my parents again. So I'd say my health that year was quite good. Fourth year came around, and this is where kind of everything changed. So in my fourth year of undergraduate, which would have been 2022 fall, or sorry, 2021 fall to 2022 winter, this was a pretty stressful period for me. I was in the middle of finishing up research, trying to get an honors project out, doing like 3 or 4 advanced courses each semester, while also applying to graduate school. Since at this point, I knew I wanted to pursue a PhD in organic chemistry, and I saw that the funding and research in the US were quite a lot better than in Canada. So I started looking into US schools for grad school. So, dealing with applications, um, interview preparation, visiting schools, still doing research. I was still in the lab 5, 6 days a week, including weekends sometimes, studying all day. I had a lot going on. I was pretty stressed out. And pretty much in February of 2022, things started to go downhill. I took a midterm. It was actually an organometallic chemistry midterm. And for the first time ever, I kind of like lost focus and had a bit of anxiety during the midterm. I spent the
Mm.
first half hour of the hour-long midterm doing the first question, and there were 10 questions on the entire thing. I was like looking at the paper, my vision was blurry, I couldn't really see what was going on. And then I kind of just, focused and finished it and ended up acing the thing, but I don't know how I did that. Then I flew out to visit some schools the next day. Pretty stressful interviews again. I actually ended up like kind of having the same like blurry vision, like anxious feeling during those interviews. And we were showing chemistry on slides and I couldn't see the screen, so that was a little concerning. But I figured, oh, maybe I'm just sleep deprived. I'll go home and rest and sleep. I ended up like going to the gym with a professor early in the morning after being out late with the students at night, and I ended up actually like essentially passing out in the parking lot, and got up pretty quickly after that, went, ate some food, felt a bit better, came back to Ottawa, rested up, felt a bit better, kept kind of going through the same stressful cycle that I was going through, with lab work, studying, preparing for interviews, all that stuff. And then essentially a week later, everything crashed and I was in bed for 16 hours a day. I couldn't do much. I was sensitive to light, sensitive to sound. My hands were losing sensation. My face was losing sensation. Just like a lot of anxiety, digestive issues. And then I noticed I'd lost weight. So in this last year, in my fourth year, I forgot to mention, I hadn't really been lifting weights. I decided to kind of sacrifice that and make more time for studying, which probably wasn't the best choice. My fitness definitely deteriorated there, but I had lost a bit of weight from not lifting and not eating as much as well. I'd gone down from maybe 195 pounds to 175 over something like six months to a year. But then in that last little portion before everything crashed from January to February, I lost another 15 to 20 pounds. So I was down to about 155, 160. And I hadn't weighed that little since I was maybe like 16. So I was eating a ton a day after I got sick and after everything crashed. So now we're in like March. So again, I have like severe brain fog. I can't think clearly, headaches, like my whole body hurts, sensitive to light, sensitive to sound. I'm sleeping all day, can't focus, lots of anxiety, like digestive issues. I lost a lot of weight. I was eating maybe 7 to 10 meals a day, like full 7 to 10 meals. This was more than I was eating ever, even when I was near 200 pounds. I wasn't able to gain a single pound during this time. Still weighed around 155, 160. A lot of doctors' visits. They were essentially like, there's probably nothing wrong with you. Maybe you're just burnt out. Go home. Like, you'll be fine eventually. And then at that point, there was a lot of stress as well, since I was in the middle of finishing up my degree. There were 2 months of school left, and doing all these grad school interviews and visits. So I essentially had to decide to defer all my final exams and my thesis into the summer, and I had to reject all my grad school offers and accept that I'm at least taking a year off, and I don't know when I'll be able to graduate. I don't know when my brain's going to work. I don't know when my body's going to work. I just kind of have to figure that out first. So that's kind of what happened pretty much a year ago now. It's April, yeah. So I made that decision basically in April after a month of suffering with that. And then this was pretty crazy. So this is actually how I found your Instagram. So from all my explorations in powerlifting, I'd developed some connections with people and followed a bunch of pages and lifters, coaches, that type of thing. And our mutual buddy Sean Noriega at that time had started his nori.plate account where he was posting his meals. And right around that point, I kind of realized that healthcare system here is set up in a way where family doctors only going to spend 15 or so minutes with you. Hospitals are only for kind of like chronic, something that's diagnosed, or immediate emergency. So I kind of felt like I wasn't being supported or helped out by the system. And I decided that things were in my own hands and I had to do whatever I knew, whether it's, monitoring how badly I feel, how different foods make me feel, how much sleep I'm getting, how tired I feel, the pain, that sort of thing. And I was like, okay, let me just try changing my diet and see if that can make me feel any better at all. So I essentially copied Sean's diet to a T and started eating like him. And pretty much right away, within a week or two, I started feeling maybe 10 to 20% better. Another thing I forgot to mention is that I tried like getting back into exercise during the period that I felt sick. and I would like do 10 push-ups and be in bed for 3 days with severe pain. That's how destroyed my body was. And now, after switching my diet completely to exactly what Sean was eating, so this would have been a lot of beef, eggs, rice, sourdough bread, fruits, honey, I was immediately able to start a bit of light exercise again. The kind of numbness and lack of sensation and uncoordinatedness in my hands and face went away, and I was able to do a bit of studying. I was actually able to study for 1 to 2 hours a day, rather than just sleeping and trying to survive. And I kind of started like measuring certain metrics. Like I'd measure how long it took me to read, I don't know, 5 pages of content. Before changing this, it would take me like an hour to read 5 pages, and now it was half hour. So that was improvement, and that was pretty exciting. So I started like tracking all these metrics and trying to see if I would improve, make it a task to go for a walk a day, read a couple pages a day, and gradually I started to feel better. But then it sort of plateaued, and by midsummer, I'd say like July, August, I was starting to get a bit frustrated and realized that a lot of the issues were still there on and off, and I wasn't necessarily back to full health. I was still slowly completing my courses. At this point, I was doing like one exam a month, just adding sections to my thesis as I went, and I still wasn't fully recovered. Then there was a day in August where I realized that I feel worse after breakfast, and breakfast is where I eat sourdough bread, and that's my only gluten source.
Mhm.
So then I realized, oh, wait a minute, maybe this is the issue. So I stopped eating sourdough bread, and 2 weeks later, I felt perfectly fine. So it turns out the microdose of gluten in sourdough bread, it's about 200-fold less than maybe 500-fold less than other breads. I think it's a couple hundred ppm versus a couple 100,000 ppm in regular unfermented breads. Turns out that was causing enough inflammation, you could say, in my body that was messing me up over those couple months. And that before making that switch, my high gluten diet of, just pasta, a lot of bread was the issue from the start. So that's kind of the main aspect of the story. And then obviously after, following Sean and his health page or his nutrition page, that's how I found you through his stories and posts, and, started taking my health more seriously, especially with, eating whole foods, avoiding processed junk, avoiding seed oils, which we're going to talk quite a bit about later on. But yeah, that's kind of the crux of my journey.
Very incredible, man. And I'm sorry that you went through all of that in over a year too. And at the same time, you had to reject all of the graduate applications. And you were accepted to places like Scripps Institute, which is very hard to get into. So must have been tough. And I'm sorry I wasn't there to be able to help you with this stuff either. But a couple of things that I want to say in regards to that is I understand entirely what it's like to have to take off from the gym because of academic demands. Like even right now, I worked out probably 6 days ago. I can't devote as much time to training as I used to because it's just way too big a load. So I definitely think there was an aspect of burning out and your nervous system was fried. But yeah, maybe the food was like that contributing factor that put you over the edge essentially. And it's interesting how even a couple parts per million, I'm glad that you mentioned that, with sourdough bread, gluten still affects you in unique ways. It's not like you're celiac, but you still have gluten insensitivity. And things like this exist for a lot of people, and they don't even realize it. They're operating at such a low level that they think, oh, a piece of bread won't hurt me, but they don't realize that actually it is causing more harm than good, and you just don't know what it's like to feel good. You haven't been there before. But I'm glad that you're able to first come back from that, and second, you look a lot more active. You look a lot more filled out. You're eating well. Your habits are awesome from what I see.
No, thank you, sir. It means a lot. It's great to have good influences like you around in my circle now. And yeah, I'm trying to be more balanced with my exercise, do a bit of lifting, a bit of running, a bit of sports, play a bit of soccer now. But yeah, one more thing on that gluten thing. So we actually still to this day don't know whether it's a sensitivity or full celiac disease. I was given like a blood test or like a requisition for a test, but essentially told that it's pointless to do it now since I'm not consuming gluten, so I'm not going to have any of the I think it's
Yeah,
antibodies they look for. But the kind of pieces, 2 or 3 pieces of evidence that make me think that it could actually be celiac disease are the weight loss before everything happened, the inability to gain weight after it, and kind of the widespread systemic issues that might have come from the inability to absorb nutrients due to all that inflammation, right? If you think like if my gut was inflamed that entire time, I wouldn't have been absorbing anything, whether it's macros or micros, so I wouldn't have been gaining weight. And also I would have been starting to get deficient in key micronutrients, like whether it's copper or B vitamins, that could have been causing some of the kind of more neurological feelings of like losing sensation. So that's definitely a possibility. The other thing is now every time or like the couple times I've accidentally consumed gluten, it's been just almost immediate digestive issues. And also the last piece of evidence there is that someone pretty close in my family has also developed a similar thing in the past couple months where they got the virus that caused the pandemic, and after that they haven't been able to eat gluten. A lot of similar issues to what I had, and now on a gluten-free diet they are doing a lot better. So maybe for
Very
me it was
interesting.
something stress induced,
Yeah.
whereas for this closely related person in my family it could have been infection induced.
Gotcha. Well, thank you for sharing everything. I think it helps to know for a lot of people that might not have as much breadth of knowledge as you do in chemistry. Like even people like ourselves, we still can get messed up, even with everything we know. Health is a very complex um, system overall. It's not just knowing the chemistry. It's like there's more to it than we can possibly hope to try to understand. We do the best that we can.
Right, definitely. And that's where I think there's value in different experts from different fields, right? Like, can't necessarily blame a doctor for not being able to figure that out since it's such a complex issue and there's so many possible things it could be. Can't just randomly screen for everything. But, one of your buddies, like, Tyler Pansner, who you did that interview with,
Hmm.
um, he's a proponent of just screening for everything, full genome sequence, figure out what every possible thing that could be there. But at the end of the day, I think there's value in trying things for yourself, trying to get informed based on different trains of thought, different experts, different. There's value in a lot of different fields that you can consume, I guess.
Yeah, I agree.
Hey guys, Kian here. So there's a couple things I forgot to mention in this section, so I figured I'd just put a clip in. Essentially, I forgot to explain kind of my rationale behind delaying my PhD and doing a master's first. So in 2022, when I got sick, I was in the middle of visiting several schools that I'd been accepted to. Been accepted to the PhD programs in organic chemistry at Scripps Research in San Diego, Princeton, Stanford, Berkeley, and Yale. I got to visit a couple of them and then had to cancel my other visits and ultimately reject all the offers when I got sick. And I, of course, could have just reapplied that same fall and, started my PhD in 2023. But I actually decided against that, and I'm going to explain why. So at the time, when I applied in 2021, my plan was to pursue a PhD in synthetic methodology, either in CH activation or electrochemistry or photoredox catalysis. I thought, the implications and societal benefits to this type of research were superior to total synthesis. I liked the sustainability aspect of it, the creativity aspect of being able to visualize a transformation and then use your knowledge and skills to kind of optimize that and make it work for a variety of systems. And my plan after that was to go into academia. Now, while I was doing all the visits, it seemed like everyone else wanted to do total synthesis and wanted to work in industry. And that's not really something I'd considered in the past, and it kind of made me doubt what I wanted to do. So, while I was sick and having to reject all the offers, I had a bit more time to reflect on everything and realized I'm not quite ready to make that decision yet. I don't have enough experience in terms of deciding what I want to do. And I just didn't have enough experience in general compared to everyone else. Most people at the interviews had been doing chemistry in the lab for at least 3 years, whereas I'd been only doing chemistry experimentally for a year. But obviously, during that year and during the year where I switched into a more chemistry focused program before that, I had worked incredibly hard to kind of catch up. But I still felt like everyone had a bit of a leg up on me, and they were a lot more confident in their decision making. And I overall began to doubt whether, you know, a PhD in methodology is something that I wanted to do, whether academia was something I wanted to pursue, whether I'd be better off going the total synthesis route and then looking to switch to industry after. So these were all questions that I was having at the time, and I realized the best way to address them would just be to delay everything. I would get more experience. I would clarify exactly what I wanted to do. So that's what I ended up doing. I figured, okay, well, I can't really start anything official this year since all the deadlines are done. So let me take this year to try out total synthesis, which is what I have done for the past 8 months now. And then after that, I'll do a quick master's in methodology. And by the end of that, I'll have a pretty good idea of what I want to do, what I prefer, and that'll inform quite readily on which school I should go to. And yeah, so that's what ended up happening, and that's why I made the decision I made. One more thing I forgot to mention with regards to my health habits is that I do not drink or consume any other mind-altering or carcinogenic substances willingly, and I haven't for the past 4.5 or 5 years. And the reason for that, I guess I'll tell a bit of a story to go with it. So I went to a pretty special high school. You had to apply to get in. The learning was accelerated. You learned more content in a shorter time. So you basically gathered like all the majority of the smart, hardworking kids in the city into one high school. So I had to bus across the city to get there. And as a result of that, I was pretty sheltered in high school. I wasn't really exposed to any like partying or substances. My peers were all very studious and hardworking. Then once I started university, I was more kind of thrown into the middle of that sort of party culture. And, for about half a semester, got cut off there. For about half a semester, I'd say I, tried to experiment with that, see what it was like. And pretty quickly, I realized it's not conducive to my goals. At that point, I cared about my academics, I cared about powerlifting, and I cared about speed cubing. I didn't have any long-term goals in terms of what I want to do with my career. I knew I wasn't going to be lifting forever. I knew I didn't want to be the best at that. I knew I didn't want to be cubing forever. I just knew that eventually my academics were going to end up being the most important. And pretty much I noticed all three of them were negatively impacted. Yeah, just from like one night out, one night of drinking and losing sleep, pretty much. I noticed the next day, like, I can't study. My brain isn't working as well as it should. I can't cube. I'm 2 seconds slower than I should be. And 3, my deadlift single that was supposed to be RP7 was RP9. So just from that one experience, that one day, I made the decision then and there that drinking and partying was not my thing, that sleep was important, that, alcohol is pretty toxic to your health and your productivity, and just wasn't aligned with my goals. And ever since then, from like fall 2018 to now, I just haven't had a single drink or a drop or any other sort of substance. And yeah, that's what I've been rolling with. And obviously, after like learning more about the cellular effects and the chemistry behind it, the toxicity of aldehydes and epoxides that derive from drinking and smoking, that's even further reinforced my views on whether you should or shouldn't drink or consume substances. Final comment I'll make on the drinking thing. A lot of people have told me like, oh, come on, one drink a month or half a drink every now and then isn't going to have that much of a negative impact. And to that I say, no matter the impact, no matter how small, I still think it's too much. Even if it's over a lifetime point, quadruple 1% difference in productivity, output, health, anything like that, I just don't think it's worth it for me at all.
So, in regards to this and your health and the most important facets of health, what are some of those things to you? Is it like sleeping? Is it your diet? What is the biggest one? And also, how has chemistry helped you in optimizing that?
Right. So I think for me now, diet's definitely the biggest one. Um, Obviously, if I eat gluten, I'll get pretty messed up. But even other than gluten, I've always had issues with dairy, so I can't eat that. Also, trying to avoid seed oils for reasons we'll discuss later. What else can I eat? Nuts also give me issues. That's the most recent thing I figured out. So being pretty strict with my diet, avoiding the things I know I can't eat, and making sure I'm eating whole foods that are high in micronutrients and high in macronutrients, key macronutrients, especially protein as well. Obviously that's the obvious one, but I also eat quite a bit of kind of fermented foods, sauerkraut, those type of things for general gut health, and it's a bit more digestible than raw vegetables for me.
Yeah.
I also eat a little bit of liver every day. I know there's a bit of controversy or whatever around certain figures in that realm, but the nutrient profile is pretty good there. I actually enjoy the taste of liver, especially when it's cooked with onions. So that's something that's important to me in terms of cooking and what I cook in. Obviously, can't be consuming any processed oils, but I do cook in beef tallow that I make myself, as well as olive oil for low heat eggs. I've been trying coconut oil recently. I know you like that, but outside of diet, yeah, I'd say sleep is my second priority. I've always been pretty sensitive to loss of sleep. If I don't sleep 7.5 to 9 hours, I immediately notice that I physically feel more tired. I feel weaker. My brain doesn't work as well. So
Same.
that's my second priority for sure. And then after that is definitely exercise. just getting some blood flow, some cardiovascular movement, keeping your muscles strong, keeping your system supported. Everything comes together with that in the end.
Yeah. Thanks for
And in terms
sharing
of,
that.
oh,
Okay.
I think forgot to answer one section of that there. You asked how chemistry has helped. So I think
Yeah. Go
the
ahead, Shepard.
main way kind of learning chemistry has helped me with health is knowing the kind of biochemical implications of everything that I do. So from kind of, cell bio physiology courses, I learned what happens in cells when the system's healthy. And from organic chemistry, I learned the fundamentals of reactivity. Then when I took kind of pharmacology and medicinal chemistry courses, it brought things together and showed what happens when you take certain drugs or substances of abuse, or potential toxicities of things like alcohol or tobacco, um, or even like polyunsaturated fatty acids were taught at the undergraduate level in terms of oxidative damage. So we'll get into that later, but kind of knowing how these things are processed in your body by the liver and how they can, alkylate DNA, that type of thing makes all these consequences seem a lot more drastic. So it definitely makes you think twice about what you're consuming, and like what you're consuming when you know what it does to you.
Yeah. Really good point. That's exactly how I see things as well. I think you've been long enough in my page where I would post food pictures and then I'd say, hey, look, it's not just food. The next slide, it shows food with all the chemical constituents of it that you'd not even consider, but it's like you're ingesting kilograms of, or rather hundreds of grams of an amount of a substance that you don't even know is there, but still affects your physiology. All of this is
Mm-hmm.
chemistry in the end.
Yeah, exactly.
Nice. What do you do in your spare time, if you even have spare time? Because I
Yeah.
see you in the lab for hours, man. You're there from 6 a.m., 12 p.m. You sleep there. It's crazy.
Yeah, so you're kind of right on that. I don't have that much spare time. I do spend most of my time sleeping, doing chemistry, whether it's running experiments, reading textbooks, reading papers, or eating. Um, but other than that, I do still like exercise 6 times a week. I lift weights 4 times a week. I run once, and then I play soccer once. Or if there's no soccer, I'll just kick around a ball with friends, or play basketball with friends, or go for a high intensity sprint workout. But outside of that, I've kind of retired from speed cubing. It's something I rarely practice. Maybe once every couple of weeks,
Hmm.
I'll sit down and solve some cubes for half hour. Other than that, I really enjoy cooking. I've been getting into that recently as well. Kind of in the past year because of this health stuff. I like reading books. I've read maybe 12 to 15 books in the past year. I picked it up. I used to be a big reader when I was growing up, but kind of lost it. Picked it up again after I got sick, since it kind of became a metric for measuring how well my brain works. But
Hmm.
I've enjoyed reading quite a bit. I'll also tried to get back into guitar, playing the guitar. That's pretty enjoyable as well. But yeah, that's pretty much it.
Got it. What are you reading at the moment?
Right now, I think I showed this on my Instagram story. So I'm reading The Brothers Karamazov by Fyodor Dostoevsky.
Nice pick.
It is widely regarded as one of the best novels of all time. I'm like a third of the way through, and man, it's pretty engaging. It's the contrast between the characters and how they represent bigger ideologies is pretty fascinating.
I love that, man. Dostoevsky is always a nice read. Never read that one, but I like Dostoevsky in general.
Yeah. Hold. I think there's a bit of. So I think what's happening here. Do you see? Okay, I'm gonna just fix it and then see. I'll ask you if it's better.
Oh, with the sound, right? Are you able to hear the clicking sound?
No, I was actually looking at the video. There's a bit of like
I'm
sun
hoping
through the
that by
window.
the end of this doesn't have like a clicking sound throughout the entire interview. It might be my speakers. Let me see if I can fix this. Maybe if I use headphones and this is still capturing my audio. Let me try really quick. This way, it's not 2 hours of clicking.
Yeah.
Can you still hear me?
Yep.
Yeah, for some reason I still hear like that clicking. Speak really quick just so we can check. I'll
Yep.
edit this.
I'm talking. I'm speaking. What are you hearing? Is
I'm
it good?
hearing
Click, click.
everything's good actually.
Everything's good. All right.
Oh, the click came back. It might be just this. If it happens, it happens. But we'll roll
Yeah.
through with it. All right. So the next question I have for you: how did you, or how does somebody get to your the level of competency that you have with solving Rubik's cube? What did you do to get to the position you're in now?
Yeah. So I think I mentioned earlier it was kind of just an obsessive passion when I was younger, similar to the way chemistry is now. I just dedicated countless hours to practicing, solving, trying to learn techniques online. And it got to the point where I started when I was 13 or 14. And those first couple summers, I'd just be solving cubes for anywhere from 4 to 12 hours a day. And at the time, I think I improved faster than anyone had in history. I got down to like 8 or 9 second solving times within a year. And people thought I was, cheating or fake. And then, showed up to a competition, I was fine. So um, nowadays, there's a lot more kids who start younger and dedicate a lot of their time to it. So especially over the pandemic, there's people who started from nothing and are now world record holders. And
Wow.
yeah, it's pretty insane. So I'd say, kind of like any other thing, you just immerse yourself in it and practice it for as long as you enjoy practicing it, as long as possible, and try to learn every day from people who know more.
Got it. Very cool. Good to know. I might get into it. Let's see if I even. Alrighty, let's see. Your powerlifting ventures. What are your goals with powerlifting? Is it something that you see yourself doing in the long run, or are you becoming a more balanced athlete? What do you think?
Yeah, so I think for myself, I don't think I'll be competing again in powerlifting anytime soon, maybe further down the line in 3 to 5 years. But I think I'm in a similar situation as you, where I don't have kind of the consistency of being able to train for many hours a week, intense exercise to be able to support powerlifting with my academic ventures. The most significant implication of that is like the way I train in lifting is I do like 4 week training cycles, with week 4 being the heaviest. And I just every time I try to go into the lab or read a paper or read a textbook after a week 4 training session, I just feel destroyed. I can't focus as much, and it really slows me down. So, kind of because of that, I've put it on the back burner of definitely trying to be a more balanced athlete, train a bit more for hypertrophy, and keep a lot of cardio training in. So that's
Yeah.
there's no real major goals in that regard other than just trying to get stronger. I'm working in a lot higher rep ranges now, just sets of 8 to 10 on squats and deads, which
Right.
is a little tiring, but I kind of like it a little more than heavy singles and sixes and fives and whatnot. Um, but other than that, in terms of lifting, I'm now kind of prioritizing my coaching quite a bit more. Um, the way I started coaching is when I started university, I didn't know much about lifting. There was a club around here, like a powerlifting club at the school, and one of the older members kind of offered to coach me for free. He knew a lot more than me, but looking back on it now, we both knew almost nothing. And kind of through experimenting together, reading a bunch of books, looking at whatever we found on YouTube, Instagram from different people, we were able to piece together kind of a framework for what works and what doesn't. Then
Mhm.
he started coaching, 8 to 10 other people. He graduated. I inherited the club, and then by necessity, there were just like a lot of new lifters asking me what program to run, and I was like, I guess I'll just coach you for free, and we'll figure this out. So for the past like 3-4 years, I've been coaching anywhere from 5 to 15 athletes. I've definitely learned a lot. I'm hoping to continue learning there. Um, and yeah, so at this point, my main goal for that is to increase my technical toolbox as a coach and to help my athletes succeed.
Very awesome. I like that you mentioned how you just took a step back. You looked at all that's out there in terms of how to coach properly, powerlifting stuff, and you're able to analyze everything and come up with a framework. That's something I noticed after diving a little bit deeper into chemistry and math. It's like anything I think about now, I'm like, wait a second, I understand this really highly complex stuff. I can just take a step back, analyze everything, and see what I can get out of it in a really succinct manner and quickly too, because you have to consider a lot of things when it comes to building molecules or doing equation. It makes everything else that you do so much easier. And I like that you mentioned that.
Yeah, 100%. Definitely. Once you have that solid base, once you build the framework and have that solid base of knowledge for that encompasses the field, you have the freedom to dive deeply into specific topics and
Yeah.
use your tools to analyze it.
Awesome, man. So that takes us through the entire personal side of the questions that I have for you. Now we're going to get into more theoretical grounds. So for the average listener, we will get a little bit technical, but we do plan to simplify things. So after every point, once we're done, I'll say, okay, how can we summarize this in a simple, fashion? Why is it important? So that you understand why all of these topics are really, really interesting. And before we even get into that, one thing that I wanted to ask, because I did get this question before, is what even is an organic chemist? What differentiates organic chemistry from all the other fields? Because most people haven't even done a general chemistry class, and so they're like an organic chemist. What does that even mean? Can you explain on that?
Yeah, for sure. So, an organic chemist is someone who works with molecules and reactions that are hydrocarbon based. So that means they have carbon and hydrogen in them. The kind of classical definition is if it's a carbon containing compound, then it is an organic molecule. Um, the reason it's called organic is because carbon containing compounds make the basis of all the building blocks for life. All forms of life contain carbon containing compounds, a lot of hydrogen and oxygen containing molecules as well. Kind of the other elements involved are nitrogen, sulfur, phosphorus, chlorine. But anyone who's really working with carbon based compounds and there's some hydrogen, maybe some oxygens, then you can call them an organic chemist. The divisions between the fields, whether it's organic or inorganic, is a little bit arbitrary because once you start having metals involved, when it's kind of hard to draw the line between is it inorganic or is it organic, since there's reactions that are on organic molecules but use inorganic reagents. So the division is a little bit arbitrary, I'd say. But if the goal is to be making organic compounds that are built on carbon frameworks, then I'd say you're an organic chemist.
Hmm. And I would think that organic chemistry is pretty much a more analytical version of almost like herbalism, where people would take herbs and different plants and extract them through some process, and you'd get the concentrated form of the medicine. But with organic chemistry, you're actually getting the key molecule involved in all of this, and you're finding out how to synthesize it from scratch. So you're, like I said in the beginning, like you mentioned, you're doing Lego building with atoms, which is awesome to think about. But yeah, in a sense, I would imagine a lot of the things that people have done and cultures and civilizations have done in the past with plants and herbs was a form of organic chemistry, just a very rudimentary form.
Yeah, exactly. And that's pretty much where the field originated. A lot of the traditional medicine practices involved, you know, hot water, you put in some tea leaves, something comes out, you use it to treat a fever. They didn't know, but they're essentially isolating a natural product, which is a complex organic molecule, from that complex mixture and then consuming it. And um, those types of natural product isolation chemists of the past who were just trying to get some medicine out of some leaves ended up building the initial studies that inspired people to try
Yeah.
figuring out what's in those, and kind of those people interested in those same areas ended up realizing, oh, you can mix some things together and get something that's similar to what we see there.
Yeah. Awesome. Alrighty, let's start. So the first question I have for you is, what are your current projects with organic synthesis? And what were your past projects, things that you've done before, like the peptide paper? And finally, where do you see yourself going in the future with chemistry?
Yeah, for sure. So currently, I am working on the total synthesis of a natural product called quasin, and I'm working on a route that makes use of a gold catalyzed polycyclization cascade. So I'll kind of unpackage that and make it relevant to why we're doing it and what we're trying to do. So quasin is a natural product. It's found in nature in the wood of the Quassia amara plant. Um, it's been used in traditional medicine for digestion. It's one of the most bitter compounds in existence. It has some cool insecticidal properties, and it's essentially a terpenoid product. So it's the product of polymerizations of isoprene building blocks. So there's a lot of carbons in uh, five carbon fragments built together to make this molecule, and it's polyoxygenated. So there's a lot of oxygens on it, and the key thing that makes kind of the quasinoids cool is that there's a lactone as well. So there's usually 3 or 4 carbon-based rings, and then there's a lactone ring where there's an oxygen involved. This product was pretty much discovered a long time ago, at least 100 years ago. Structure was elucidated, I think, in the 60s, and it's been the target for organic synthesis for quite a while. There's a number of syntheses. Interest in quasin and quasinoids, which are kind of the broader spectrum of natural products related to that initial one, were pretty widespread in the 80s. There was a lot of research in that field in terms of trying to isolate them and trying to invent different ways to synthesize them chemically, since one of the molecules in the family was found to have pretty potent anti-cancer activities. So historically, that's why there's interest in these natural products. There's been quite a few syntheses in the past, but a lot of them are really long, not very practical, and just require improvement. The most recent synthesis was published last year, and that is quite an elegant one. It makes use of some cool radical chemistry. It's pretty short with 14 steps, but one limitation of it is that it's very target oriented. And what that means is it's very tailored to making one product and not necessarily granting access to the whole family. And the reason you want to access the whole family is, let's say tomorrow someone discovers a new one from a plant that could be a drug. You'd want to already have a method to be able to make and access the family so that you could quickly synthesize that drug-like compound, test it further, maybe do some preliminary studies before then, investigating it further. So in terms of kind of pharmaceutical interest and medicinal campaigns, it makes sense to have synthetic routes that are modular and diverse in the way you're able to access different molecules. So that's kind of our inspiration for undertaking this. We wanted to kind of make a more modular approach to this family of natural products. And we selected quasin, which is kind of the prototypical simple one, as our model to try to synthesize. And our lab works not primarily, but historically has worked in gold catalysis. So we are using a key step involving a reaction catalyzed by gold. And I'm not going to say anything further about that, since in these types of projects, you generally want to keep it a bit secret, since there's a bit of competition between different research groups around the world. So you don't want to get scooped by giving away too much, but that's essentially what I'm working on ever since from September to now, essentially.
Awesome. Very, very, really cool. What was the past project that you worked on with peptides and transglutaminase?
Yep. So before this, I was in a different research group for my honors project in my 4th year. And there I was working on developing inhibitors for an enzyme called factor 13. So this was kind of a more medicinally relevant project where we were interested in making inhibitors for factor 13, which is an enzyme involved in blood clotting. It's the very final enzyme in the clotting cascade. And there's recent evidence that inhibiting it could produce a blood thinning or anticoagulant effect that could be kind of less severe than current drugs that are used for clotting conditions. So my task essentially was to synthesize a bunch of different peptides and test them for inhibitory activity against this enzyme, see if we could improve on previous inhibitors that had been made. And essentially what we ended up doing is looking at the structure of the target enzyme and some of the off targets and looking for key differences, trying to change the structure of our inhibitors to target the desired enzyme factor 13 and not the off target, which was transglutaminase 2, and testing them out in vitro assays to see what worked and what didn't. By the end of the project, we essentially realized that none of our inhibitors were better than the lead compound that we started from to base our studies off of. So we ended up kind of shifting gears and making a fluorescent probe. Essentially, the purpose of that was to irreversibly attach a molecule carrying a fluorescent piece to the enzyme factor 13 so that you could selectively label it in biological systems, whether it's in cells or in animals. And then you could further study where factor 13 localizes, where it's active, and its response to clotting.
Very awesome stuff. When it comes to factor 13, what is it that gets made? Is it fibrin, the final product? Yeah.
Yeah, so it cross-links different fibrin proteins into cross-linked hard clots. So fibrins are proteins involved in clotting, and essentially if factor 13 isn't active, you have these kind of like loose and separated fibrin soft clots. But once it cross-links between the glutamine and lysine side chains, you essentially get these linear peptides that get attached, or these linear proteins, sorry, that get attached. So now you have these large macromolecular complexes that make the clot a lot more hard and resistant.
Yeah.
To
so
degradation.
Interesting that the cross-linking reaction is one that's seen with so many pathologies. Like the first one I can think of is advanced glycation end products, the cross-linking of lysine to sugars, glycosylation, and similar processes occur in response to like the pathology. The cells respond to it in an inflammatory fashion. The body can produce clots from it. It's all interesting how a single reaction type can dictate the entire pathology of multiple diseases. And if you know the reaction mechanism, you can expect what the disease outcome would be.
Yeah, exactly. If it's one of those things where biology is so tightly regulated, and if you have little too much of that cross-linking or not enough, then the implications can be pretty widespread.
In regards to your goal with catalysis, we were talking before this interview even started for a couple of minutes to check if everything worked, and we talked about how different metals are unlikely to provide the right reaction mechanism for you. And I wanted to ask you if you can expand on that. Like, why is it that certain metals are good for, say, alkyne reactions or alkene reactions, and others aren't?
Right. So in terms of transition metal catalysis, each metal kind of has unique properties. They have different number of electrons in their valence shell and their d orbitals. They have different, let's say if you have a heavier metal, you have more diffuse and soft orbitals that are going to be more likely to interact with diffuse and soft ligands and diffuse and soft substrates. You have different electronegativities depending on where they are, whether they're early or whether they're late. And all of that's going to affect not only the polarity of the bonds, but also what types of atoms they interact with, the geometry of those, how they affect the electronic structure of the ligands and substrates they interact with.
Mm-hmm.
So there's a lot to consider in terms of transition metal catalysis, and not only the metal, but also the supporting ligands. It's essentially the additives as well. So there's a lot of factors to consider,
Yeah.
but the understanding of those systems has been greatly improved in the past, I'd say, 50 years.
Right. Yeah. One thing I noticed when doing inorganic chemistry is how much more room for error there is in the expected reaction, the expected outcome. And it's so interesting that you mentioned all of these aspects: the electronic configuration, the d orbital type, whether it's if it has valence electrons in that specific d orbital or not. All these things can be changed in a matter of a setting, like where there's a little bit more red light or yellow light or blue light, because the metals absorb those lights, and changes all the reaction mechanisms entirely. It's crazy to consider how much isn't known or remains to be understood about transition metal catalysis in many different fields, not just organic chemistry.
Yeah, definitely. And kind of the types of diversity and reactivity with metals is pretty overwhelming. So if you think about it,
Yeah.
something like 50 to 100 metals, depending on how you count. And in terms of organic molecule or organic atoms or organic associated atoms, there's maybe, I don't know,
Yeah.
10 to 25 or so. So it doesn't make much sense to go atom by atom or element by element.
Yeah.
Sorry, I think I said atom instead of element like 5 times there, but it doesn't
You're
make
good,
much
man.
sense to go element by element and try to understand the reactivity of each individual element. It goes back to building a framework of reactivity principles and then being able to generalize that and apply to each different mode of
Mhm.
catalysis.
So if we can synthesize in a simple fashion, your project is basically using gold as a catalyst to make a natural product found in a bark of a tree, right?
Yep. Essentially, there's
And
a natural product in the bark of a tree. There's related products that might have cool medicinal applications. The ways to make these aren't that simple, and we want to improve it. And we're going to try to use a reaction catalyzed by gold to make the synthesis of this more simple.
and then in regards to your past project, you essentially developed a new molecule from a starting pharmaceutical to see how it would stop the enzyme that makes blood clots, essentially.
Yep.
Awesome. Now, where do you see yourself going with chemistry in the future? Do you see yourself getting a PhD in chemistry, total synthesis? Do you think you'll branch out, things like that?
Yeah, so in the future, I definitely see myself pursuing a PhD. I still have not decided what field that will be in, whether it's total synthesis or synthetic methodology development in catalysis. So for now, I'm working on a total synthesis project. And in the fall, I'll be starting a master's. I'll be staying here at the University of Ottawa, switching to a synthetic methodologies lab, where I'll be working in the field of nickel or palladium catalysis, trying to activate strong bonds like CH bonds and CO bonds for doing different couplings or functionalizations. So, and then the goal with that is not only to, improve all my skills and knowledge, but also to give me more exposure to the catalysis side of things, since that's something I've never worked on before. And then hopefully once I've experienced both catalysis and total synthesis, I will be able to decide which would be best for me to pursue in my PhD.
Fascinating stuff. What about anything with like photoredox catalysis? Because that's one I'm really interested in recently.
Yeah, so photoredox is definitely one of the major fields that's developed in synthetic methodologies in the past, I'd say 10 years. And pretty much every journal you look in is going to have some photoredox stuff in it. There's labs across the US, across Canada, working in that field. So if I do pursue synthetic methodology development in my PhD, photoredox will definitely be one of the things I consider. It's also becoming more prevalent in industry, so they are looking for more people with experience in photoredox and how they can implement it in their processes. So it's definitely a something to look into.
Really cool stuff. All right. Let's see. So with gold catalysis, I think this is something that I came to understand after I did a little bit of inorganic. Is like these metals that we categorize as precious rare earth metals that we value for economic purposes, like gold-based currencies, silver-based currencies, or in general, you want to hold some gold and silver because they retain their value over a period of time. A lot of people think of it as it's still just another system that doesn't have any use. But I've come to realize it's like these metals are so useful for so many different chemical processes and industrial processes that without them, the society we live in would be blank. There would be nothing to consider, nothing to live in really that's functional. What do you think about that? The value of transition metals based off of their use in industry and then the economic aspect of this?
Yeah, that's a great question. So, kind of to address it, I'm going to start with a bit of a historical kind of perspective of how metals have become to be so prevalent in organic chemistry. So, going back maybe 100 years ago, the metals used in synthesis were the early metals, non-transition metals. They were used in stoichiometric amounts, to make grignards or organolithiums or organozincs, or they were just used as reductants or oxidants. And only in the past, I'd say 50 to 70 years, have more precious metals come to be more widespread with the advent of catalytic transformations, specifically kind of cross-coupling revolution. So around the 70s is when palladium catalyzed cross-couplings started to become all the rage. People essentially discovered that with just a stoichiometric amount of palladium metal, you can cross-couple, or you can have one molecule, another molecule, and join them together with a palladium catalyst. So in catalytic amounts, so let's say you have 10 of this, 10 of that, you only need 5% of palladium to form that bond, rather than having to take this one, form a grignard, and then take this one and form something else with it. For these stoichiometric metals, catalysis kind of removed the need to do all that and kind of revolutionized the way people make molecules. And after that, or around the same time, there was also metathesis chemistry being developed using ruthenium for closing rings based on alkenes, polymerizing things to make different materials, stitching things together through cross metathesis. There's also a lot of developments in hydrogenation, so going all the way back to like what's the word I'm looking for here? Heterogeneous hydrogenations on metal supported surfaces, going to now like asymmetric homogeneous catalysis using iridium or ruthenium or rhodium. So all these metals have become pretty much indispensable to organic chemistry. They've changed the way we make bonds, we make molecules. They've made syntheses a lot more practical, a lot more efficient in terms of the number of steps. All of these reactions are widespread in industry. And now with photoredox catalysis, the use of iridium is skyrocketing. And all these metals are very precious, very expensive, very crucial to all these processes. But there's issues associated with them, right? They're not that sustainable. There's only a limited supply available on the earth. There's potential toxicity if you want to use it to make a drug. Even if you get 1 ppm through at the end, that's something that contaminant could potentially cause toxic effects. And I actually have some data pulled up on the cost of some of these precious metals as of 2023. So some of these late heavy transition metals that are viewed as precious, like ruthenium, rhodium, palladium, iridium, platinum, silver, gold, cost anywhere between hundreds to thousands of dollars per ounce think gold is $1,788 per ounce. And then there's iridium, which is about threefold more expensive at 4,300. Rhodium is another threefold more expensive than that, upwards of $13,000 per ounce. Whereas base metals, things like iron, cobalt, nickel, and copper, which are widely abundant in the Earth's core, are 4 cents to a couple dollars per 32 ounces. So thousands of fold less expensive.
Fascinating. And this makes me think of the process in physics. I forgot what exactly it's called, but essentially when sun or solar bodies make atoms through fission and fusion, the process that happens generally, that iron is the last atom to be made because anything afterwards is just not energetically favorable. But it makes me think of the processes that they're developing for nuclear fusion, and how maybe through just decay, some of these fused atoms can become some of the more rare transition metals. Like that might be the future once we run the course of the available metals, which I don't think would be anytime soon. But yeah, I think only then will their value maybe reduce, or they might be less appreciated overall. But right now, like you said, what's the price for iridium?
Iridium, 4,300 per ounce.
For
I think iridium is one of the most concerning, since I think the supply is quite low, and a lot of these photochemical or photoredox transformations that are being reported in literature and implemented in industry are iridium dependent. Even something like palladium, which has become so widespread, is pretty expensive. And with these homogeneous catalysts, the majority of the time, you're not going to recover it from the reaction mixture.
That makes sense.
So
that puts
I just think these are going to get more and more expensive as the years go on, and they're used more and become more prevalent in chemical synthesis.
And that puts a strain on laboratories and institutions around the world, where only certain ones will have the grants or the money in general to actually buy these metals for synthesis projects. That's going to be pretty bad.
Yeah, but on the other hand, it has also opened up the field to kind of a move towards more base metal catalysis. So nowadays, kind of an emerging trend in literature is to try to use cheaper and more sustainable, less toxic metals to catalyze a lot of the same reactions that are catalyzed by the more expensive metals. So maybe 10, 15, 20 years ago, there was a huge trend of people trying to replace a lot of the palladium catalysts for cross-couplings with more affordable nickel catalysts. And then out of that, people actually discovered a lot more modes of reactivity that nickel can engage in, but palladium can't. So I think nowadays, nickel chemistry is becoming a lot more widespread. We're only tapping into the potential of that recently, but there's still quite a few transformations that palladium is just always going to give higher yields for, and it still doesn't make sense to use nickel.
Which one is the heavier atom, nickel or palladium? I don't recall.
Palladium, yeah.
Interesting. I wonder if the radius and the orbital radius plays a role here. Then I've seen the use of nickel catalysts in photoredox catalysis, where they're achieving like nickel 1 or nickel 4 oxidation states, which is very unusual for that metal.
Nickel and palladium are both in the same group. They're group 10 metals, so they have the 10 electron configuration, and their most stable configuration is generally the 2 oxidation state. Palladium generally cycles between 0 and 2. You'll rarely see anything other than that. Sometimes people invoke that there's a palladium 4 in the mechanism. That's a little bit more rare. But nickel essentially has the reversible transformations anywhere from 0 to 3. Nickel 0, 1, 2, 3, so it can have a D10, 9, 8, or 7 electron configuration. So that allows it to access either cycles of 0, 2, doing the same transformations palladium does, or 1, 3, doing the same transformations palladium does, or it can cycle 1, 2, 3, 1, or essentially access single electron transfers and 1 electron radical pathways that are not accessible to palladium. And that's what makes it a bit more diverse in its reactivity in terms of being able to engage with photocatalysts. And the other kind of distinguishing factor is that nickel is a little bit less electronegative, so it's more electropositive, which means that nickel 0 is more reducing than palladium 0, which means you can insert into stronger bonds like carbon-oxygen bonds that palladium can't access.
Is there any reason that you can think of as to why it'd be more reducing despite being D10 and then within the same group?
Yeah, so the general periodic trend for electronegativity is that it increases up and right, but so within this group, you'd expect that nickel should be more electronegative, but it's actually the opposite. Transition metals display the opposite trend, where they're more electronegative as you go down the group. And I used to know the explanation of this pretty well, but I believe it's to do with the um, kind of the difference between adding an electron into the d orbital versus adding another proton into the nucleus. The shielding effect of that d orbital isn't as significant as the uh, kind of effective charge increase from adding another proton.
Right. I wonder if, or have you ever seen anything where they discuss possibly the John Teller distortion effect since it's a higher d orbital?
Yeah, so I've studied the John Teller effect in kind of my intro transition metals course, and yeah, so that would be more prevalent in the heavier metals, and I think it's heavily electron configuration dependent though. So if they have the same configuration in that zero oxidation state, you're not going to get any John Teller since you have a symmetrical electron configuration with the D10. There's
But when it oxidizes, it goes down. Say, for example, from D10 to D9 for the first oxidation state, and then
yeah.
that
So
might be what causes
in
the
that
distortion.
case, yeah, in that case, the one oxidation state isn't really accessible to palladium.
Fascinating stuff. How can we summarize this for people?
I'd say the summary for non-chemists is that precious transition metals are crucial to organic synthesis. They have revolutionized how people make molecules that are important in medicine, in agrochemicals, in fragrances, and all these different industries. And there's a limited supply of these in nature. Um, and there's a lot of effort now to use cheaper and more abundant metals to kind of do the same reactions, but also do more new reactions that the more expensive and rare metals can't do.
Awesome. Thanks, bro. That was perfect. So let's transition into organometallic chemistry. What is organometallic chemistry then? Since we talked about organic chemistry and you said how at some point the fields they coalesce essentially, there's not that much of a divide, but still organometallic chemistry is its own thing. It's almost like an art in synthesis. Could you expand upon that and then we'll go into some of the stuff here?
Yeah, for sure. So organometallic chemistry kind of bridges the gap between inorganic and organic chemistry in that you have these metal-based complexes, right? Transition metal complexes in different coordination states with a sphere of ligands around them, around a metal center. But you also have carbon. So you have kind of the classical definition of organometallic chemistry is you have a metal carbon bond and that it's halfway between organic and inorganic. So, thus, the reactivity trends are also halfway between organic and inorganic. So, in organic chemistry, you generally have covalent bonds. They can be polarized, but generally they're covalent, where the electrons are shared between the atoms. Whereas in inorganic chemistry, you generally have more dative interactions, or rather more ionic bonding. Um,
Hmm.
Organometallic chemistry is somewhere in between that. You have slightly polarized covalent bonds that are not necessarily covalent. You have bonding and back bonding. You have kind of Lewis base Lewis acid interactions. It's a lot more complex, and even putting these labels on the type of bonding is heavily
Right.
debatable. But since the bonding is intermediate, the reactivity is also intermediate. Let's say you have a carbon lithium bond. Um, that's formally, an organometallic species, but lithium is traditionally more kind of inorganic element because it's not a transition metal. That's heavily polarized, and you're going to have a very reactive system where the majority of the negative charge is on carbon and the positive charge is on lithium. So it's almost like an ionic bond and almost like an inorganic character. Whereas if you have an organometallic complex, let's say a carbon palladium bond, that is a little bit polarized towards the negative charge on carbon, but those electrons are a little bit more shared. It's a bit closer to being a covalent bond, and it's not so reactive. Then if you go to more organic chemistry, let's say a carbon chlorine bond or a carbon oxygen bond, that's polarized in the opposite direction. Now it's a covalent bond by almost all definitions, but the electron density is on the chlorine atom or the oxygen, and the carbon atom is now positively charged. So organometallic chemistry gives you kind of access to this unique intermediate reactivity mode that is also kind of by definition more diverse than the two fields that make it up, because you can have all the variation in organic chemistry, all the variation from inorganic chemistry, and combine it together. You have all these different d orbital splittings, different metals, different polarities, electronegativities, ligand effects, steric environments around them, coordination number, the coordination mode. You can have bridging ligands. It's just the amount of complexity is vast. The amount of diversity and reactivity and molecules you can make within this field is vast, and subsequently the applications, whether it's in biology or materials, are seemingly unlimited.
Yeah, seriously, especially in materials from what I've seen. I think one way to really summarize why it is that organometallic chemistry is so unique is at some point the d orbitals in metals they become the dominant character, and then the s and p orbitals become almost like core electrons depending on oxidation and stuff. Whereas with organic compounds, you have s and p orbitals that are the dominant. And so you have this beautiful dance between different electronic orbitals that naturally you wouldn't get otherwise with just organic or just inorganic. And for those listening, when we talk about p orbitals, d orbitals, s orbitals, that's just the configuration that electrons occupy in atoms. And usually, when you think of an atom and an electron, you think of it just orbiting the atom. In reality, they fall into these beautiful petal-like structures or sphere-like structures that allows chemistry to occur. And it's only through matching the structures and the electronic energy that chemical reactions can occur in the first place. So when you combine organic and inorganic compounds, you're making these beautiful structures interact in ways that they normally would not. Is that correct? Do you think it's a good way to put it?
Yeah, I think it's a great kind of analogy or simplification.
Awesome, man. So in regards to organometallic chemistry, how do you see the field advancing, considering, for example, you talked about iridium-based catalysts, but then there's a move towards the less precious metals. What do you think?
Yeah, for sure. So I think that's one major advancement that I'm expecting, or that's already happening, the move away from kind of the heavier, expensive, and rare metals to more base metal catalysis. So trying to avoid the use of iridium, palladium, platinum, ruthenium, and a move to more, nickel catalyzed chemistry, copper chemistry. Even iron is starting to uh, be discovered as a tool for doing things only thought to be possible with heavier metals. So that's
Wow, that's
definitely
interesting.
something that's going to blow up, I think, in the next couple of years. Even for photochemistry, a lot of people criticize it and say that it'll never be viable long term because of the reliance on iridium. However, the iridium isn't actually crucial to the process, since all you need is something that can absorb a photon of visible light and act as an oxidant and reductant. And in that sense, kind of the organic molecules can serve as photoredox catalysts. So
Hmm.
something like a dye or like a stain or something that is heavily conjugated and can absorb light of visible wavelength. Um, yeah, so organic molecules are becoming more prevalent as photocatalysts. So I think there would be a bigger move towards that. Otherwise, in terms of, uh, I will preface this by saying, like, my perspective of where organometallic chemistry is going is mostly from the perspective of a synthetic organic chemist. So I'll be mainly talking about the applications in organic synthesis. But the other field that I see exploding, or the other two fields, are CH activation and electrochemistry. So I think those are going to continue to expand in the next couple of years. I'll just give a bit more background on what those are. So CH activation is where you take a bond between carbon and hydrogen and you use that to directly make a new bond, whether it's to another carbon atom or boron or chlorine or fluorine or oxygen, you name it. Essentially, you start with a carbon hydrogen bond, you use some sort of metal catalyst to make a carbon metal bond, then you treat it with another reagent to make uh, the desired bond, whether it's carbon carbon or carbon something else. And this is revolutionary because in the past, the standard method for functionalizing carbon hydrogen bonds was to first make it into a halide, or like a carbon bromine or a carbon iodine, then convert that separately into a carbon metal bond, and then in a third step, treat it with another reagent. So essentially, you're doing 3 steps to make one bond, and a lot of those steps are inefficient. They require toxic reagents that are expensive, dangerous to handle. You're losing yield. There's selectivity issues with the installation
Hmm.
of the bromine or iodine halogen at the start. So there's a lot of purification demand. Whereas recently, I'd say in the past 15 to 20 years, CH activations emerged as kind of a direct method for functionalizing molecules, and I feel like that's going to continue to revolutionize synthesis in the coming years. There's a lot of challenges still to address in terms of regioselectivity and stereoselectivity, since carbon-hydrogen bonds, well, there's a lot of them in a molecule, especially an organic molecule. There's anywhere from 5 to hundreds. So trying to develop catalysts and systems where you can discriminate between the different carbon-hydrogen bonds and only functionalize that one position is kind of a major challenge in the field. Also, unactivated carbon-hydrogen bonds. So a lot of literature in this field has been focused on carbon-hydrogen bonds that are easy. Let's say they're already acidic, they're already beside an electron withdrawing group, or they're sensitive to H-atom abstraction, they're beside something that stabilizes a radical. Those type of functionalizations are pretty widespread nowadays, whereas performing CH activation on a position that isn't activated, so it's just purely aliphatic, there's no activating group around, that's been a lot bigger of a challenge. So I think the methods and catalysts for achieving that are going to continue to improve in the coming years. I also mentioned electrochemistry as another modality of catalysis that I think is
You
going
mind if
to...
I cut you off?
Yeah,
Quick?
go for it.
I don't want to miss this question.
Yeah.
Then we'll go over electro. But you mentioned with CH activation, if it's highly aliphatic, it won't activate likely. I can't help it, man. But the first thing I think of was like, oh wait, saturated fats is a perfect example. Is this? There we go. Okay, we'll talk about that later.
Yeah, we'll get there. But essentially, anything adjacent or nearby to a CH bond is going to make it easier to access, right? Whether it's an amine 5 bonds away, or a pi system 1 bond away, or an oxygen directly bonded to that carbon, that's all going to make it easier to activate that CH bond with a metal, whether it's through deprotonation to form an anion, or oxidative addition into that carbon-hydrogen bond, or a radical H-atom abstraction. So yeah, that's we'll cover that in the later sections.
Awesome. So yeah, go over the electrochemistry, because this is the first time I'm hearing somebody besides myself think of, wait a second, it's possible that electrochemistry might have a lot of the answers to a lot of these problems currently in many different fields of chemistry. What do you think, and what were you thinking over the past couple of months? I assume you've been looking into this.
Yeah, so in terms of electrochemistry, it's been, things like electroplating of metals onto surfaces has been known for probably 100 years, where you essentially use an electrolytic cell, apply potential, and it'll cause the reduction of a metal from the solution onto a surface. And it's gone pretty much ignored in organic chemistry for decades. There's been maybe 1 or 2 key transformations that involve electrolysis in chemistry, but they haven't been used that often. Now, in recent years, it's been found that electrochemistry is actually a pretty useful tool for organic synthesis, especially when paired with transition metal catalysis. It's kind of a similar tool to photoredox catalysis, in that the strength of photoredox is that you're not using any stoichiometric oxidant or stoichiometric reductant, right? In a lot of older chemistry, you would have to use 3 equivalents of zinc or 5 equivalents of magnesium, or something to pump in a bunch of electrons into the system to cause these reductions, or you'd have to use a lot of oxidants that are expensive, they're toxic, they're dangerous, all that stuff. Whereas in photoredox catalysis, the same catalyst, or you essentially catalyze the oxidations and reductions needed in your reaction, and that's mediated by the catalyst, which absorbs light, and then now you have a singly occupied molecular orbital, right? You start from the ground state with 2 paired electrons, you photoexcite up to 2 singly occupied states, and you're now reducing, you have a high energy electron that can transfer, or you have a low energy electron that's orbital that's empty or singly occupied that can accept an electron, so oxidize the substrate. And if you accept one, now you're the reduced metal, and you can give that other one away at another point in the catalytic cycle. So that's where photoredox comes in. But you can kind of see the same thing happening with electrochemistry, right? You can give an electrode up at the anode and take one at the cathode. And so once you incorporate that with metal catalysts, let's say nickel, let's say you want to achieve a nickel coupling where you want to access nickel 0 and nickel 3. A lot of times in the past, you would have had to add a stoichiometric reductant to get nickel 1 down to 0. Whereas now with electrochemistry, you can just get that nickel 1, have the electrolytic cell running, reduce it to nickel 0, then it does the oxidative addition to give you nickel 2. Then at the other side, at the other electrode, you can oxidize the nickel 2 up to nickel 3, and then it can do the chemistry again. So kind of the use of electricity as a sustainable resource, right? If you can make the electricity sustainably, then it's a sustainable source of electrons to run your chemistry. That's a major advantage of electric catalysis. The other one, I think, is that you can tune exactly the potential you want, right? If you're just dumping in zinc, like zinc 0 metal, that's going to have a specific reduction potential, and it might destroy your molecule. It might do the thing you want, but it's going to be, a certain number, whether it's minus 1.7 volts or whatever. With electrochemistry, you can essentially just turn the dial to exactly the number you want and have it selectively do the chemistry that you want.
It's all based off the same SI unit of electron volts too. It's like it's all there. It's always been there. You just had to find a way to put it all together in terms of like an experimental model, and it makes perfect sense. You also don't lose your catalyst this time because it's not bonded to organic molecules. It's there, and you can, if you want to do like an extraction, I think it becomes a lot easier of just a pure metal, right?
I think it depends in that case. So it would, even though the reaction itself is technically heterogeneous, since you have processes at the electrode surfaces and then processes in solution, the metal catalyst in that case, whether it's nickel or something else or zinc, would still be homogeneous. So I think purification would be a challenge. But yeah, the other thing I forgot to mention there is electrochemistry and photoredox catalysis. Not only have they made things more catalytic and less reliant on stoichiometric harmful reagents, but they've also allowed for the access to reaction modes that weren't ever accessible before.
Right, I've heard.
Since they do these sort of single electron oxidation or reduction reactions, they've kind of brought radical chemistry back into the spotlight. There used to be a lot of work on radical chemistry a long time ago, maybe 70s and 80s, and then ever since then it's been kind of two electron or polar bonds being formed and broken. But now these reductions and oxidations mediated by electrochem and photochem have allowed for just a revolution in how we disconnect molecules using kind of radical approaches.
Awesome stuff. And if we can summarize this in a simple manner, I'd say it's that essentially any kind of reaction is ultimately the transfer of electrons. And if you can do reactions with molecules, you'll get some kind of transfer of electron that's very defined. But with photochemistry and electrochemistry, you can go even further with the dial and define it at an even smaller interval where you can just have one electron movement per molecule, and that can cause some kind of reaction that otherwise you would not get with two electron movements with organic molecules. Would that be a good way to summarize this?
I'd say that's a pretty good way, yeah. A really good example of that would be decarboxylation, right? So everyone not everyone, but if you've taken some sort of organic chemistry or biochemistry, you'll know that decarboxylation is a common process where you lose carbon dioxide. And typically the way this works is you have carboxylic acid, right? CO2H plus or CO2H, and then it's acidic, so you can lose a proton and get CO2 minus, and then you can lose that as CO2, leaving a negative charge on the carbon atom next to it. And usually this only occurs if you have another electron withdrawing group beside it. So this is really common in biology. If you have a beta keto acid, you can decarboxylate it and get an enol of a ketone or an enolate of a ketone and use that in subsequent chemistry. That's pretty prevalent in the biosynthesis of quite a few classes of natural products. But in polar chemistry or organic chemistry, that's not that common, right? Whenever you want to decarboxylate, you're not always going to have a withdrawing group beside it. And if there's no withdrawing group beside it, you're going to have to heat the thing up to 500 degrees Celsius for it to go. On the other hand, if you do this photochemically or electrochemically, you can oxidize the carboxylic acid from CO2 minus to CO2 radical. Now, that radical decarboxylation happens at room temp, like almost instantly, and you get a carbon-centered radical. Then you can use that carbon-centered radical to do even more chemistry. You can add to an alkene to form a carbon-carbon bond. You can couple to another carbon-centered radical that's also been generated from another decarboxylation. You can do a cross-coupling of two different carboxylic acids, or you can use that carbon-centered radical to then bind a metal, right? Say you have a nickel 1, and then it combines with that carbon-centered radical, and you get a nickel 2. and then I don't know, you reduce it back to nickel 1, you oxidatively add into an alkyl halide, and now you've cross-coupled something else. So access to carbon-centered radicals
cool.
has been made much more easy or much more efficient with the use of these methods, allowing that single electron chemistry.
Now we should transition into the biochemistry, since you already brought it up with iron-based catalyst, how there's a push from palladium-based and other precious metals to more common metals like iron, and the use of these organometallic compounds in biochemistry, because it still happens in biology. It's just that most people don't even think about it. Let's go into that. What are some ways that organometallic chemistry occurs in biology, and why is it important?
Yeah, for sure. So I'll start with a couple like kind of generic connections between concepts in the fields. So, there's a lot of biosynthetic routes. For example, let's take um, turning glucose into ethanol or then to acetic acid by fermentation, right? Cells do this all the time. It's part of their metabolism. And, for making acetic acid, which is an important industrial product, you can, culture cells to do this for you, but that's quite inefficient. Whereas the organometallic chemist route is to use something completely different, a rhodium complex, and HI, hydriodic acid, to from methanol. So you're essentially carbonylating methanol, inserting a carbon monoxide unit. So you're achieving the exact same thing as the biological system, but using an organometallic complex that makes it more industrially viable. Now, on the other hand, you can kind of use the inspiration from nature to make something more efficient in uh, organometallic catalysis. So that's the field of metalloenzymes. So the way enzymes in biology catalyze reactions is generally by creating the right steric environment so that the reactant and substrate can come together, providing some hydrogen bond donors and hydrogen bond acceptors to stabilize the transition state. Maybe there's a metal or a cofactor in there, but a lot of time enzymes kind of accelerate the same reaction mechanism that happens naturally. Obviously, there's a ton of enzymes that have different cofactors and different reactive positions as nucleophiles that change the mechanism. However, there's a vast spectrum of enzymes that don't change the mechanism and simply just stabilize the same intermediates and transition states. On the other hand, organometallic catalysis, the way it's used in organic chemistry, generally just provides an alternative reaction mechanism and doesn't do so much in terms of tuning the sterics and electronics around the reactive site. However, in recent years, with the advent of kind of like designer ligands, so you have the metal, you can kind of design all this complex ligand system around it to specifically tune the reactive environment. And organometallic complexes in the lab have been able to replicate enzymatic reactions in terms of selectivity, stereoselectivity, all that sort of thing, just by tuning the sterics and being more enzyme-like, and kind of the word metalloenzymes being thrown out of there. So those are just kind of like two conceptual connections, but now I'll get into kind of more direct connections or applications rather of organometallics in biology or organometallic biological complexes. So the first one I thought of is cisplatin. Do you know about this?
That's the dichloroplatinum drug used for cancer, right?
Yeah, exactly. So it's essentially it's technically an inorganic species because it's like diamino dichloroplatinum 2. So there's no metal carbon bond, but it's an inorganic molecule that's a cancer drug. And the way this works is when it goes into cancer cells, which are very low in chloride compared to normal cells, the chlorines dissociate and you associate two water molecules. Now, chlorine is anionic, or chloride is an anion. So when you lose the two chlorides, you now formally have platinum 2 plus. And then when the water comes back, water's neutral. So now you still have platinum 2 plus. Now, this platinum 2 plus is very reactive and electrophilic. So it can then alkylate or metallate DNA at guanine residues. So essentially two guanines on the same chain are going to get linked to this platinum. And you're going to have this adduct, which is going to prevent it from replicating or repairing, and you're going to eventually kill the cancer cell. So this type of reactivity is very organometallic based, and it's cool, I think, that you can involve this in a biological system and have it work as a drug.
You mentioned alkylate or metallate, right? That's the term for this?
I guess metallate.
Metallate. In
Yeah.
molecular biology, they call it intercalation or intercalating. It's interesting. It's like different, same thing, but just weird how the fields describe this stuff.
Yeah.
But yeah, that's fascinating to consider with the reactions. I didn't even think about the water being neutral, and so it still maintains electrophilicity. Still maintains electrophilicity. Really interesting stuff. What do you think? For example, of something like cisplatin, is there selective targeting to guanine, for example, or could it be other potential biomolecules that have a similar electric potential that can donate to platinum?
Yeah. So I think a lot of the toxicity that's observed from it is due to just off-target metallation or other Lewis acidic functionalities on biomolecules. Proteins have some pretty nucleophilic sites, the lysine and cysteine residues. That there's that nucleophilic
Hmm.
amine and thiol, which can probably functionalize there. But generally, um, the target is that guanine residue of the bases of DNA, since it's a pretty electron-rich heteroaromatic system, and that nitrogen, I think it's nitrogen 7, is where the majority of that electron density is localized.
Yeah, eight or yeah. Damn, don't recall now. But yeah, I see what you're saying with the positioning. Okay, cool. So
I
what
have a
about vitamin B12?
Yeah, that's
Oh, go ahead.
exactly what I have written down next. So
Go ahead.
the main true organometallic complex in biology is vitamin B12. It's a cobalt 3 complex with a carbon cobalt bond, and it's involved in quite a few different metabolic pathways. Its main role is to transfer methyl groups around from like tetrahydrofolate, 5-methyl tetrahydrofolate. It's involved
Hmm.
in the amino acid biosynthesis. So think what is it, methionine and homocysteine. So it shuttles that methyl group around. The way that works is you just cleave the carbon cobalt bond. Um, this is pretty. So the way I'll talk about B12 is more like from an organic perspective, since what I just said now is pretty much all of my knowledge on what it does in biology. But from the
Hmm.
organic perspective, it's B12 was actually the subject of a lot of total synthesis efforts in the past. So chemists in the lab have tried to make vitamin B12 synthetically, and it took about, I think it was like 10 to 15 years, hundreds of PhD
Jesus
hundreds of
Christ.
PhD students and postdocs working on this at the same time across two different laboratories. It was the Eschenmoser lab and the Woodward lab. I think they made this in the quite a while ago now. It might have been the 60s, but don't quote me on that. Maybe 70s. Um, but the other cool thing about vitamin B12, I don't know if you know this, but it's chemically competent for catalyzing organic reactions. You can take vitamin B12 and subject it to, I don't know, you can use it for cross coupling a halide with an alkene. You can like do some cool photochemistry with it. It's photoactive. You can reduce it.
Yeah.
There's a lot of interesting things you can do with B12.
Yeah, the reaction stuff that you're talking about, the only reason I know about it was from looking at organic semiconductors because they used a
Mm.
porphyrin-based system for the same stuff. So that's one of the reasons I was like, oh, we should talk about organic semiconductors because B12 performs some of the same reactions, even though its main reaction mechanism is giving off that methyl group. But yeah, I know exactly what you're talking about, but I don't know the exact mechanisms by which this happened. Are you able to identify them or explain them?
Yeah, so like one of the common applications of B12 in synthesis is for dehalogenation. So say you have a carbon bromine bond, right? So for this, you do need an external reductant. So you start with a cobalt 3 complex, and then you want to get to a cobalt 1. So what happens is you have a reductant that reduces the cobalt 3 to cobalt 1. Then the cobalt 1 oxidatively adds into your carbon bromine bond that you're trying to get into. So now bromine is gone as bromide, and you have a cobalt 3 again, since you gave 2 electrons to the carbon atom to oxidize. And then you have a cobalt 3 bound to carbon. Then you can fragment. So, in the presence of light or a bit of heat or energy, you homolytically cleave and reduce to cobalt 2, and you get a carbon centered radical. Then that carbon centered radical can abstract hydrogen from whether it's solvent or you have an H atom transfer donor, and now you have a carbon hydrogen bond. So overall, we turned carbon bromine into carbon hydrogen, and then to turn over, you reduce your cobalt 2 back down to cobalt 1.
Fascinating stuff. Just for a little background, because I don't recall exactly, why is it difficult to donate the bromine and abstract the hydrogen in the first place without the metal catalyst?
Right. So you have to have some way of oxidizing that position, right? Because you're turning it from carbon, or sorry, reducing that position. Because a carbon-bromine bond is polarized positive at bromine, negative at
Hmm.
carbon. You want to turn that into negative at carbon, positive hydrogen. So you need some sort of way of introducing electrons into that position, whether it be through
Gotcha.
abstracting the bromine as a radical to leave a carbon radical, or just giving 2 electrons in to kick out bromine and then protonating it. So the harsh ways of doing this are with like stoichiometric magnesium, like magnesium 0 or zinc 0 directly. That'll just make the, like the Grignard essentially, and then you just protonate it. But that's pretty harsh. You might have other functional groups in the molecule that aren't going to tolerate a Grignard. Kind of the other way of doing it is through radical dehalogenation. So this can use like tin chemistry, or but still you're going to have to use some sort of stoichiometric H atom transfer reagent, some sort of
Gotcha.
stoichiometric bromine atom abstracting thing. Um, Whereas if you do it with a catalytic metal in this case, it's a lot more functional group tolerant, and it becomes catalytic.
Very interesting. When it comes to the cobalt in the center of, if I'm not mistaken, I hope I'm not, but the porphyrin-based system, the cobalt is equatorial with the porphyrin, right? So they're
Yep,
all in the same
they're
plane,
on the same
and so
plane, and then you have some sort of other neutral L-type ligand, kind of held beneath
becomes
it,
a
and then you have that
yeah.
one spot for binding the substrate, usually a methyl group or some type
Hmm.
of alkyl group above it.
What d orbital would that be that caused the reaction then? The dz squared?
So in terms of saying what orbital causes the reaction, the orbitals all kind of, right, the way we think about orbitals in isolated metals is different from the way we think about them when it's in the complex. Because when it's in the complex, you no longer have isolated atomic orbitals, you now have molecular orbitals. So
Mm-hmm.
in kind of organometallic mechanisms and uh, new method studies, people rarely ever say what orbital it is, and they rarely ever draw precise mechanisms, since with that level of complexity, you no longer have atomic orbitals. You don't know exactly where the electrons are in terms of
Yeah.
localization between the metal and the ligands and the substrate and everything else. So it's kind of assumed that the atomic orbitals of the metal mixed with the atomic orbitals of the
Hmm.
ligand now have some sort of molecular orbitals that are binding together. The
Right.
electrons are somewhere in there and they're doing their thing.
Good point reminded me on that. I do remember now. The reason I thought about the dz squared, I was like, okay, you have 4 nitrogen atoms donating. I'm sure it has to be like the dxz orbital, and so it leaves the dz squared. But I completely forgot. Soon as they bond, the energetics of HOMO and LUMO change altogether, and so you have this mixture. That's what the crazy models of molecular orbitals for complexes with like an energy chain are showing. And simple things that I forgot. Thanks for reminding me on that.
Oh yeah, no problem, dude. That was a good question. I think a lot of people ask that question, like, oh, because especially in organic chemistry, right? It's pretty. The models we use to understand that in terms of like, oh, this is a sp3 orbital, this is a sp2 orbital, this
Hmm.
is going into this sigma or this sigma star, this pi star. That's pretty like clear cut and easy to visualize in terms of just drawing it on paper. Whereas for organometallics, it's not so simple. Bonding is a lot more complex, and it's a lot harder to kind of specifically say exactly what it is. Until you do some computations to say, oh yeah, this is the EG3 and the all those different symmetry
Yeah,
labels that you can
God.
put on there.
I despise those, man. Those messed me up when I first started learning them. A1, G1. I was like, what is
Oh yeah,
this?
yeah. I think this has
Awesome.
been
So how can we
a good section.
summarize?
You want to
Yeah,
do a
yeah,
summary first and then jump into more examples? I have like 2 more examples. I think I
exactly.
can. So
Sure,
okay, I guess
let's do the
I'll do the 2 examples first then.
go for it.
All right. So the other example I thought of, although again, it's kind of not strictly organometallic since there's no carbon metal bond, but it's pretty obvious. The cytochrome P450 reactivity.
Mm,
So this is an iron complex, and essentially what it does is it's in the liver. It's involved in detoxification, um, that type of thing. So although there's no metal carbon bond here, the reactivity that the cytochrome P450 enzyme undergoes is very organometallic reminiscent, and it's actually inspired quite a bit of organic chemistry. So essentially what happens here is you start with an iron 3 complex, which then gets reduced down to iron 2 by just different organic reductants, whether it's NADH or whatever it may be. Then iron 2 combines with triplet oxygen to give you iron 3 and a peroxy radical. This then gets reduced again to get a peroxyl anion bound to iron 3. This gets protonated a couple times, and you end up losing water and making an iron 5 oxo compound, which can also be represented as an iron 4 oxy radical. And this is now kind of the prototypical example of the oxidant, the powerful oxidant that cytochrome P450 is. This can do a lot of different chemistry. You can abstract CH bonds to like result in the oxidation of alcohols to aldehydes to acids. It can turn a CH bond on an unfunctionalized substrate. Like you could just turn like, I don't know, like it could probably just turn pentane into like pentanone if it wanted to.
Yeah. Yeah.
Very powerful oxidant. It can demethylate ethers and amines, right? If you have like an anisole, like a phenyl OMe, it can demethylate that and make phenyl OH. And the purpose of all this is to make compounds you consume more water soluble so that you can excrete them. And our understanding of this took years of research, but it's also inspired a lot of organic chemistry. There's quite a few like iron-based and manganese-based catalysts that use very similar chemistry to what cytochrome P450 does to do selective CH oxidations and like abstraction of H dot from CH bonds to hydroxylate them. Things like the white Chen catalyst is pretty like widespread in synthesis.
Interesting. You said H dot in specific, like a single hydride radical?
Yeah, you can abstract the hydride radical. It's essentially the main thing that initiates these types of reactions.
Fascinating stuff. I don't think I've ever seen that before. With regards to the oxidation state, it reaches oxidation 5, you mentioned, right? For iron?
Yes.
Really interesting too. And one thing I noticed about this was I think Dean St. Mart, he's a synthetic chemist too. He pointed out to me how because of the oxidation state of the metal, hopefully I'm not putting words in his mouth, but he said that that's why some of the most stable compounds can still be undergo reactions that otherwise wouldn't happen, such as a stable benzene group in estrogen. And then that allows a detoxification of some of these reactive, rather unreactive groups in hormones, for example. Like the only thing I can think of is estrogen, because the benzene ring on the first carbon ring system is very stable. It's unlikely to react, but thanks to the reactivity of the iron, that allows something like that to happen.
Yeah, exactly. So like the cytochrome P450 iron, you can either draw it as like an iron 5 bound to like a double bond oxygen, or an iron 4 bound to a O radical. It's one of the most powerful oxidants, and it would pretty much react with anything you give it. The only reason it's selective is because of the steric environment created by the enzyme that's very substrate specific. So it's so reactive it can oxidize benzene rings to epoxides. So that's just one example.
Fascinating stuff. With this epoxide metabolism, what is it about epoxides that make them so highly reactive towards nucleic acids in specific? Because this is something I see all the time for 4-hydroxy estrogen, I think is one of the metabolites by CYP enzyme. Don't remember the exact one. And that hydroxyl group isn't the reactive form, rather it's the epoxide one before it gets hydroxylated. And then that becomes a DNA adduct group. So it's very reactive to it. But what is it about the epoxide in specific that makes it so reactive, since it's more nucleophilic, right?
Yeah, or electrophilic. So we're hitting on a good health related topic here. So I think I'll take it back. So where do these compounds come from? So it's pretty well known that smoking releases these polycyclic aromatic hydrocarbons, or a bunch of benzene rings stuck together, and that our own metabolism then breaks that down, and cytochrome P450 is going to make an epoxide out of that, and then the epoxide is very electrophilic. You have a really strained ring, right? You have these sp3 orbitals that are just crammed into like 60-degree bond angles between the carbon and the oxygen, and oxygen is the bond is polarized towards oxygen, so you have an electrophilic carbon, which can then be attacked by anything nucleophilic. We use this reaction it's pretty widespread in like sugar chemistry if you're trying to make a molecule in the lab. But in terms of what happens in a biological system, that epoxide can either then be hydrolyzed down to a diol, so you can have hydroxide add in, So you get, two alcohols beside each other from the epoxide. And that's actually the productive metabolic pathway. Is you take this benzene ring, you make the epoxide out of it with cytochrome P450, then you use a hydrolase enzyme to get the diol, and now the diol is super water soluble. It'll be excreted in urine. The other thing is you can just remove another proton from it and restore aromaticity and make a phenol. I think that's what you were alluding to earlier with the estrogen, right?
Estrogen, yeah. Hmm.
So that's another pathway, and it's pretty well known that those epoxides, before getting deprotonated or hydrolyzed to the metabolites that are non-toxic and excretable, those epoxides can be intercepted by DNA. Right? DNA is pretty nucleophilic. The nitrogenous bases are electron rich. I think we mentioned this before. Nitrogen 7 on guanine, especially. Electron rich, pretty good nucleophile. It can add into that sigma star antibonding orbital of the carbon oxygen bond on the epoxide, break open the strained ring system. It's entropically and enthalpically favored because you're giving some more freedom and you're breaking a kind of strained bond and releasing that ring strain to then get these DNA adducts, which can result in a bunch of different downstream consequences like disease.
Very good explanation. I love that. So naturally, when the body makes these epoxides, that's why the hydrogenation reaction has to happen simultaneously after, or close enough to be simultaneous. It's like as soon as the epoxides are made, the diols get made immediately so that it's flushed out in urine. And if that doesn't happen, that becomes an issue
Yep.
in the
And
body.
one interesting thing actually on that topic that I learned in a course was that, those compounds like the polycyclic aromatic hydrocarbons are well known to result from smoking. You're burning organic material, they're gonna make these aromatic rings, you're gonna inhale them. So if you have too much of those, obviously you're gonna get too many epoxides, your body won't be able to handle them. But the same compounds are actually made from cooking. When you cook food, you get a bunch of different reactions. What most well known is the Maillard reaction or
Hmm.
Maillard reaction, which is like you form bonds between sugars and amino acids. Enhances the taste, changes the food, but lipids in food, when you cook them, they also form. They go through a similar process to make these polycyclic aromatic hydrocarbons. So if you're eating like a burnt piece of meat, that's essentially what you're consuming. And for some reason, I don't think it's that well understood. Eating fruit along with cooked food or cooked meat accelerates the rate of your hydrolase enzymes. So even if there is some amount of burnt food or burnt lipids that are making those polycyclic aromatic hydrocarbons that are then going to give you too many epoxides that you usually wouldn't be able to handle, that might lead to DNA damage. Consuming fruit along with it for some reason accelerates your hydrolase enzymes and allows that to be productively turned over into a water soluble unreactive species that can be excreted.
Fascinating. Do you have any theoretical framework for why do you think that might be? Because one thing I can think of is potentially the flavonoids, since they're rich in phenols, and that might have something to do with water solubility or in general electronegativity. What do you think?
Yeah, I'd say it's got to be some sort of secondary metabolites, some sort of those complex molecules in fruit that are then interacting with the enzymes that are involved in that hydrolysis process. It's not something we were taught, and it's not something I've looked into. But now that we've talked about it, it's definitely something we
Hmm.
should look into. But to me,
I
at least,
agree.
it seems kind of like common sense. Why not eat your fruit and your meat and your cooked food at the same time?
Right. Awesome, man. Let's sum this portion up. Organometallic chemistry. What is it? Why is it important?
Yeah, for sure. So organometallic chemistry is the field involving the interactions between metals and compounds containing carbon. It's incredibly diverse. You can do a lot of different reactions. You can create a lot of different molecules, and you can create those molecules to help you make other molecules more efficiently. Furthermore, you can use these complexes to affect systems in biology, and there's systems in biology that already do this stuff without us looking at it. So we can use it to influence biology, or we can learn things from biology and use it to influence how we do chemistry in the lab.
Awesome stuff. Do you want to take a break right now, or are you still good? How are you feeling?
Um,
We could take a break
let's
anytime, man.
let's see. I'm looking at like what sections we've got next and thinking whether it makes sense
Yeah,
to
modern
continue straight, because the next is pretty related
chemistry.
to I guess we kind of covered this in terms of like
Mm-hmm.
CH activation, photoredox
Yep.
catalysis, electrochemistry. I
Yeah.
feel like we could skip some of this.
Sure. Do you want to go to total synthesis?
Um, yes. So
Like data-driven
let's go
synthesis?
straight. Yeah, let's go straight to total synthesis, and then we'll come back to some of the. I've added some stuff about electroaffinity labeling and
Yeah,
affinity
see that.
labeling. So I think we'll return to that after click chemistry, since it's pretty relevant
Right.
to that as well.
Sounds good. You want to take a quick pee break? Anything?
I'm good. Are you good?
Yeah, I'm going to take a quick break.
All right, all
Give me
right. I guess we take a
I'll
break.
be right back.
Oh, sir, I have returned.
Hey, awesome.
Can you see and hear me?
Yeah, I can hear and see you just
All right.
fine. Man, this
Sweet.
convo's going great, dude. We went through quite a lot already.
Yeah, man. I figured if I don't go now, I'll go later, and then you'll have to wait anyways. So.
Sounds good. Glad we both went. We're ready.
Yes, sir.
All right, bro. So let's talk about total synthesis. What is total synthesis then? Since you already mentioned organometallic, you already mentioned organic chemistry. What's the full purpose of total synthesis and some of the historical perspectives around it?
Yeah, for sure. So, in the broadest or most simple sense, natural product total synthesis is using organic chemistry in the lab to synthesize or create really complex molecules that are found in nature. So, let's say you find something in nature, it's a really complex molecule, it's interesting. Now you say, okay, how do I make this in the lab? How do I plan backwards and come up with a sequence of reactions that's going to make this from commonly available commercial reagents using chemical reactions? So, historically, total synthesis was kind of initiated out of the, I guess, like interest in medicinally relevant compounds. There were quite a few natural products isolated from nature that are used in medicine. Quite a few early drugs were natural products, since that was the only way we could really get anything. So, once those were discovered, there was kind of a push to access these synthetically in the lab to see if it would be cheaper, more sustainable. A lot of times, the natural products we isolate from nature are going to have different concentrations, right? If you just have a plant, it's not standardized. The leaf isn't going to have the same concentration as the next leaf. So you're going to get variable amounts out of it. And also the yields are going to be really low. If you have a big tree, you're going to have to chop down this entire tree to just get like a half milligram of stuff out of its bark. You might have to chop down an entire forest just to get enough, medicine to treat one person. So in that sense, total synthesis in the early days was kind of crucial to provide enough drug to treat people. Um, Furthermore, total synthesis is useful in the early stages of drug discovery. Let's say a certain natural product is found to have a certain biological activity, and people think that close derivatives or modifications to that structure might provide a drug. Then total synthesis allows us a way to develop a route to not only the natural product itself, but by tweaking little bits and pieces of the synthesis, we'll be able to change different parts of the molecule. The other thing it's been useful for is for confirming and revising the structure of these natural products. So there's a whole field of chemistry. I guess they're more analytical chemists, where their role is to isolate new compounds from nature and characterize them. But a lot of times these are really difficult analyses, right? They have to use a breadth of spectroscopic methods to determine the connectivity and the 3D geometry, the stereochemistry of these compounds. And a lot of times they make mistakes. It's just inevitable. It's a very difficult task. And synthesizing these unnaturally in the lab gives us compounds to be able to compare. And if the spectra match, then the assignment's correct. If they're wrong, then a revision needs to be made. Other than that, the kind of motivation behind total synthesis is for the development of new chemistry. So over the past 100 years, total synthesis campaigns have led to discovery of just broad chemical reactivity modalities, and just have taught us many concepts that we never would have thought to look at unless we had been faced with those types of challenges in synthesis. And last but not least, I think total synthesis is a great way to train students to have a diverse understanding of what it's like to plan a synthesis, to carry it out, deal with challenges, be exposed to a lot of different reaction types, and to just improve their skills at problem solving.
Really good description. I appreciate that a lot. And in regards to total synthesis, I think one thing that I would love to mention that is often overlooked is a lot of pharmaceuticals are based on natural products in the first place. It's just that chemists may tweak. Maybe they'll add like an acetyl group, or I know I was looking at ivermectin the other day and how it's derived from avermectin, the product synthesized by bacteria. And the only difference that I spotted was there was a hydrogen abstraction in one of the ring systems out of the entire complex molecule.
Hmm.
That single change made it more tolerable as compared to like avermectin. There might be other changes that I'm missing, but that was the only noticeable change. And that's really what organic chemistry is useful for. It's like you're taking from nature, you're revising it to make it more safe, or you're trying to make it more effective. And at the same time, it allows a plethora of other compounds that are not normally found in nature to be made in the first place. And I seen a paper that was looking at chemistry as a whole, and the field of chemistry that was most widely regarded as the best field of chemistry was total synthesis because of everything it provided. Not only medicine, but polymerization techniques that provide our clothes, for example, certain industrial applications and containers. What else? Teflon, even though it's a major issue nowadays, Teflon is still one of the most useful things for transporting highly reactive acids. Like without Teflon, most of synthesis with other really acidic compounds could not occur.
Yeah, for sure. Kind of I think the medicinal benefits of total synthesis have been most pronounced. The kind of most famous examples are Taxol. So, this was a cancer drug
Hmm.
discovered from the bark of the yew tree, and this was that example essentially where you would have needed to clear cut the entire like American Pacific Northwest forest to get enough for like a couple thousand patients for a couple years, whereas chemical synthesis made that unnecessary, provided compound pretty quickly. But on the other hand, Taxol being the incredibly complex molecule it is, the total synthesis is quite lengthy. There's only been I don't think there's been that many, and most of them are quite long. So, in terms of modern synthesis of Taxol, it's produced semi-synthetically. They've essentially like engineered bacteria, or I think it's
Hmm.
I don't think it's bacteria actually. It might be I don't remember exactly what type of microorganism it is, but you essentially engineer a microorganism to make a semi-synthetic like analog for you, so like something halfway there, and then you take that halfway there compound and you do chemistry on that to get it all the way. Um, so that's the Taxol story. The other main contributions of total synthesis have been in antibiotics. Things like vancomycin and derivatives thereof were huge. Another big one was spongistatin. This was from some marine algae, and it was kind of the most potent anti-tumor compound ever isolated ever, or like ever
Hmm.
made or ever isolated. And it was again one of those cases where you would have had to take like metric tons of this algae or this sponge to
Hmm.
get just like a milligram of this compound to test. So in that case, even if total synthesis takes 3-4 years to develop, and then you go through this long lengthy process of expensive chemical manipulations, you might be able to start with 10 grams and get like 20 milligrams out. That's still much better than destroying the environment because of one compound.
Yeah. Yeah, I was just gonna say in regard to that, I was like, so would people be able to eat the sea sponge and get the medicinal benefits? It's like, no, man, you'd have to eat 2,000 pounds of this sea sponge to get 1 milligrams worth, and that won't even have an effect.
Yeah, pretty much.
So now, in regards to current methods in total synthesis, one of the recent papers that you showed me and you presented on your stories was about AI-driven or data-driven synthesis, where it's like you feed the AI algorithm information on reactivity, how chemical reactions happen, and then it predicts to you how a certain reaction pathway might happen. And not only was that validated through experiments, but it showed you other mechanisms that weren't noticed before. Is that correct?
Yeah, so kind of in the modern era, I think the biggest sort of progress in total synthesis has been the application of AI and machine learning models and just computations in general, and also the implementation of new catalytic methods, right? So everything we talked about earlier from the organometallic section, and we were talking about new uses of metals in synthesis, all of that has made total synthesis a lot easier and has shortened routes exponentially. People have been using the metal catalyzed reactions that have been developed to make total synthesis easier. And in the process of pursuing natural products, they've developed new metal catalyzed reactions to get them there. And then those methods have become generalized for more applications to other general syntheses, whether it's pharmaceuticals or otherwise. And as a result of this, kind of funding and interest in total synthesis have been reduced in the past, I'd say 10 to 20 years. And also, I think that might be related to the advent of AI and the implementation of computational models to predict syntheses. So in the past, I think the idea of using computers to plan syntheses has been around for probably as long as computers have been around. And I think there's evidence back in the 60s and 70s of people trying to program things to plan the synthesis of complex molecules. As you can imagine, they weren't very good in the old days, and they were only really applicable to simple syntheses, maybe 3 or 4 steps, and they weren't even close to being able to plan complex natural products with all these different oxygenation patterns, stereo centers. But nowadays, with the increase in technology, as well as just AI, the amount of data available, as well as kind of like a human and machine interface, right? People have augmented the machine learning models by programming in the fundamental rules of reactivity that like a person would learn from reading a textbook into kind of the framework of these systems. Nowadays, these systems are quite effective. That paper you mentioned that I sent or I shared on my story essentially showed that an AI synthesis predictor or synthesis planner passes the Turing test. And what this means is that, let's say what they did is essentially they got the AI to develop 20 different syntheses for 20 different natural products. And then they looked at 20 different syntheses of 20 different natural products from recent literature. And then they sent those 40 to experts in the field. And they found that the experts couldn't tell the difference between the syntheses that were computer made and the syntheses that were planned by humans. And I think that's a pretty incredible milestone in the ability of computers to plan that far in advance and that many complex reactions that have different regioselectivity issues, different stereoselectivity issues. And again, we could say like, oh, computations, like sure, it says these 20 are going to work like this, but are they actually going to work like this? Well, out of those 23 were carried out and all the steps worked. Obviously, it took some human experimentation and messing with the conditions to get things to actually work in the real world. But at the end of the day, those 3 routes that were planned did end up working. And I think this is pretty revolutionary.
Very interesting that you mentioned that it passed the Turing test from an organic chemistry perspective, because I know the Turing test is based off of other parameters too. Like if it was a physics Turing test, it might be slightly different. It makes you think about where the definition really maintains a true definite statement, like a Turing test, the Turing test, where you know for a fact the machine has reached that level of competence. Does that make sense?
Yeah, I guess like the original test is essentially if you're talking to it, can you tell if it's a human or a machine? Right. And in this case, it's like,
right. In this case,
if you're looking at
yeah.
the output, if you look at the synthesis that it's planned, can you tell that it's a human or it was made by a human or made by a machine?
Right. And by that definition, it's already surpassed that, huh?
Yeah, it's already gotten there. So kind of the main criticism of like AI in the past was that it couldn't access complex molecules and that it wasn't very creative. But this shows that it can make bonds in a creative way and plan over multiple steps. I still think it's limited in that it can't take like very very rare or hard to come by literature examples and come up with a new idea for a new reaction or a new modality of activation that doesn't exist before and isn't well precedented. I think there's still a lot of opportunity for human creativity to shine above it in that regard. Like let's say if like the AI of 10 years from now was present in 2000, I don't think it would have still created the fields of like photoredox catalysis. I don't think it would have just had that idea to go and like make that. But who knows, maybe in 50 to 100 years, they'll be so good at like learning based on the outputs they themselves provide that they'll then be able to have that sort of like human-like creativity.
Right. Interesting. One thing that this brings up to me as well is the possibility of, well, before I even state this, a good way to think about what I'm going to say is, so at what you mentioned, like in early 2000s, the AI was nowhere near a level that, if they even had AI, that was sustainable and substantial enough to look at outcomes and synthesis. They weren't able to even come up with a possible 20-step synthesis for AI back then.
Mhm.
Whereas with inputs and improvement in technology, inputs from actual human minds, it's gotten to this point where it does pass the Turing test. My idea is, what if within 10 to 20 years down the road, the AI system gets so good at analyzing patterns and how synthesis happens that it notices things that might be missed by some of the best synthetic chemists in the world, much like what has occurred in biology, where they're using AI models to determine, for example, differences in MRI scans between people to see how quick they could determine things like cancer, for example, developing. And what has happened was that the AI system used for biology and medicine has actually noticed that through scans done in MRI, CT scans, they can see differences in racial body types, even though experts that are analyzing these scans have not been able to determine to this day. So it's like the AI got so good, it's even noticed patterns that weren't able to be analyzed before by some of the best minds and eyes in the field. I wonder if something like that might happen with chemistry, where it notices patterns that and new reaction mechanisms and laws of chemistry that we don't see yet.
Yeah, I think that's definitely possible somewhere down the line, and I don't think that's a bad thing at all. I think the kind of interaction between man and machine is inevitable, and I think it's even happening today, like not quite in
Hmm.
terms of new reaction mechanisms and new modalities of activating bonds, but in terms of synthesis, there's one example. I think I mentioned this to you, but Professor came and gave a talk here. He's from I think it was the University of Michigan. His name is Tim Cernak, and he presented a work where they were pursuing this total synthesis of an alkaloid called stamoamide. And I think the shortest synthesis of this compound in the past, which was planned by humans, was around 12 steps. And then they used AI to generate something like 100 routes. And then they looked at them and looked at which were the most promising. And they just selected one, kind of went with it. And they were able to synthesize it in 6 steps. So already that's, cutting the step count in half compared to the previous best human planned synthesis. But if you look at the individual steps of what the AI proposed, none of them were that crazy. They're all reactions that had pretty strong literature precedent. They've been known for quite a few years. It just happened to point out a specific disconnection and reaction cascade that a person looking at it has just never happened to see before. It's something a person could definitely see, but
Fascinating.
someone had just never seen it before. Now this is where it gets crazier, right? So that's 6 steps. Then what they did is they looked at the 6 steps and said, oh, 3 of them are productive. They're getting us bonds that we want. 3 of them are kind of just useless functional group interconversions that are setting us up to make productive, efficient bonds. Why can't we make an even shorter synthesis? So then they got the AI to generate 1,000 routes, and now they looked at all 1,000 of them manually, and instead of just blindly following one of them, they took bits and pieces from each and tried to come up with an idea to how they can take the suggestions from all the different possible routes and come up with the most efficient synthesis by combining their brain power and the computer power. And they ended up with a 3-step synthesis of this compound. And this one I thought was pretty insane. It's a very, very elegant and creative synthesis. It's I don't think a human alone could have seen this. Maybe someone could have seen it alone, but a computer alone couldn't do it. A human alone couldn't do it. Together, they could do it. So I think that's kind of the direction the field is
Really
heading.
interesting. From 20 steps to 3 steps, right?
I think it was 12 or 9 to 12 down to 3.
9 to 12. How big of an improvement?
The one kind of caveat there is that 3 steps was supposed to be something like 5 or 6 again. However, the experiment won, and it did 2 or 3 steps in a single cascade. So things that the machine predicted would be separate steps ended up happening as a cascade in the same flask.
When it comes to laboratory costs and efficiency, how big of an improvement is that if something like that were to be applied to many different syntheses? Would that be substantially enough that the entire field of synthetic chemistry would change?
Yeah, I think that would change quite a bit. At first, there would be a bit of inequality between labs that can afford that type of computational resource and those which couldn't. But I think right away, or not right away, but over 10, 20 years or however long it takes to implement, the industries involved in organic synthesis, especially the pharmaceutical industry, would benefit quite a bit from that. If you want to develop a synthesis that's scalable on a process level and for it to be the shortest possible route, it's much cheaper to just run a few computations and then sit down and pick the best 5 and then try those, rather than spending like 2 years of work and manpower and reagents testing 10 to 20 different routes. So I think this relates back to what we talked about with computations before. As long as it's cheaper and quicker to scope out a broad range computationally and then narrow it down to the specific number of small experiments you want to run, then it's going to be beneficial and save you money at the end of the day.
Gotcha. You cut off for a second, but I
Yeah.
heard. Understood.
So the same thing goes for whether it's synthesis or development of methodologies, right? Nowadays, AI has also been used to predict conditions or ligands or metals or base additives that are going to work for a specific new transformation. And again, if you can cut the experiments from 100 to 20, and then, or let's say from 5,000 to 2,000, and then have the robot set up the 2,000 in like, high throughput screening wells, and then you take the best 20 and do them yourself by hand, that's going to be a lot faster than kind of shooting in the dark or trying to pick the perfect conditions.
Awesome. Thanks for explaining all of that, brother. That was incredible. And I'm actually really excited to see where this goes.
Yeah, man, no problem. Thank you for bringing up this topic and letting me explain it.
Yeah.
We want to simplify for people before we move on.
Yes, let's do that.
I'll let you take a shot at this one.
You want to take the
it.
lead?
You
Okay,
got
sure.
it.
I'll take a shot.
Yeah,
Sure.
yeah.
So, what AI-driven? First of all, total synthesis is the field of chemistry involved with making natural products and making them better if possible, and through efficient synthetic routes. So you're always looking to make things as efficiently as possible. You don't want it to be like 100 steps. The less the steps, the better. So things like AI come into the picture, where they're not only able to predict synthesis routes, but they can predict better routes, why it should happen this way, and help with outcomes in experiments, not only to reduce costs, but to improve yields, which is a big one, because not all synthesis provides a good enough yield of the final product that you want. And so far, AI-driven synthesis has been so good that it's passed what's called the Turing test, where things from a machine would be indistinguishable from things emanated from a normal human being. And that is suggesting that the field of organic chemistry, with the use of AI and then the experimentee, might produce substantial results that might expedite the field even further than it already at the position that it already is. And one thing I think was important to mention is a lot of discussions have been presented in the past about how total synthesis as a field of chemistry has been dead since the 80s. I think with this, it's going to be revived, and not only revived, but expanded upon so much further than we could possibly have thought about.
Yeah, I agree there. I think the revival from AI-driven synthesis is pretty exciting, and like as you said, now we have modern methodologies for forming bonds catalytically with all these organometallic catalysts. We have AI to help us with planning and making disconnections to well-known chemistry. We have creative people still coming up with new reaction modalities, and all of these are going to combine to push the field of total synthesis into a new level.
Awesome. Here we go. We're moving on to click chemistry. And this is only something I found out about last semester. What is click chemistry? Why is it important? How does it work? And why was it awarded a Nobel Prize back in 2022?
Yeah, so click chemistry, as you mentioned, was given the Nobel Prize last year, the most recent one in chemistry. It was given to Carolyn Bertozzi, Sharpless, Barry Sharpless, and the other guy's name was Meldal. So essentially, click chemistry, the most important application of it, or the one that's found the most impact recently, is in biology. So you're essentially using chemical tools to affect biological systems and make them easier to study. So I'll go back to like what defines a click reaction. So a click reaction is something that clicks. It's got to be fast. It's got to be selective. You want thing A to react with thing B and nothing else. And it has to be high yielding. You want almost all of your A and almost all of your B to react together, and for there to be no A or B left in solution. You want all of them to consume each other. You want it to be fast and selective, so only they react with each other and nothing else. Now, the important kind of field within click chemistry is bioorthogonal click chemistry, which is the type of click chemistry that is compatible with biological systems. If you think about how things work in biology, our metabolisms carry out a vast array of different chemical reactions to convert the simple biomolecules that we need into other biomolecules, to move energy, to synthesize new compounds and cells and all that good stuff. And if our click chemistry gets messed up by the biology, then it's not going to work in cells. You're not going to be able to do anything if the reactions that are already happening in your cells just destroy your click chemistry reagents. On the other hand, if your click chemistry reagents mess up the biology stuff, you're just going to kill the cells or kill the organism. So that's not good either. So that's why the word is bioorthogonal. So it has to be like perfectly perpendicular. It can't have any overlap. It has to be something completely different. It's not going to mess with the biology, and the biology is not going to mess with it. So the reason people wanted to develop this is to get more information on what's going on with biomolecules at the cellular level. There's only so much information you can get from like microscopy or like doing tandem mass spec or like any sort of biochemical study without first labeling something. If you label something, then you're going to be able to isolate it and see where it is, what it's doing, how highly it's expressed in different cell types, different organelles, between like, disease cells and healthy cells. So if you can find a way to label something, and by labeling, I mean using like a click reaction to attach something to a biomolecule. So let's say this is your biomolecule, and you put something click sensitive onto it, and you have something else click sensitive. You click them together, and now all of a sudden, every single molecule of this protein is going to glow fluorescent green, and you're going to be able to see where that is. That's going to help you figure out if this protein is overexpressed in disease or if it's expressed less or more at different parts of development. So that's kind of the rationale behind this. Now, there's a lot of challenges, right? The cellular environment is pretty weird. It's pretty dense. It's aqueous, so you can't have anything very reactive that isn't going to be stable in water. You can't have anything that's going to be consumed by like the nucleophiles in your cells, the thiols and amines that we mentioned earlier on your proteins. Cytosols are pretty reducing, so you can't have anything that redox active. And the probe that you're putting in there has to be like stable to all the enzymes, right? If you think of like enzymes that cleave peptide bonds or ester bonds, all those different things, they're going to just chop your probe up if it's not stable. And lastly, you want to avoid metals since a lot of those are toxic. And the other challenge, which is important, and I want to return to this later, is that in order to click something like fluorescent or something heavy to label a biomolecule, you have to have a site on the biomolecule to click onto, right? It's very, very difficult to just selectively throw something into the cell and have it go to a biomolecule. So you're going to have to find a way to incorporate something, like one piece of your click chemistry onto that biomolecule. So you can see there's a lot of challenges here, and the kind of bringing this to fruition was a major achievement, I think, and that's why it was awarded the Nobel Prize. So the way they figured this out, or maybe you want to stop me and ask a question. I can't.
No, I'm hearing you just fine. Got everything. I wanted to make sure you're able to see me as well, and you can hear me in real time because it does cut off a couple of times, but I got everything so far.
Yeah, perfect. I thought I heard you breathe, and you were about to say something, so just wanted to make sure.
No, it's good. All good.
All
Keep
right,
going.
sweet.
I'm listening,
Yeah.
and I think you're explaining this really well, especially for some if somebody didn't know click chemistry. I think the explanation is really good and why it's important. Keep going.
Yeah, so then essentially the way they started this is by identifying one functional group that they thought was completely bioorthogonal, so it's not going to do anything, and then there's known chemistry with that functional group that's fast. So they started with the azide, like N3, and they said, okay, this is small, this is bioorthogonal, there's no azides in biology to our knowledge, or not many, and it's not going to do anything in the cell. So they had to think of a reaction to do with the azide. The first they thought of was a Staudinger ligation, which is the reaction with a phosphine to form a bond, related to the Staudinger reduction. But the issue with this is that it's pretty slow. So they kind of discarded this. The other reaction known with azides is a cycloaddition with an alkyne. So an azide is 3 nitrogens, and then an alkyne is 2 carbons. So you attach those 3 nitrogens to the 2 carbons, and you get a 5-membered ring. So it's a 3 plus 2 cycloaddition. You're making a ring and you're adding 2 things together. So you get a 5-membered ring called a triazole because there's 3 nitrogens in it. This is a pretty bioorthogonal reaction. There are cycloadditions in biology, but they're pretty rare. There's one I can think of, I think. There's a
Thymine,
couple.
thymine dimers.
Yeah, there's that, and there's I think there's a couple natural products that have cycloadditions in their biosyntheses. There's pericyclics in vitamin D synthesis for sure.
Oh, but yeah, vitamin D sigmatropic rearrangements.
Yeah,
from
it's not quite a
cycloadditions.
cycloaddition, but close. It's in the same family. But anyways, people are
Yeah.
pretty confident that the cycloaddition between an alkyne and an azide would happen selectively between those two and not with any of the other molecules or functional groups in the biological system. The issue with this is that the reaction is slow and requires heat again. So this is where kind of the chemistry of Sharpless and Meldal came in. They found that if you just treat with a copper catalyst, you can have the cycloaddition go at room temperature. Then Bertozzi's group came in, and then they started to realize, well, copper in biological systems is still pretty toxic. You don't have too much copper in there. So they started to shift gears and find a way to do this without adding copper. And this is where the kind of physical organic chemistry perspective comes in. So they were like, okay, how do we accelerate this without heating it? Because, biology is 37 and it's dilute, and without a copper catalyst, so no metals, without adding something else, you just want to have the alkyne and the azide. Well, the only way you can kind of do it is by changing the structure of the starting materials to make them more unstable and more reactive. And the way they rationalize this is that the alkyne has sp orbitals that are 180 degrees apart, and at the transition state, you're bending the alkyne from 180 to 120 because you're making it an alkene. So if you can do what enzymes do, which is induce strain in the starting material, so you destabilize the starting material, but then relieve that strain in the transition state so that you're destabilizing starting material, stabilizing transition state, you reduce the activation energy. So what they did is they made a strained alkyne by putting it in a ring. So they made cyclooctane, so octagon with a triple bond in it, pretty strained. The bond angle is now closer to the transition state, so the reaction is a lot faster. They did quite a bit of, just reactivity studies on this, with adding electron donating groups, electron withdrawing groups, and they found that electron withdrawing groups made the reaction faster, since the alkyne uses its LUMO, or lowest unoccupied molecular orbital. So if you withdraw electrons, that LUMO is going to come down and make it more reactive. And the other thing they did is they added a bunch of different hydroxyl groups and whatever to make this more water soluble, because you can imagine an octagon of carbon is pretty greasy, pretty hydrophobic, so it's not going to be soluble in water, and you need it to be soluble in water because it has to go in cells. So they put a bunch of these functional groups on it to make it water soluble. Then, so once you're set on the reaction, okay, we're going to do a cycloaddition between this cyclooctane and an azide. What you then have to do is make molecules that have cyclooctanes and azides with handles to attach biomolecules to. And the most convenient is a carboxylic acid, because you can do an amide coupling. Make an amide bond, and then it's attached to something that's going to go in biology. So now we get to the last challenge, which is finding a way to attach one of them to a biomolecule selectively. So if you just put an alkyne or a cyclooctane thing and an azide thing in a cell and have them click, okay, now you just click two things together. One of them has to be attached to a biomolecule. So what the Bertozzi group did is they were interested in studying like cell surface peptidoglycans. Specifically, I think it was sialic acid or something like that. So what they did is they grew cell cultures that were enriched in sugars labeled with azides. So they just fed the cells azido sugars that already have an N3 group on there. So then all these get incorporated into the cell surface peptidoglycans that they were interested in studying for different cancer models or what have you. Then, once the organism does all its metabolism and synthesis of these biomolecules, you get these sugars labeled with azides on the surface. Then all you need to do is throw in your cyclooctane that has some sort of reporter molecule. This can be a fluorophore, so some type of organic molecule that absorbs light and is going to make it colored when it labels it, or something like biotin, which has a measurable mass, and then you can do like mass spectrometry to measure how many or where or what got labeled. And that's essentially what click chemistry is. So pre-install that functional group, you hit it with something that has a reporter on it, they click together, you get labeling, and you can use this tool to study disease, study different biomolecules. You can throw in like azido amino acids to get incorporated into a specific protein or what have you. and then put in the other click component and study what's going on.
Oh, there we go. I think you're back. You cut off for a second. Can you see me?
Oh, how long was the second?
Oh, you're no matter what happens, the recording will happen anyways because it's getting from both sides. So when I have the
Okay,
finalized video,
perfect.
everything will be the same.
Yeah. What did you
But
hear last?
what I heard is like, I think you mentioned. Let's see. I got pieces of the reporter tag, and then from there cut off.
Oh, okay. So I'll just go through it quickly again, just for you as well.
But it's okay. I read the paper that you sent me with the click chemistry where they're using
okay,
the
perfect.
cyclooctane group and
Yep.
then the cyclo additions. I know exactly what you're talking about. Awesome. So yeah, don't worry about it. I got it, and it's more for the
Sweet.
people anyways. But isn't it fascinating when you think about it? It's like a simple thing with click chemistry became this beautiful complex system that you can now use for biology, fluorescent chemistry, bioorthogonal chemistry without copper, so it's no longer toxic. It's like everything about chemistry inevitably becomes very interdisciplinary because it's part of everything anyways, part of the living
Yeah.
world we're part in.
Yeah, exactly. So I think this is a great example of like the full story from beginning to end, where you start with a very like pure chemistry, physical organic chemistry principles of how can we induce strain, how can we reduce this activation energy, how can we make this LUMO lower, how can we increase the rate of this, and then once you have that, it's quick succession, get it in the cells, label things, and then use it right away to start learning things about disease.
Yeah. Now, like the beginning of the physical organic chemistry part, where it's like the strain is the determining factor here in reactivity, which is awesome
Yeah.
to think about.
Yeah, for sure.
Cool. So that's click chemistry, and it ties back into a lot of the different things that you talked about before. Is there anything you want to tie it into in specific, like the electrochemistry, electroaffinity labeling, or anything like that, before we move on to the next one?
Yeah, for sure. So, kind of the more modern approach to doing something similar has been photo affinity labeling and electroaffinity labeling, which has been enabled by the new developments in those fields in terms of catalysis. So that limitation that I mentioned with click chemistry is that you have to have one of the components pre-installed on the biomolecule, right? With photo affinity labeling and electroaffinity labeling, that's not a requirement. And that's why these have become so widespread for the determination of what the target of a drug is, right? So let's say you discover a compound that, you know, inhibits the growth of cancer cells, and you put it in cells. And it's not good enough to be a drug yet, but you want to investigate it more. You want to optimize it, add methyl groups somewhere, add chlorine somewhere, whatever you want to do your structure activity studies. But you have no idea what enzyme this compound is targeting. And you have no way of figuring that out because you're just throwing it in a cell and then you're seeing that it's inhibiting the cancer cell growth. And the way you have to do that is determine what target it's doing. And tools like photo affinity labeling have made that a lot easier. The way this works is you take the molecule that's having the activity, you link it to something that's redox active, so it's susceptible to reduction or oxidation or light or electricity, and it's going to get cleaved and form something reactive upon photoexcitation from a photocatalyst that's excited or from a gentle electric current, and then it's going to form a covalent bond to your biomolecule. So essentially, let's say you have this component of the drug right here, and then you have this like photo affinity or electroaffinity probe sticking off of it. What happens is the biomolecule floats over to the target. It reversibly binds there, right? Because the majority of compounds that are created as drugs or initially discovered to inhibit things are going to be reversible. It reversibly binds, but then it spends most of its time there. If you think about equilibriums of association dissociation, it's going to spend most of its time bound to the target. Then you expose it to either the the redox of the photocatalysis or electrochemistry. Then this reactive group does its chemistry. Usually it's a aziridine or some type of system like that. So like a three-membered ring with two nitrogens. Then you lose nitrogen gas and you form a carbene, which is incredibly reactive. But since it's sequestered within that biomolecule, all it does is insert itself into some type of carbon hydrogen or oxygen hydrogen or nitrogen hydrogen bond. And now you have this compound irreversibly bound to your target. Now, sorry. now that you have a covalent bond between your biomolecule or between your inhibitor and the biomolecule, you can use that handle that you introduced on the probe to add something fluorescent. So let's say you add something with, I don't know, an aldehyde or something on the part that has the reactive, photoactive, or electroactive thing. Then you can add like a fluorescent probe to go and bind that, and then now your target glows green or whatever. Or you can add a biotin and then just cleave the cell, subject it to mass spec, and then see exactly what got labeled. And that provides a really efficient way of labeling a biomolecule and determining the target of something without having to pre-install the functionality to do the click, and without even knowing what you're trying to find.
Fascinating stuff. And it would be an advancement basically to the fluorophore-based peptidic molecule that you use for transglutaminase study, right? So if you could do that during the in vivo state, essentially, without having the fluorescent tag in the beginning. Is that similar
Yeah, essentially.
to what you're describing here?
In our case, in my project, the reason my fluorescent probe works is because the inhibitor is irreversible, right? The inhibitor itself already forms a covalent bond with the target. So if you have the fluorophore already attached, then the molecule is going to make the covalent bond and the fluorophore is already going to be there. Whereas in the case of most compounds that are medicinally active or used in medicine, they're reversible inhibitors. So you can't necessarily do that, since once if you want to figure out what the target is, if you just take the molecule out of fluorophore, hope it binds to the enzymes, and then you want to cleave the cell and figure out what it was. The moment you cleave the cell, the concentrations are all going to change, and the enzymes are going to denature, everything's going to go wrong, and your molecule is going to dissociate, so it won't be stuck there. Now with this photoaffinity and electroaffinity labeling, you form a robust covalent bond, then you attach the fluorophore to that linker of the probe, and then you're good to do like mass spec and large data analysis there, or just do a blot and look at the fluorescence, whatever you might be interested in doing.
Really cool stuff. How do we summarize click chemistry overall then as a field of chemistry, why it's important?
Yeah, so click chemistry is a field of chemistry where you try to do fast and selective reactions between two components. And the reason this is important is because we can do this in biological systems. So we can label a biomolecule that we're interested in studying, whether it's for a disease or for studying its function. We can label it with another component, and then we can detect exactly where this biomolecule is, where it's expressed, where it's overexpressed, what it's doing, and this can give us information on its roles in the cell, whether it's involved in certain diseases. So click chemistry and bioorthogonal chemistry, photoaffinity labeling, electroaffinity labeling, these are all different tools that have been developed by chemists studying chemical reactions, from fundamental studies in reactivity in molecules to be able to influence biological systems and study how these different biomolecules work and what they do.
And if I'm not mistaken, with click chemistry, one of the main advantages is normal chemistry that could be toxic to cells and would not work most of the time is automatically able to not only work in the in vivo state where it's very sensitive to temperature changes and to aqueous environments, but at the same time, it makes otherwise hard to study enzymes a lot easier to study. And so you really understand how things work biologically a lot better with click chemistry. Is that
Yeah, for
correct?
sure. Yeah, I see that, since the more similar your system you're studying is to the real. Okay, I said a lot of words there. The more similar the system under study is to the real system, the more relevant the information you're going to get out of it. So if the click chemistry allows you to observe the phenomenon in its natural state without any further interference, you're going to get a bit better information out of it.
Awesome stuff. Here we go. We're moving on to homochirality, probably
Oh
the
boy.
most important topic, in my opinion, that we're going to get into.
Yeah, this is
So
going to
let's
be.
give a primer first. Homochirality. What does homochiral stand for? What is chirality? Before we even get into this.
Yeah, for sure. So chirality can be simplified as handedness or molecular asymmetry. So the definition of something that's chiral is that it's non-superimposable on its mirror image. So it's a little bit of a long definition, but essentially what it means is if you look at your right hand, this is my left hand, but if you look at your right hand, and you look at your left hand, these are mirror images of each other, and no matter what you do, you can't overlap them so that they're the exact same. You can go like this, but that's not the exact same. You can't lay them on top of each other and have them be equivalent. So I guess our hands are chiral. A right hand only fits into a right glove. There's a lot of different types of chirality. There's the most common one in chemistry is central chirality. So if you have a tetrahedron, which is the most common geometry of carbon, then you can have 4 different groups to that tetrahedron. And if you have 4 different groups, then the mirror images aren't going to be able to overlap. The other types of chirality are axial chirality and helical chirality. So if you have a helix like this, imagine like a corkscrew or a spring or something, and you take the mirror image of that, it's not going to be superimposable. Planar chirality is a bit harder to explain without thinking about molecules, but that's just another form. But essentially, that's what chirality is. Do you want to take over and comment?
When it comes to helical chirality,
Go ahead.
Go ahead.
I was just gonna say maybe you want to jump in.
I was gonna say when it comes to helical
Oh, I feel there's this.
We're cutting each other off.
Dude. There's a delay, so I can't when I start speaking. You've started speaking as well, but I don't hear you until like 2 seconds after.
Cutting off. Hold on, let's see. You cut off for a second. So I think I realized it's anytime either of us moves too much, the video cuts off for some reason.
Oh, no way.
But even though it's still recording, so everything's fine. But in case you hear this, I can't see you doing anything. Now I see you. I think you're still now. Yeah, it's low quality. How I see it is low quality, but the actual recording is higher quality, says it up here.
Okay, perfect.
So one of the questions Kian had asked me was if I wanted to expand upon the role of homochirality in relation to biology and life. And I figured, okay, let me do that. Homochirality, in essence, just means that the handedness of the molecule is different from another version that is opposite oriented in terms of its handedness. So you have left hand, right hand, for example, like Kian was explaining. And DNA, for example, one of the biomolecules that are made of nucleic acids, takes up this right-handed helical shape. So when you look at DNA inside of the human body, the helix rotates in a right-handed helicochiral fashion. It's not left-handed, it's only right-handed. And that is the form that codes for life. Interestingly, you can have left-handed form of DNA, not in biological systems, but outside of biological systems, you're able to manipulate it to make it the opposite chiral form or the mirror image. And this left-handed DNA can actually store data. It's the equivalent of a biological USB, where you can store a large amount of data just because this chiral molecule is, in essence, a system that takes in information and can hold that information in its hydrogen bond network. And when you need to pull it out, you just got to transcribe it.
Yeah, that was great. I had no idea about the information storage thing and how massive it was. That's pretty cool in terms of applications. But last thing I want to add before we jump into the homochirality is why does it matter? And it matters because the drugs we consume are often also chiral, and the targets they interact with are also chiral. And if you give the wrong enantiomer, which is the name we give to the isomer of a compound, that's the opposite mirror image to the correct one. So you have 2 enantiomers that are chiral mirror images of each other. If you give the wrong enantiomer, you're either going to do nothing or you're going to do the wrong thing. And the most catastrophic example, I think anyone who's studied any sort of biology or chemistry knows this, is the thalidomide example. This was a drug used as like a painkiller for like morning sickness for pregnant women, where the correct enantiomer did that desired thing, but then the incorrect enantiomer ended up being a teratogen, which resulted in birth defects. So it's quite, honestly, that's the craziest example I've ever seen. It's crazy to think about how much of a coincidence it is that the thing that was prescribed to women during pregnancy when they were experiencing morning sickness ended up being a teratogen and affecting the babies that they were carrying. It was really catastrophic, but that is why chirality matters. And as Pedro mentioned, we still don't know exactly why nature is homochiral and why that life is the way it is and not the opposite way.
And there's a lot of research being dedicated to this to understand how it came about and whether it was chance or it was some sort of actual driving force behind it.
Here, I had asked Kian, how do you think homochirality arose? And this leads up to a concept in biological physics where the weak force or the weak interaction that's part of physics, subatomic physics, dictates potentially the formation of chiral molecules simply because of the small energy change that occurs when, for example, there is beta decay.
Yeah, so there's a couple major theories for how homochirality arose, and there's a couple that are kind of more biomolecular. They're kind of more, some are more like life based, there's some that are more small molecule based, and then there's some that are entirely based in kind of like physics, and there's a couple that are, mostly physical chemistry and thermodynamic. But I'll start kind of from the top down in terms of the biological theories and then go down. So once we get to the middle portion, we'll see how it's related to synthesis and how a lot of the theories for the chemical bases or bases are common techniques that are used in organic synthesis. So we'll start with the biological theory, and this is just that life just happened to develop on a certain chirality template, and due to selective pressure, or that just happened to accelerate and develop faster than life that was the other way. And then now life is the way it is because that's just what happened. It was the molecules themselves, the proteins, the amino acids, the um, basic building sugars weren't very chirally enriched, but then life just developed on one chirality template. And then as it grew and multiplied and cell division and all that stuff happened, all the cells started having the same chirality. So that's kind of the most top down kind of biology theory. Do you have any thoughts on that before we go to the next one?
In this portion of the interview, Kian had asked me from a biological perspective, what do I think about the developments or how it came about that homochirality became a thing biologically? And I tend to approach it more from a physics perspective. And from the physics perspective, there is in terms of the weak nuclear force, which is connected to the electromagnetic force, out of the four fundamental forces of physics, these two are basically one unified force at higher energies. It's possible that when things first started, this interaction, electroweak interaction, because it violates parity, allowed for one enantiomerically type of molecule to take hold over another that allowed life to develop the way that we know it. Once again, the right-handed form of DNA versus the left-handed form of DNA. Possibly, and researchers look at this, the spin of the electron being the same, and this having an effect on energetics of how molecules develop after weak interaction occurs with what I had mentioned with beta decay, for example. It's possible that it led to one enantiomer of different biomolecules being produced over the other.
Yeah, so on that note, I guess we'll go from the biology approach down to the physics approach and come back up. But that paper that you sent, I had no idea. So essentially what we're talking about here is out of the four fundamental forces, right? The strong force, the weak force, the gravitational force, and the electromagnetic force. The weak force is the only one that violates parity. What that means is if you take any molecule, atom, system, whatever, and you invert it completely. So you take the center, the exact middle of it, and you invert every point through it. So going from coordinates xyz to negative xyz, the weak force actually changes. And what this implies is that enantiomers at the molecular level and everything bigger than that as well will have different energies. And this has actually been computationally supported for the first time ever. It's been shown recently that enantiomers of molecules do have slightly different enthalpic stabilities. The energy difference is quite tiny. If you convert, the Gibbs free energy difference to an equilibrium constant, it turns out that at equilibrium, you're going to have an excess of one enantiomer by like 1 in 10 to the 17. So every 10 to the 17 molecules, you're going to have like one in excess to the other, which is pretty small. But the implication of this is that it supports kind of I guess the random like initial excess of one enantiomer. So let's say like initially, and the other important thing here is that based on computations, they found that the L amino acids
and the D sugar building blocks are actually the more stable ones. So if this is, you know, true, this would mean that if life were to develop in a billion different universes or a billion different planets, more often than not, it would end up being the L amino acid and D sugars that end up being the ones that support life. So this implies that there's some directionality or some sort of predisposed template. But again, the difference is only tiny, and in terms of the outcomes on a molecular scale when you're doing chemistry in the lab, it would be quite minuscule. And this theory alone, I don't think, explains biological homochirality, unless you want to argue that, you know, that 1 in 10 to the 17 was enough for the life that was L and the life that was D amino acids to compete, and then the L1 by that one tiny difference. Unless you want to make that argument, there has to be some sort of amplification mechanism for making that small difference a bigger difference that then led to life afterwards. Yeah, I don't understand it that well either. I'm sure you have some physics friends that will be able to pitch in on this, but I believe it has to do with the spin of subatomic particles. It's not much else I could think of there. Yeah, I think the biggest applications of physics are in terms of like photophysics and the interactions of light with organic molecules, which has been essentially done to death. It was a field even before photoredox. But the other thing I learned from reading up on homochirality is that circularly polarized light, I mean, everyone knows that, or not everyone, but anyone who studied organic chemistry knows that plain polarized light is rotated differently by the enantiomers. So the interactions of light with the enantiomers is how you determine which is in excess, but also that circularly polarized light can consume or cause a reaction in one enantiomer more rapidly than the other. So rather than polarizing light in a plane, if you polarize it in a circular manner, you create like these electrical field vectors, which they themselves are chiral, and those can kind of serve to chirally induce the initiation of reactions differently at different rates, or the consumption of compounds differently at the molecular level. And this has actually been shown I think it was shown in the 90s actually. The applications aren't that broad. It's only been shown in a quite limited number of systems. But one thing I think you knew about this before, but one of the papers I added was the mechanistic study on the SOI reaction. This is something we'll get into a bit more, but organic chemists noted that if you take a pyrimidal aldehyde, so a pyrimidine that has an aldehyde coming off of it, and you react it with a alkyl zinc reagent, so this is just a nucleophilic carbon that's bound to zinc, you end up getting a mixture of products that isn't racemic. So usually if you do this type of reaction, you can add to the top or the bottom of the aldehyde, producing a new stereogenic center, a new chiral center. And if you have nothing chiral in the reaction, you should get 50% from the top, 50% from the bottom, and you should get an equal mixture of enantiomers by the end. But in some cases, people were noticing like pretty significant, like 20 to 30% excess of one enantiomer over the other. Then the weird part is that they noticed that if you add like 1% of product that's enantiomerically pure, so you have an EE of 1%, so you have like 49.5% one and then 50.5% of the other, you end up amplifying that through the course of the reaction. So you start with 1% EE. By the time the reaction's done, so essentially the observation they made is that, you know, when you run the reaction with a racemic starting material and no chiral additive, you end up with slightly enriched enantiomer in the product, maybe 20 to 30%. But if you add 1% of the product with, you know, the rest of the starting material, and that product is enantiomerically pure, or even 1% enantiomerically enriched, you then get amplification of that enrichment up to 80 to 90%. So your product ends up being more pure than the additive that you added in the beginning in terms of the enantiomer composition. And this is known in physical organic chemistry or catalysis as a nonlinear effect. And essentially, this implies that what's happening is you're getting aggregation of the catalyst and you're getting autocatalysis. So the product itself is enantiomerically pure. The product molecules are coming together to make a complex that can catalyze the formation of the product itself to be the same enantiomer of what it initially was itself. And this was pretty revolutionary. No one really understood this. Took like years of mechanistic studies through spectroscopy, isotope labeling, computations, kinetics to figure this out. But the other thing they noted, which is relevant to the physics, is that if you just start with so I mentioned if you start with racemic, you get like maybe 20 to 30% enrichment. If you put a bit of an additive, you get up to 80 to 90. If you shine circularly polarized light, that'll also have the same effect as adding an additive. It'll skew it to one direction, and it'll end up with a bigger excess than without light, and it'll be comparable to additive.
Freaking crazy to think about. And I like the term that you mentioned, chiral electromagnetic vectors, essentially, which is really interesting to think about.
Yeah.
And that's a autocatalysis, right?
Yeah. So I guess that would be like helical.
Gotcha.
That would be called autocatalysis, where the product either inhibits the formation of the opposite enantiomer, or it catalyzes the formation of the enantiomer itself.
Insane stuff. Cool. So, what does this have to do with synthesis in general? Is chirality easy to achieve when it comes to synthesis? Is it hard? Where does the connection between the origins of life and total synthesis come in terms of chirality, aside from autocatalysis and things like that?
Yeah, for sure. So what we've covered so far isn't that relevant to synthesis, because the examples of autocatalyzed reactions are pretty rare. I think the two concepts in synthesis, or the three concepts in synthesis that are most relevant to homochirality and the theories behind them, are dynamic kinetic resolutions, chiral resolutions with like crystallization, and lastly organocatalysis. So I'll first cover like the theories behind homochirality and then I'll come back to how they relate to these concepts that are used in synthesis. So the homochirality theories are essentially, there's like two fields of thought. One is that, amino acids became homochiral first and then influenced the synthesis of sugars. And the other one is that sugars became homochiral first and then they influenced the chiral synthesis of amino acids. So the sugar group, their argument is essentially that sugar building blocks, namely glyceraldehyde 3-phosphate, or even glyceraldehyde itself, which is a 3-carbon sugar, can racemize rapidly at room temperature under prebiotic conditions. So there's one stereocenter in the molecule, it's in the middle, and it can do keto-enol equilibrium, or I guess aldehyde enol equilibrium to make it the aldehyde and then the enolate, and that can protonate on different sides to rapidly interconvert the stereoisomers. However, there's been a lot of like physical chemistry computations and experiments that show that when you aggregate, or when you crystallize this compound and related sugars, the homochiral solid is more stable than than the racemic solid. What we mean by that is, I guess from a thermodynamic standpoint, homochirality is entropically disfavored since it's a more ordered system and there's less accessible microstates, less freedom, whereas having a racemic state is entropically favored. That means for homochirality to come about, you have to have some type of enthalpic driving force, right? And that's where the kind of crystal studies come in, where it's seen that if you have a solid that's made of all DG3P, glyceraldehyde 3-phosphate, the interactions between the molecules are stronger than if it's a mixture of DL. So what might have happened is, let's say the physics thing is true and DG3P is slightly more stable than LG3P, and the difference is only like 1 part per 10 to the 17. Then at the beginning, you have nucleation, or the formation of a small crystal, and there's going to be more small crystals with DG3P than LG3P. Then you're going to have rapid formation and crystal growth of the DG3Ps around that initial DG3P crystal, and that's going to grow more rapidly, whereas the L1s are going to grow more slowly. So now you have two different competing rates that consume different enantiomers. But as I mentioned with the racemization, the D and L can interconvert rapidly under aqueous conditions. So what's going to happen is the racemic one is unstable. It's going to dissociate, go back in solution, and gradually they're going to all equilibrate towards that D solid, right? Most of the D is going to be consumed to the D solid, the L is going to be left behind, and then that's going to rapidly racemize to a mixture of D and L. So you're going to consume 50%, then the remaining 50% is going to get converted to 25, 25. You're going to consume the other 25, and then 12 and a half, 12 and a half. So you see where I'm getting at. Essentially, over time, continuous cycles of racemization and co-crystallization in a chiral state, you're going to end up with enriched D-glyceraldehyde. And this is relevant to synthesis because this is actually called a dynamic kinetic resolution, where you're resolving the enantiomers by making use of rapid interconversion and then irreversible conversion of one of them. So if you have irreversible conversion of one of them, and then they're allowed to interconvert, you'll eventually funnel all of it to what you want. And the way we do this in synthesis is typically through enzymes. If you genetically engineer an enzyme to, let's say, oxidize, let's say you genetically engineer an enzyme to, I don't know, hydroxylate the R configuration of something and not the L configuration, but then the R and L interconvert, then you just treat a mixture of the racemic mixture with the enzyme, and then you'll end up with something like 99.9% pure product. So that's that application. And the other application that comes out of this is chiral kind of co-crystallization. And this is where the templating comes into play. So say you have a chiral mixture and you want to separate them, but you can't do a dynamic resolution. You'll just do a normal resolution where you treat it with another enantiomeric salt that's enantiomerically pure. So some people theorize that if you get the sugars pure, then those can co-crystallize with the amino acids and get those pure. So here, if you have a mixture of two compounds and you only want one of the enantiomers, you can treat it with an enantiomerically pure salt. It's going to bind to both of them, but the complexes that it forms aren't going to be enantiomers, because these two are enantiomers, but this one is enantiomerically pure. So when it binds to this one, it forms diastereomer A, let's say up, and it binds to this one, it forms diastereomer B, let's say it's up-down. And up versus up-down are not enantiomers anymore, they're diastereomers. They're going to have different solubilities, and then you can crystallize out one, leave the other in solution, or take the solid if that's what you want. But
Fascinating things.
That lets you purify them.
I'd seen the genetic engineering of enzymes to produce one enantiomerically pure product before, actually an orgo 1, and it completely escaped me because I presented on this, but I didn't know what this was at the time until you just talked about it now. But it was in regards to butylenic acid. It's almost like cholesterol, except it's a little bit longer. It has like a longer alkyl chain on top, and the same process where they genetically engineered yeast to produce an enzyme that would catalyze only one specific type of enantiomeric product, to produce one enantiomeric product. And I never even thought about how that relates to homochirality. It's totally escaped my mind until now. And then the second thing you're mentioning about crystallization, it makes me think that something in regards to the polymeric state, because we do consider DNA a polymer. And if it's a homochiral polymer, well, you're basically describing the crystallization stuff that we would expect to happen with DNA as well. It's like it was inevitable for this to happen when you think about the reaction mechanisms and the kinetics.
Yeah, exactly. You're definitely on the right track there. So that's another major theory. It's that let's say physics caused a slight enrichment, 1 in 10 to the 17. Crystallization or like dynamic resolution caused another bit of enrichment. Then once those biomolecule building blocks, the amino acids and sugars, start forming biopolymers, that's polysaccharides, proteins, and nucleic acids, then you get another level of amplification. It's pretty well known that if you introduce a L ribose into a DNA strand, you destabilize it because the hydrogen bond network gets perturbed and you're not going to have as stabilizing interactions. The same goes for proteins. If you introduce too many D amino acids rather than L, you'll interrupt the hydrogen bonds in the secondary structure, the alpha helices and beta sheets. Same goes for carbohydrates. So that's another place that we could have had amplification. And it seems to me like all of these must have gone together. Like the thermodynamics add up, the kinetics add up. So it seems like it makes sense. The last thing I want to mention that I think is really cool is that regardless of whether you're on the sugar first or amino acid first homochirality approach, both of them have pretty robust mechanistic studies supporting organocatalysis of the other molecule. And what I mean is let's say you're of the belief that amino acids became homochiral first, and then they were the template that resulted in the homochirality of sugars. There's been quite a few mechanistic studies and model systems in the lab that show that this works. And this has actually inspired a field of organic synthesis that won another Nobel Prize the year before in 2021. So the theory behind this is that the way sugars are made is through aldol condensations. And in prebiotic Earth, this would have been between glycoaldehyde, so a 2-carbon sugar, and formaldehyde to make glyceraldehyde, which is 3-carbon sugar, and then you can make everything else from that. So that aldol reaction without a chiral catalyst is usually racemic. But if you have amino acids, what you can do is the amino acid can do a condensation reaction on glycoaldehyde to make an enamine, and then the enamine is then chiral, right? You have the amino acid that has the side chain coming off of it, and that center beside the amine, right, alpha to it, is chiral. It's asymmetric. And then through a hydrogen bonding network, that's been shown to influence the face of the enamine that the aldehyde adds to. And this kind of concept has actually been used in organocatalysis. You can synthesize derivatives of proline or other amino acids to be organocatalysts. So if you want to do an aldol reaction, or you want to halogenate a ketone derivative at the alpha position, or any sort of thing where you want to functionalize alpha to an unsaturated bond that's going to react with an amine to make an enamine, you can do that with a chiral amino acid moiety to make an enamine and then asymmetrically induce. And then since it's a reversible formation, you can hydrolyze it back to the amine and reduce your ketone or aldehyde. And that's something that was developed in the 90s and 2000s, and that also won a Nobel Prize. Similarly, the enamine catalysis raises the HOMO, so the highest occupied molecular orbital, to make the nucleophile of the aldol more reactive with the electrophile. You can do the opposite and do iminium catalysis, where if you have an aldehyde or an unsaturated aldehyde, you can treat it with an amino acid, typically proline. You'll form an enamine, which is positively charged, an iminium, which is positively charged, make the LUMO energy even lower, and it chirally induces since you have the asymmetric center of the amino acid. So now you can take that and you can do 1,2 addition with an organometallic. You can do 1,2 addition with another aldol. You can do 1,4 addition, conjugate addition. You can do a Diels-Alder on the unsaturation. There's so many things you can do from that one framework of reactivity. And another benefit of the organocatalyst is that it's cheap, it's abundant. A lot of these chiral catalysts that rely on metals aren't very air stable. They're very expensive. They can be toxic. So that's why organocatalysis was such a big deal. And then, as I mentioned, the opposite can also happen. Sugars can also...
Oh yeah, you are so much better now. You're crispy. Yes, so where you left off for me was how the organocatalysis drives the reaction. It's cheaper, more efficient, and then that's when you cut off.
Yeah. So all I was saying was that what we found from the homochirality theories of amino acids catalyzing sugar formation in the asymmetric aldol condensations, the same sort of concepts have been used for organocatalysis using amino acids like proline to catalyze whether it's nucleophilic or electrophilic functionalizations. And the benefit of these organocatalysts is that they're cheap. You can just get them from nature. You already have the chiral center there. They're non-toxic. They're air stable. Whereas transition metal catalysts, which are typically used with chiral ligands, can be pretty hard to work with. You have to use them in a glove box. They're moisture and air sensitive. They're more expensive. But again, the drawback is the metal catalysts are usually more efficient, faster turnovers, more turnovers before they degrade or stop working. Whereas the organocatalysts, you typically need a bit higher loading.
Gotcha. Understood. Okay. Very interesting.
Yeah, and I guess to finish off that
So,
section, sorry.
how do we
Yeah, I'll finish off with one more thing.
No, no worries.
Yeah, so what I just presented was like how if you make amino acids homochiral first, they can catalyze carbohydrate or basic sugar formation with that enamine type catalysis. The opposite can also happen, and this has been shown experimentally, where I think you read this today. Was it the Donna Blackman paper on the Strecker synthesis of alanine?
Yes, yeah, Strecker synthesis was part of it. I'm not familiar with the synthesis method though,
Yep.
but
So
I did see it was alanine converting an azo. What was the other molecule into an entermerically pure form?
I think it was the. I think this is the other one. Yeah. So the
Or
other one. This is the other one. So a common way of
okay,
synthesizing amino acids is the Strecker reaction. So if you have an aldehyde, what you do is you treat the aldehyde with ammonia or ammonium, so like NH3 or NH4. That condenses to make an
hmm
imine or an iminium, and then for that you add a cyanide nucleophile, so Cn minus, which adds into the iminium at carbon. So now you have an aminonitrile. So then nitrile you can hydrolyze down to an acid. So you go from an aldehyde to an imine, then from an imine to an aminonitrile, and then from an aminonitrile you hydrolyze it to an amino acid. And evidence has shown that if you have a chiral sugar like D-ribose in the mixture while the reaction's happening, you end up with predominantly L amino acids. So that's pretty strong support for it being possible that a homochiral sugar mixture can lead to a homochiral amino acid mixture. And also, I don't think I made it clear the other way around, but the right homochirality is observed if you have like L amino acids do predominantly form D sugars when they do that aldol reaction. So there's evidence for both sides, and I think the evidence is pretty strong all around. Everything seems like it's feasible under biological conditions. The mechanistic work is solid. It's been replicated experimentally. Which one is true? I don't know. Could be both. Could be a mixture of both. Could be kind of like self-amplifying in a sense. Once you have a bit of one, it helps the other. A bit more of that one, it helps the other.
yeah,
It's kind of like auto cross-catalysis type thing. So yeah, I think it's a very cool field, and it's kind of like pieces of the puzzle where at first it was a mystery, and then now you see it all coming together.
right. Fascinating things to consider. Awesome. How do we sum this portion up? Homochirality. What is it about? Why is it important?
All right, I'd say homochirality is the idea that biomolecules in nature are symmetrically one way and not the opposite way, and it's pretty much the same throughout most of organisms. This has implications for the way we make drugs, the way we look at molecules, and it's really interesting to think about how it came about and why it is the way it is. There's a lot of different theories. A lot of them focus on carbohydrates first or proteins first. There's a lot of physical and stability studies on this, but essentially, um, there's a lot of complex interactions between these molecules, and some of those concepts can be used towards making compounds in the lab.
Awesome. That was great, man. I'm glad we went over this. And I don't know, just going through homochirality, autocatalysis, and seeing how, wait a second, we can just transition to organic molecules, especially with bioorthogonal click chemistry, or rather bioorthogonal click chemistry from click chemistry principles, how you don't really need these metals to make these reaction mechanisms occur. It pushes me a little bit towards the organic side, man, the total synthesis side. I don't know. You're kind of winning me over here, bro.
This side will accept you if you ever wish to make it yours.
The dark side of synthesis.
The dark side
10
is
hours a
calling.
day in a lab.
Dude, like, oh man, people in total
Awesome, man.
there's a reputation in total synthesis that everyone works crazy hours, and I've observed that it is true. You know, people show up before breakfast, get some stuff done, run
Yeah.
home, eat breakfast, run back. They're there. They only run home for meals. They don't sleep much. You know, I think I like to work quite a
Right.
bit, but it's a lot of experimental work. It's a lot of experimental work.
Here we go. Let's move on to the final topic before we get into questions, and that is in regards to polyunsaturated fats, PUFA, their oxidation, their mechanisms, and how it relates to some of the things that you studied with synthesis, organic chemistry, physical organic chemistry, and then we'll look at the biochemical implications. So before we even go into it, for the reader that, or for the listener that's doesn't even know what PUFAs are, they're polyunsaturated fats like canola oil, rapeseed oil is the same thing as a canola, if I'm not mistaken. I don't know why they call it
Yeah,
that. Sunflower oil, any kind of seed oil, vegetable oil
cottonseed.
would be a polyunsaturated fatty acid. Why is it important? Well, there's a large discussion between a lot of the nutritional sphere. So I was mentioning PUFAs, and in the nutritional sphere, there is a lot of discussion about why they're actually good for you, while other people have talked about why they're bad. And we feel like we can provide a much deeper understanding of what the mechanisms involved in disease are with PUFAs that aren't considered unless you're really like a chemist. You've done physical chemistry. You look at physical organic chemistry, reaction, and kinetics to really understand why they're the way they are, why they react such as oxidants, and why it's important for health. So I would say we could start this off with first. How did you find out about polyunsaturated fatty acid and their mechanisms, their oxidation products, and how they relate to disease?
Yeah, so I was actually taught this in my undergraduate courses in third year. When we got introduced to radical chemistry, it was pretty much the third example or second or third example of applications of radical chemistry, or where we see radical chemistry in the real world.
Interesting. Yeah. So yeah, that was like the second week of organic chemistry, like chapter 4. You go over lipid propagation and stuff. So orgo 1.
For me, it was actually Orgo 3. We didn't do any radical mechanisms till third year.
Oh wow, interesting. That's so fascinating. It must be totally different how they teach up there.
Yeah. Yeah, I think my school is a little bit unique in the way it does it as well. We, instead of kind of taking a reactivity approach and going through just like a bunch of different reactions in sequence, we go through a bit of a more mechanistic approach. So we just like cover an entire mechanistic paradigm first before going on to the next thing.
Interesting. We over here we don't even have a class called Orgo 3. It's either Organic Chem 1, Organic Chem 2, and then you just go through physical, physical 2, all the other stuff. And then for graduate courses, you come back to synthesis, reaction mechanisms, and physical organic chemistry. So there's like this huge gap between sophomore year of high school, of college, until graduate school of organic chemistry, which is crazy to think about.
Yeah, that's huge. That's a big difference. No, we have a clean Orgo 3 and Orgo 4 as well, which definitely like puts the pieces together,
I
like
see.
builds upon what you learned before, gives you a better background before you move on to grad school.
Now you know why I decided to look at physical organic chemistry on my own. I was like, I'm not waiting 5 years to get into this course. So
Yeah.
awesome.
Yes,
So
sir.
let's go over then.
Right. Shall we
Yeah.
dive into
What do you
it?
think about polyunsaturated fats? Did you at once think they were good? And how did you come to the conclusions that you came to now, where you realize, like myself, the chemistry behind it is actually really reactive and does cause a lot of disease?
Yeah, so it was actually never anything I thought about. I never really put much thought into what oils I cook with, or like the oils that are in processed foods or fast food. Never really crossed my mind. All I did is like I did observe just empirically that when I do eat foods that are cooked in, canola oil or whatever, it makes me feel really like slow and greasy, and it always gave me a strange feeling. So I tended to just naturally shy away from foods cooked in too much processed oils. But it was honestly only at the like last year when I went through all my health stuff and started looking into like health things on Instagram that I started to see people talking about the negative impacts of excess consumption of polyunsaturated fatty acids. And then pretty much the moment I saw it, I was like, oh yeah, no, that makes 100% sense. I've seen the mechanisms before, and I just like read more into it. And now I have a more clear biological picture of what happens on the both the chemical and biochemical basis. So that's kind of how it happened for me.
Gotcha. Okay. What are the reaction mechanisms involved in polyunsaturated fats and polyene systems that you realize we use in organic synthesis for highly reactive states or highly reactive oxygen species that you put together causes disease states? So one thing I can think of to simplify this is hydroperoxide, formation of hydroperoxides, and how this creates cross-linking with proteins. When did you put the two and two together, essentially? And what did you find from analyzing the mechanisms?
Yeah, I think I don't think I put two and two together. I think like listening to people like you and others to cover it, put it together for me, and then it just kind of makes sense based on what I already knew. But as of now, in my mind, there's a pretty clear picture of how it happens, and I can go through that. So essentially polyunsaturated fatty acids are present in the phospholipids of all membranes, especially the mitochondrial membrane. And then at the mitochondria is where you're doing oxidative phosphorylation in the electron transport chain to make ATP. So you have like NADH and these reducing equivalents shuttling electrons to the transporters, which pump out protons, and then the protons create that force, the proton gradient, that powers the ATP synthase to phosphorylate ADP to ATP. And ultimately, the last acceptor of the electron is oxygen, which gets reduced to water. Now, when the mitochondria aren't making ATP, or when there's too much NADH or not enough coenzyme Q, which is a quinone to accept electrons, you end up reducing triplet oxygen, which is the oxygen single bond oxygen diradical, which is actually the ground state most stable configuration of oxygen. It's actually not double bond, it's a single bond and two radicals. You end up reducing that triplet oxygen to superoxide, which is O minus and then bound to O radical. And this is kind of a reactive oxygen species. The same sort of thing can happen by exposure to UV radiation or ionizing radiation. And our body has like quite a few mechanisms to take care of this, since this is going to wreak a lot of havoc, as we're going to see. There's a superoxide dismutase enzyme that gets rid of it and makes it into hydrogen peroxide. And then hopefully hydrogen peroxide is going to get broken down by a catalase enzyme or some other enzymes we're going to talk about later. But yeah, the major superoxide and other reactive oxygen sources are that the reduction at the mitochondria there, the plasma membrane as well as the endoplasmic reticulum and the peroxisomes. So, okay, now we're going to dive into the chemistry, right? So once you form this superoxide, right, O minus bound to O radical, O minus gets protonated because it's pretty basic. So you have now HO bound to O radical. So this is a hydroperoxy radical. Now this is where we're going to get into physical chemistry. So for analyzing the reactivity of radicals, we use BDEs, or bond dissociation enthalpies. And these are kind of the equivalent of pKas. So for two electron polar chemistry, we often use pKas or acidities to determine how nucleophilic the conjugate acid or conjugate base of an acid is, right? If something has a pKa of 35, then when you deprotonate it, it's going to be pretty nucleophilic. Now, as for BDEs in radical chemistry, the BDE is measured as the homolysis energy. So how much energy do you have to put in to break this bond and make two radicals? Right. So for and the more energy you have to put in, the more stable the bond is and the more unstable the radical is. So the bigger the BDE, the more stable the bond, the more unstable the resulting radical. So for the hydroperoxy radical, so if you take H2O2 or HOOH and you reduce you split at the O and the H to get an O radical and an H radical, that BDE is about 88 kilocalories per mole. Now, for perspective of what that means, some other BDEs I've written down here are for methyl or like methane, like CH4, to take an H off and leave a carbon radical. That BDE is 105.
So it's favorable.
Now, if you have, so it's very unstable. It's a very strong bond. You're going to form an unstable radical. Now, if you form a carbon-centered radical that's allylic, meaning it's alpha to an alkene, that means the radical that you produce is going to be conjugated to that alkene or that unsaturated pi system. So the resulting radical is going to be more stable. So the CH bond that's allylic is weaker and is going to have a BDE of around 88. So just by adding one alkene next to that carbon, we reduce the BDE from 105 to 88 kcals per mole, which is absolutely enormous. That's a massive difference. That's an enormous amount of energy. Now, if you add another alkene on the other side, so if you have a carbon and then alkene here, and now you have another alkene there, the BDE of the CH bond between the two alkenes, this is called the bisallylic position, is 77 kcals per mole. So another 11 down from the monoallylic. Now, why this is important is that once you form a radical, you can't then use that radical to abstract a hydrogen from something that's a stronger bond, right? If you form this HOO radical from that pathway that I described earlier, that has a BDE of 88, it's not going to be able to take a hydrogen atom off of a primary aliphatic CH bond that has a BDE of 105. That's thermodynamically uphill. It's not happening. Is it going to be able to take a CH off of an allylic CH bond if it's monounsaturated fat? Yes, because the BDEs are equal at 88. However, at equilibrium, they're going to transfer back and forth because they're roughly equal. On the other hand, the bisallylic CH bond, which is between two alkenes, as in linoleic acid, which is an 18,4 polyunsaturated fatty acid, that BDE is 77. So even if the HOO radical takes some from an allylic or a monounsaturated fat, at the end of the day, you're going to take the H dot off of the bisallylic CH bond because it's the more stable radical. That radical is conjugated across 5 carbons instead of 3, and that's the most stable thing you're going to form there. So now, that was a lot to digest. I'll pause there. So now, we made that superoxide O minus next to O radical. We protonated the O minus. Now we have HO radical. That O radical has a BDE of 88. The most accessible thing it's going to rip off is the CH bond that's bisallylic on a polyunsaturated fatty acid like linoleic acid. Since the radical that you form is on carbon and it's stabilized by conjugation by 2 alkenes beside it, and has a BDE of 77, so you're downhill, thermodynamically favorable by 11 kcals per mole. I'm going to pull up the calculator actually. A difference of 2 kcals per mole is already more than 99 to 1 at equilibrium. So let me pull up calculator.
I like to stay with
energy.
kilojoules. One of the reasons I just don't like calorie units, but I get you. Go for it.
Yeah, I was taught phys org in a very classical kcal way from like older textbooks. I'm not finding it right now. I'll tell you the figure when I find it, but it's essentially like many thousands, maybe millions to 1 at equilibrium. So now you have all these radicals derived from polyunsaturated fatty acids where you've abstracted an H dot from the bisallylic position between the 2 alkenes. Now what happens? Well, carbon-centered radicals have a propensity to combine with triplet oxygen, which is just ground state oxygen. So the carbon dot between 2 alkenes is going to very quickly react with that triplet oxygen. The rate constant for this is 10 to the 9 per molar per second. 10 to the 9 is pretty much almost diffusion controlled, which means the moment they bump into each other, if they're anywhere around each other, it's just going to happen very quickly. Now this is going to produce an alkyl peroxy radical. So you have 2 alkenes, a carbon here bound to O and another bond to O dot. So you have an alkyl peroxy radical derived from that polyunsaturated fatty acid. Now the resulting radical is a peroxy radical again. So now you have a BDE of 88. Now you might be thinking, you just said you can't go uphill from 77 to 88. How come we ended up with a new radical that's more reactive than the old radical? The reason is because we didn't abstract, we didn't break a bond. All we did is form a bond between a diradical and a monoradical. So now the instability that you gain by making a less stable radical is made up for by the formation of a CO bond, which is a lot bigger than that 11 kcal difference. So that's why you go from the more stable bisallylic radical to the less stable alkyl peroxy radical, because you're forming a CO bond, and that's really favorable. So now you have something with a BDE of 88 again, and this becomes a radical chain. Now you have ROO dot, and that ROO dot is going to do the same thing. It's going to pull another H dot off of another PUFA, and then it's going to do the same thing, combine with oxygen. Now you have OO dot again, pull another H off another R, and you have another R dot from the bisallylic position of another linoleic acid, linolenic acid, or arachidonic acid, or whatever it is, and then you combine with oxygen again. So very rapidly, you have this radical chain where you end up formally inserting oxygen between that CH bond, and this process is called autooxidation, like auto-oxidation, and pretty rapidly you can insert oxygen and form these alkyl hydroperoxides. So that's the beginning of that. I think we'll pause there if you want to have some input.
Let's summarize that portion for the average listener, because I'm sure they're even wondering what the hell is bond dissociation enthalpy. First of all, the way I learned it, funny enough, was bond dissociation energy, but the enthalpy is the right term here. It's like, why did I read the textbook and they're saying energy? It's like, you have to differentiate between what types of energy. So thanks for clarifying that, because I've never heard it mentioned that way before. But second, so really quick, before I even go to summarizing that, Autooxidation can still happen without the singlet oxygen species being produced. It can happen just based off of light energizing the electrons in the pi bond into a higher electronic structure, right? And then that reacts with like a perfectly stable oxygen or some kind of nucleophilic group that reacts in the same fashion. Is that correct?
I believe so. However, the way I've read it is kind of the opposite way around, where you need the reactive oxygen species to abstract the CH first. So
With, even in the presence
I
of
guess
the
what we're
in the presence of the light, like it has to have the
yeah.
reactant
So
there.
yeah, so if you just have oxygen O2 diradical and then the polyunsaturated fatty acid here, or the bisallylic CH bond, if you have, you know, the like excess like the mitochondrial activity, that's going to reduce the oxygen to make the superoxide, and then that abstracts. Or light is going to is going to promote an electron transfer from something to oxygen. And I think based on what I've seen, the electron is transferred to the oxygen first, then that abstracts the CH bond, not the other way around where you
Gotcha.
excite the pi system first. So I
Got
guess
it.
like in from a broad sense, it doesn't matter what absorbs the light first, but it can either be just like an electron comes in from a mitochondria or something and it produces that superoxide, or light promotes some excitation in the oxygen. I don't think it's the pi system first.
Got it. Good to clarify. Thank you for that. Okay, so summarizing this, essentially, during the process of metabolism, your body's going to produce singlet oxygen species that will react with PUFAs. PUFAs in their pi bonds will form a favorable product that then allows a propagation of other radicals to be produced to react with other PUFAs. And so you get what's called lipid propagation, where many PUFA radicals are being produced. This leads to a cascade of cellular effects where the inflammatory process from all of these radicals damaging biomolecules quickly gets overwhelming. The mechanisms by which this happen depend on bond dissociation enthalpy. That's to say, how much energy does it take to break and make a bond? Is it favorable to make a bond, or is it unfavorable to make a bond? That's determined by the energetics of an atom like hydrogen bonded to an atom like carbon. When it comes to saturated fats, the bond dissociation enthalpy is higher, correct? Like it's at 100 something kilocal per mole. And then when it comes to
Correct. Yes. So
bisallylic,
if it's fully saturated, it would be fully saturated would be something like 100 to 105. Monounsaturated would be something like 85 to 90, and then polyunsaturated, where there's a bisallylic position, would be around 75 to 80.
And to clarify for people, bisallylic means that if you look at a carbon, on both sides of that carbon in the PUFA the polyunsaturated fatty backbone, on both sides of the carbon are pi bonds. Pi bonds mean essentially double bonds. And those are what allow the favorable reaction to occur in the first place with making peroxyl radicals. And that happens again because of the presence of reactive oxygen species. Essentially, PUFAs act as the perfect conduit to a highly inflammatory process that is very reactive, whereas other fats like saturated and monounsaturated don't have favorable energy conditions for this to occur. And so by definition, we would expect PUFA oxidation to be a really unfavorable circumstance in the human body. And that could make sense why our bodies don't use so much polyunsaturated fatty acids as in so far as for building certain structures. It's not it's not a big amount as compared to saturated fat, cholesterol, to keep the body and the structure stable. And at the same time, we don't want it to be around a lot of reactive oxygen species, because then it will produce those lipid peroxides and peroxy radicals that allow the propagation to occur in the first place. Yeah, so it's a small amount. The body still uses saturated fats, cholesterol, and other aliphatic fats to keep membrane structures like in the mitochondria and the cell membrane. If it had mostly PUFA, this auto-oxidation mechanism would wreak havoc inside of cells. And it also depends on the amount of antioxidants that are present in cells to stop this process. So there's definitely some caveats to PUFA based off the reaction mechanisms, the concentration, how likely it is to occur, the amount of antioxidants that prevents this oxidation process. But overall, the reaction and the kinetics suggest that, hey, PUFA will oxidize easiest and it does cause the most damage. What do you think then in regards to reconciling with what the evidence shows? And when I say evidence, I loosely quote it because it depends on what it is. We're presenting evidence is just not appreciated unless you're a chemist. Um, what do you think in terms of like clinical trials that use 10 grams of sunflower oil and they see a beneficial outcome in inflammatory markers over, like, say, a 10-week period? How do you reconcile that with the mechanisms involved? Because a lot of people in the nutrition sphere say, well, the mechanisms don't matter when clinical trials show an opposite results, when in reality, the mechanisms are the most defined phenomenon. They're the physics and the chemistry that you use as a chemist to have the same molecules being produced over and over again. It's like the most repetitively certified phenomenon.
Yeah. So the way I think about that is that, like you, I like to think that to understand a phenomenon in depth, we have to see both the clinical outcomes and understand a mechanistic basis of like what's actually causing that and what's explaining it. So sure, if you see like 10 grams of sunflower oil over however many weeks or months produces so ever many percent reduction in inflammation, okay, how is that happening? Is there a mechanism by which that's happening? Is there biochemical evidence for which that's happening? And also, that observation doesn't rule out the fact that the PUFA oxidation and autooxidation and oxidative stress could also be happening, but in a more chronic long-term sense, right? Sure, you might have this short-term reduction in inflammation, but if you're then storing and accumulating these polyunsaturated fats, what are the possible outcomes of that under a more oxidizing environment over many years as well?
Beautifully stated. And that comes down to the aging process as well. It is well defined that as you age, polyunsaturated fats do accumulate in tissues. And once they do, the second phenomenon that occurs is our production of antioxidants goes down. We don't produce as much glutathione. We don't have the means to reduce the oxidants that are produced as effectively. And so what winds up happening is the tissue, rather the cells, form these huge conglomerate of PUFA oxidation byproducts that eventually polymerize and they become lipofuscin or lipofusion. It's another, there's no real like way to say it, but it's essentially a bunch of PUFA byproducts with iron, with oxidized or glycated amino acids, all into this one giant polymer that fluoresces. The fluorescence is because of the bisallylic carbons, and that provides the absorption of light and emission that you see when you look at lipofuscin under fluorescence microscope. And what do you see? You only see it with people that are older and have accumulated these polyunsaturated fats along with the oxidants involved, like the metals or possibly the reactive oxygen species. So what you're mentioning about the long term is a real factor here. These clinical trials have not been done over 30 years, 40 years, 50 years, the lifetime of an individual, and it doesn't consider the other mechanisms like the antioxidants provided by some of these seed oils. Like there's still vitamin E in there, and that depends on how it's processed as well. And even if you look back on a retroductive analysis where you're looking back in patients and how much oils they consume, and when you try to account for other factors like their diet overall, their lifestyle habits, and their activity levels, those are all still factors influencing the outcomes. What do you think about that? Do you agree with it? Do you have any input or do you disagree?
In terms of the long-term outcomes?
Yeah, everything mentioned with the lipofuscin and retroductive analysis.
Yeah, so the lipofuscin thing is actually not something I was aware of. I think that's really cool in terms of the fluorescence of it.
hmm
But in terms of oxidation, lipid autooxidation and long-term disease, I think there's definitely a growing body of evidence and uh, pretty strong body of literature pointing to its involvement in a variety of diseases, whether it's cancer, neurodegeneration, cardiac issues. That like lipid oxidation is something that's widespread in all of those diseases and has been shown to be
Yeah,
correlated. So
if
there's
I'm
like
not mistaken.
there's kind of both. There's both. There's both
Yeah,
pieces of evidence. There's the biochemical basis, the chemical reactivity, and then there's the long term retrospective analysis on it.
yeah. I said retrospective. Excuse me. I was thinking retroductive.
Yeah.
I was thinking retrosynthetic analysis. Oh man. All right. So, um, what did you learn in regards to like PUFA oxidation that this is how we connected actually, and became friends. It's like you sent me this lab that was using PUFAs to analyze single radical reaction mechanisms through radical trapping. What did you find out about that lab and their mechanisms and how it relates to PUFA oxidation?
Yeah, so I think before we get there, I have a bit more stuff to cover in terms of like
Let's go for
the
it.
physical organic chemistry behind these radicals and what happens. So you mentioned the antioxidants, vitamin E and glutathione a couple times. So I think it's cool to like explain how those work as well.
Yeah, go for it.
So vitamin E, the way that works is it presents an OH bond, a phenol OH bond that is weak. It has a BDE of 75 kcals per mole. So this acts as a radical trapping antioxidant. So once you've already oxidized the PUFA and made the ROO minus or the lipid peroxy radical, vitamin E can then transfer the H atom to make an O radical on vitamin E and quench the reactivity of that radical, the radical from the lipid as ROH, terminating the cycle. Now, the reason this works is because vitamin E has a BDE of 75, which means it can no longer abstract H from the unsaturated fatty acids because it's a more stable radical. So it's a weak bond. It presents an OH or an H that can be trap the radical, and it terminates the radical chain. Some more comments on the kinetics of this. I mentioned that once you form the alkyl radical, the rate constant for combining with oxygen is like 10 to the 9 per molar per second. The limiting step in the radical chain is thus the abstraction of the H from the bisallylic position. Now, once you form the peroxy radical, the peroxy radical can either transfer the H from vitamin E or it can take it from another lipid. So obviously we want it to take it from vitamin E, and that process is 500,000 times faster than taking it from another lipid. So that's why vitamin E is a crucial antioxidant there. And a lot of this kinetic and physical organic work was carried out by Ned Porter at Vanderbilt in, I think, the 90s and early 2000s, maybe a bit earlier as well, but that's where I've seen it most. Also, their lab did a lot of cool stuff in terms of like characterizing the rate constants of the propagation chain for different unsaturated acids, unsaturated fatty acids. So other than just the BDE, there's also now rate constants for the overall rate of propagation in the chain for different unsaturated acids. So the bigger the rate constant, the faster this happens and the worse that is. The figures I have here are on a log scale, so log of the rate constant. So again, bigger is still better, but the numbers are like squished down. Mm-hmm. So we'll start with linoleic acid, which is an 18,2 unsaturated acid. So it has 2 unsaturations. This has a log rate constant of 1.7. Linolenic acid, which is 3 unsaturations, is 2.2. So the chain is 10 to the 0.5 faster. Then arachidonic acid is 2.3. And docosahexaenoic acid, which has 6 unsaturations, is 2.6. On the other hand, oleic acid, which is monounsaturated, is negative 0.1. So going from a monounsaturated acid to a polyunsaturated fatty acid, you essentially increase the rate of radical propagation for that autooxidation process by 100 to 1,000 fold.
Kian, can you hear me? All right,
Yep.
So the video on your side is saying the live video will return when the internet improves. Let's just do it without video, because then I'll take my video off as well.
I'll go without video. Yeah. Did you hear me there though?
Yeah, I did. But the video cut off entirely. So I got the docosahexaenoic, and then oleic acid was negative, and then that cut off. So let's go from there. Let me just turn off my cam.
Yep.
So just let you know really quick,
so
we're at
the polyunsaturated acids. The polyunsaturated acids, just to review, were like 1.7 to 2.6. The more alkenes you add, the higher the number. The monounsaturated oleic acid is negative 0.1. So remember, this is a log scale. So from negative 0.1 to like 1.7 to 2.7 is around 100 to 1,000 fold faster radical chain autooxidation for the polyunsaturated acids compared to monounsaturated.
Interesting. I seen that graph as well from the paper. I didn't know that was from the exact author that you're talking about right now. And it's interesting with rate constants. So I'm well aware of like omega 3s being even faster in oxidation than omega 6s. And that's also something that I've considered.
Yep.
It's like, well, then they should have the most negative effects. In reality, we don't see that until it's like a two things become the factor. One, the amount of omega 3s that get stored in tissues is easily displaced by omega 6. And so the half life is much quicker than omega 6. And so the amount of byproducts that get produced is less. And two, the amount of omega 3s that our tissue use and our cells use is even less compared to omega 6. Like we don't need more than 5 grams at most of omega 3s to hit our daily requirement. And so the negative byproducts that are made are much less in total molar quantities. Um, and then the other thing is the lipid mediators involved, even though they might be radicals, they're still immunosuppressive. So the net outcome is a benefit, meaning that inflammation is reduced, even if the radicals are produced. But just because the inflammation is reduced doesn't mean the radicals haven't caused damage. I found that fascinating to consider. And now with the rate constant, it makes a lot of sense why. I never considered that with the rates.
Yeah, that's wild. I've never heard of that either. I think that's really eye-opening as well to hear about.
It's like both the beneficial and the negative outcomes can simultaneously occur, and you won't know the outcome of the negative side until a couple years down the road.
Yeah, exactly. Talking about the negative side again, I think one thing that I only understood recently is, what happens to these lipid hydroperoxides after they're formed, like ROOH. Why are they bad? How do they cause damage? Well, this was actually not understood for quite a while, but it's pretty clear that they do rearrange and form either aldehydes or unsaturated aldehydes, which again, as we
Uh-huh.
mentioned earlier in the podcast, are pretty reactive electrophiles and are then going
Yep.
to alkylate DNA and proteins, wreak havoc, cause disease, mutations, and this is where we get into the research carried out by that lab down the hall from mine, which is ferroptosis. So, um, essentially, a lot of long-term clinical studies or retrospective analyses have shown that lipid oxidation leads to cancer, neurodegeneration, and cardiac diseases. But the other cellular kind of outcome of lipid hydroperoxides is ferroptosis, which is a mechanism of cell death, which is iron promoted. And lo and behold, iron is also believed to be responsible for catalyzing a process that converts the lipid hydroperoxides into aldehydes.
Mm-hmm. That's fascinating. And what's funny about this is lipofuscin is a byproduct of the same mechanisms as well. So the aldehydes are always there as well. The same electrophilic aldehydes. In fact, the same electrophilic aldehydes present from omega 6 oxidation through iron or through auto-oxidation, like 4-hydroxy nonenol is one that I can think of immediately, are the same ones that researchers use to induce mutagenesis in models of like mouse cancer.
Yeah, exactly. Um, as well, just increases in PUFA consumption are used to further promote that cancer generation in mice.
So there is plenty of evidence in regards to this, in my opinion. So yeah, what is that lab looking at in
Yeah,
specific with like radical trapping? Because I found that fascinating.
yeah. So essentially, they're trying to synthesize new molecules that serve to trap radicals in the same way that vitamin E does. So as I mentioned, vitamin E has a weak OH bond that then provides the H atom to the lipid peroxy radical to terminate the chain. And vitamin E is great and all, but you, it's not the best. You can certainly conceive better
Hmm.
antioxidant radical traps that do it a lot more quickly. So that's essentially their goal. And the way they study this is by studying ferroptosis outcomes on
Hmm.
cellular scale, and also studying the kinetics of these processes on the kind of chemical molecular scale.
Interesting. And what was the thing about ferroptosis that captured your attention in particular? Was it just like how the aldehydes not only induce electrophilic adducts in DNA but cause ferroptosis?
Yeah, so ferroptosis itself is kind of a funny thing, since the PUFA oxidation is well known to be correlated with long-term chronic diseases, and it's well known to contribute to ferroptosis. But kind of the link between ferroptosis and chronic disease isn't that well understood. It's believed that inhibition of ferroptosis might help for some disease treatments, but also that induction of ferroptosis might help in treating cancer. So I think it's probably one of the most recently discovered or recently studied mechanisms of cell death, and it's just one of the possible things that a hydroperoxidated polyunsaturated fatty acid can do in cells. And it also just provides a really good readout of the effectiveness of a radical trapping antioxidant. Once you've developed it chemically, you can just test it out, see if it works in cells by inhibiting that process and seeing if it reduces ferroptosis.
Fascinating stuff. Man, the more chemistry I learn, the more I realize chemistry really might be the way in understanding a lot of these processes. I mean, when I look at the papers that you sent me in regards to lipid oxidation, they're some of the most in-depth papers that I've ever seen, and I'd rather read them because of how complex your understanding has to be of all the different processes than the clinical trials involved, because you're left with the black box of, I don't know how this happened. I just know that it did happen, and I cannot stand that.
Exactly. That kind of black box feeling is what kind of pushed me away from biology. Like, just the way it was taught, the way a lot of the research is these days, it just seems like they're messing with statistics and messing with the way they measure things. And sure, all of those are really important to get a good study down. But to me, if you're not understanding the basis of what's happening at a biochemical, molecular, chemical level, what are you really studying?
Yeah. So what do you have to say to individuals that say mechanisms don't matter in the face of clinical outcomes? What would be your rebuttal to this?
I would ask them to explain how it's happening. If you can't explain how it's happening and you're just saying this happens and we're seeing it happen, then how can you be sure that this is what's causing that outcome and that it's not causing something else and that something else isn't causing this, right? You can do so much to control variables and randomize things and yada, yada, yada. But unless you know exactly how that thing's happening, I don't think you're ever going to be able to conclusively argue that this is the way it is.
From my understanding, when I looked at controls, randomization, the process of determining causality in medicine, you can do so much more with animal models and in vitro models because you're able to control for a lot more confounders, and that's how you actually identify a causal pathway. It's like you're actually determining with greater clarity when it comes to preclinical models than you are with clinical models. And then the clinical models are just to show proof of concept that, hey, what we thought was accurate is actually accurate.
Exactly. I agree 100%. That also just makes me think of something else in terms of like drug development and the way clinical trials work in the pharmaceutical industry. They follow exactly this kind of pattern. They first discover a compound that has a certain effect, whether it's anti-inflammatory or anti-cancer. Then they spend a long time trying to figure out how it's doing that, what's the molecular target, what enzyme or receptor is it binding to. Then they improve it, make sure it's still binding to that same receptor. Then they go and do, single variable changes in animals. That way they can like control everything from diet to exercise to exposure in the environment, the amount of compound. They can pump it up massive amounts. And they're like, okay, we know what it's doing in cells. We know what it's doing to enzymes. We know what it's doing to animals. Now we do the clinical trial. Now we see what it does in people. And then we can start making conclusions about whether this is useful or not. And I find it funny that a lot of people who kind of criticize the way clinical trials are run in pharma are the ones who are like believing all these nutrition clinical trials, whereas the biochemical basis of that is a lot less robust.
Right. It's funny.
Like if you're applying certain standards to drugs, why not apply the same standards to food?
Yep, I agree. And food, I mean, that's what total synthesis is. You're pulling out the key molecules from all of these different products that we can still consider as food. So I think, again, chemistry is the most important thing here.
Yeah, and food is the most important drug because you're consuming the most of it, and you can't just not.
Well, careful, brother. You can't say that food is medicine. God forbid.
Oh no.
Awesome, man. We got through it. We got through all the technicalities, and we spent so far 3 hours and 5 minutes, man, which is amazing to think
That's
about.
it,
So we're on the. We could have kept going. That's true.
bro.
We.
It's been 4. It's been 4.
Oh wait, you're right. It's been. I only have 1 hour left of this before I hit my limit on Riverside. Let's see if we could sum up the
Oh, that's
questions.
fine. We have 20, dude. We have 25 questions,
questions,
or like
awesome.
22. I removed a couple.
Let's go for it. Let's spend no more than a minute on each question and go from there. So, question number 1 comes from my cell and molecular bio professor, Dr. Neil Copes. And he's asking in regards to the mechanism of action for AZT, azithromycin, and why is it controversial for treatment? What did you find out about that?
Yeah, so this is something I wasn't very familiar with. I've never studied this drug in class, but did some reading on it, and it's very similar to a class of compounds that I've studied in the past. So essentially, it functions by terminating the reverse transcription of RNA to DNA. So I'll backtrack there. So azithromycin is an antiretroviral drug that is used to treat HIV, and it's an analog of thymidine, the DNA base, where the C3OH is replaced by a C3 azide or N3, and when polymerases are extending DNA or RNA chains, they use that 3' to add the next sugar, and that's how you extend from 5' to 3'. So if you don't have an OH there, you can't do the next step, and you terminate. So that's what the azide does. Now this drug works by selectively inhibiting the virus's HIV reverse transcriptase that converts RNA to DNA selectively over the human DNA and RNA polymerases. I think based on selectivity, just like by the biochemical affinity for the enzyme active sites, the selectivity is 100 to 1 for the HIV polymerase over the human polymerases. 100 to 1 in medchem isn't that great, but this was the first ever HIV drug to be developed, so it was kind of pushed. The other interesting thing about the drug is that it's a prodrug, actually. The 5' OH is a free hydroxyl group. So to get activated, you have to phosphorylate and then make a triphosphate. That's pretty common for antiviral drugs. So it's pretty typical among antivirals in that it mimics a DNA base or like a nucleoside, and there's no it acts as a terminator. So once it gets incorporated, you can't add any more bases, and it's a prodrug. You have to phosphorylate it. So in terms of the mechanism of action, it's pretty similar. Something like acyclovir does a similar thing, but acyclovir is a lot more selective since to be activated, acyclovir only gets phosphorylated by viral enzymes. It doesn't get phosphorylated by host enzymes, so it only gets activated in the viral cells in the viral molecules. So that's why it's selective. But the kind of controversy around AZT, there's a lot of information on the internet about this. There was some controversy about the patenting of it, saying that it's off patent and that the patent was illegitimate. There's some controversy about the clinical trials being unethical and how they gave people placebo when they shouldn't have, or that their double-blindedness was lost and they weren't double-blind anymore, and that the physicians and people figured out what was going on. Also, there's some claims that there were a lot of early deaths that could have been avoided due to it. I think the other issue it brought about is resistance. A lot of HIV strains started becoming resistant to the drug. Essentially, they were just when these things replicate so quickly, you get mutations in the genes coding for the enzyme, and you get new enzymes that don't incorporate the base that terminates. So now the drug doesn't do anything to it. And for a first ever I haven't dug that deep into like looking at the clinical trials, seeing if they were done properly, seeing if there was evidence for it working. But for the first ever drug for something that was about to be so deadly to the human population, it could have been worse, I think. And of course, there's going to be some controversy about it. I'm obviously not certain about everything there, but at the end of the day, it did light up some issues about, single drug therapy is bad. It's not really used anymore today. It's been replaced by less toxic things that are more selective. Nowadays, you typically want to do multiple different drugs that address different parts of the HIV life cycle so that you don't get resistance.
Got it. Awesome, man. Thanks for going down that rabbit hole and being so thorough with it too. I think he's going to appreciate this. And Dr. Copes, if you're listening, yes, I thought about mitochondria too. So interestingly, this drug, it causes fission of mitochondria, and it prevents these protein called mitofusins that fuse mitochondria and allow phosphorylation to occur. And I'm not sure if you ever thought about this, but like when mitochondria do oxidative phosphorylation, they usually make this thing called a super complex, where it's a bunch of mitochondria jumbled together, fused, and they elongate. And so there's a greater surface area, and it seems like it improves electron transfer for the phosphorylation to occur in the first place. And what the AZT does is it stops the fusion of mitochondria to preventing this protein from acting. And the first thing I thought of is like, why would that be the case? And the azide group, I thought about with click chemistry, maybe there's something there involving the iron sulfur complexes of mitochondria, because what it doesn't do is it doesn't damage mitochondrial DNA. So I was like, I wonder if this relates to click chemistry, but I don't know if you can think of anything.
Yeah, I can't think of anything off the top of my head, but that mitochondrial interference is definitely something I skimmed through when I was reading this.
Mm-hmm.
I opted kind of not to dive into that route since I wanted to give a kind of
Yeah.
like generic overview of what's been said about this drug, but that's definitely interesting. I also didn't know about the mitochondrial aggregation to form more
Yeah.
efficient
Very
electron
interesting
transfer
stuff.
complexes there. That's pretty cool as well.
Biophysics stuff.
Yeah.
All right, next question. 3 biggest tips for overall health.
I think we kind of did that. I'd say food, sleep, exercise in that order, basically.
Let's go a little bit further, maybe like 30 seconds,
Yeah.
saying in specific,
Sure.
why is it so important to be so focused on the foundations? Like, why not just take a supplement?
Right. I actually had this discussion with someone earlier today. He messaged me saying he's like plateaued in his lifting. He wants to try creatine. I'm like, okay, sure. There's evidence creatine works, but you're gonna have a bigger impact on if you improve your basics, like your actual training or your sleep quality or your food quality and quantity. So those 3 things are kind of form the pinnacle of what keeps your body healthy and have the biggest impact on your health outcomes rather than supplements. Obviously, if you have those other 3 things, your food, sleep, exercise figured out and pretty much optimized, or close to being pretty good, then supplements can augment that. But getting consistent sleep, on kind of sleep cycles of 1.5 hours, either sleeping 7.5 or 9 hours, I think is really beneficial. Sleeping at a consistent time that goes with your natural circadian rhythm with sunrise and sunset.
Yeah.
Waking up at the same time, eating whole foods, unprocessed, getting all your proteins and micronutrients and everything else in. Exercise, doing some cardiovascular work, some muscular strengthening, not only for just health and fitness or activity, but for preserving bone density, cardiovascular health, blood circulation, focus, mood, everything kind of improves.
Yeah, I think most people are looking for that new thing that they can focus on that sounds cool. Like imagine if we can take organometallic chemistry and really market that. It's so new and it's so niche that people would fall in love with it just because of the cool terms. So it's like when you repeat these simple process of circadian rhythm, sleep, because this happens, like, oh, I've heard this before. Yeah, you've heard it, but you're not implementing it truly, and that's possibly one of the rate limiting factors for improvements in areas of health.
Yeah, definitely. I agree. I think people are looking for that quick 10-minute exercise or like that quick supplement or drug to help them. But the other outcome of that is either put in the work and take care of yourself now or pay for it later. Or, you can either be lazy and not take care of yourself and just be on, blood thinners and heart meds and whatever for 20 years, or you can take care of it. So I think that's a conscious choice a lot of people have. It's either be on top of your health or just accept that you're going to be more miserable later in life. So,
yep. Awesome. Next question by Biochem Casey, otherwise known as Casey Clark. He's our computational physical chemist friend, so he probably hates us right now after what we said about computational chemist. But Casey asks, why do you partake in such witchcraft, creating these potions and spells? What is the motivation? Also, have you looked into density functional theory to predict reactivity and create synthesis pathways?
All right, so addressing that first part, we partake in such witchcraft of organic synthesis because it is fun and we get to discover new reactions and create new molecules. And Maybe someone will use them to make other molecules someday. Maybe it'll make something more efficient, more sustainable. Maybe it'll be able to affect biology and study something better. But yeah, it's fun. I think one of my previous supervisors said like organic chemistry is one of the fields where you get to study your own creation. You're like creating the system that you're studying. You're synthesizing a new molecule to study or a new reagent to study. Unlike biology or like, I don't know, physics, where typically you're, just studying the natural system, and organic chemistry or synthetic biology or those type of fields, you're creating something new and then studying it.
Yeah.
Oh, and then the second question, have I looked into using DFT to predict reactivity, create synthesis pathways? So DFT to create synthesis pathways would take ages. DFT for each possible step you're considering would take way too long. The solution to that would be like an AI synthesis, retrosynthesis planning thing. But for predicting reactivity, yes, that's something we've looked into. Let's say you have a key step and you want to see if pathway A is favored or pathway B is favored, or diastereomer A or diastereomer B, and you want to just get a quick idea, like computationally, of whether it's viable or not to get the desired outcome. Sure, running a DFT, even if it takes a couple weeks, is faster than doing the synthesis to get there. But at the end of the day, no matter the result, we're still going to want to make that model compound or that molecule and try the reaction out and see what happens. So, typically if there's a step like that, we'll either do the DFT first and then run the experiment and see if it helped us predicting whether it's worth it or not. Or if we run the experiment and want to understand it, then we'll do the DFT after, see why it happened and support our initial idea.
Awesome. Matthew asks, will DJ squat 405? Why can't you spell morning maniacs? What would you be doing if you didn't lift?
All right, so Matthew is one of the new boys I've met in the gym. So when I started lifting a couple years ago, I mentioned, Powerlifting club. All the guys were older than me. They all graduated. I inherited the club. Now there's a new team of, younger guys coming into first year. Matthew is one of them. Met him in the fall. He's part of the morning lifting crew. We call ourselves the Morning Maniacs. I made the group chat and I made a massive typo, and it does not say Morning Maniacs, and we just kept it. So that's why that question's there. Will DJ squat 405? DJ is another one of the crew. He's also doing a master's in chemistry, kind of the more like, I don't actually know what he's doing, to be honest. It's more biochem related. He's honestly more of a biologist, to be honest. He's like expressing proteins and whatnot, but he's also pretty good at like computational stuff, and I think he wants to do that in the future. So we'll DJ squat 405. He failed it yesterday, and I spotted it, so I think that's his third fail. So eventually he'll get it. But
DJ,
what would you be doing if you didn't lift?
I was gonna say for DJ, hey bro, look,
what were you gonna say?
I was just gonna tell him it's all right to just hop on a cycle, man. Even if it's for one cycle, it's all.
Dude, I knew the moment you started talking, I'm like, this guy's gonna say he should take Tren. But here's the thing, right? If you say, bro, just hop on a cycle, that's the same thing as like, bro, just take a supplement and you'll be healthy. Like, dude, he weighs 155. I'm like, dude, gain 5 pounds and you'll squat 430. Like, come on, man.
Agree. And he could do it quickly if he just hops on a cycle. So just saying.
Yeah. Okay. What would you be doing if you didn't lift? I think I would have been cubing for longer, and I would have been better at cubing for longer if I didn't lift, since cubing took a lot of time and energy away, and like, hand fatigue from gripping bars made me worse at cubing. So I would have probably kept cubing for longer, but I would have definitely tried to do something else active. Maybe a combat sport, maybe wrestling, maybe probably more running, I'd take up a combat sport, either boxing or wrestling. And I think, something like that.
Nice. What's your best tip for improvement on bench press?
My best tip is get a coach if you can afford it, or if you can't afford a coach, learn things online yourself from reading books and watching YouTube. If you can't do that or are too lazy to do that and you just want to listen to me saying what I want to say, think about how many times a week you're benching and probably add one, and probably do more reps than you're doing right now. Probably do higher rep ranges and lower rep ranges. Probably improve your technique to have more control and keep more tension in your pecs. Probably add some variations like a tempo bench to reinforce that proper positioning and proper bar path. But yeah, something like that.
Opinions on omega-3s having multiple double bonds and being more unstable than omega-6 and saturated fats. Since we already talked about this, you could give like a summarized version.
Yes. I'll actually let you do that.
Okay, sure. So, yeah, omega-3s are more unstable, and Kian mentioned it with looking at reaction rate constants. Clearly, DHA is very much more unstable than linoleic acid and omega-6, and the instability does contribute to different byproducts made, same radicals, but the amount of omega-3s that we have as part of our tissues, as part of our diets, is much less than omega-6, and so the concentration in general is going to be less, and also because they produce certain lipid mediators that reduce immunity, it looks like inflammation drops even though you have these radicals being produced. So it's very interesting in that it has both a beneficial and negative outcome, as most things do, and you wouldn't notice the negative outcomes probably until decades down the road. So I'm not a fan of supplementing omega-3s, and I haven't done it for years now, and I'd probably only ever do it if the case was like clotting or acute heart attack where you can help thin out the blood with omega-3s.
Sweet. I like that answer. It was very succinct and detailed and to the point at the same time, and gave a broad overview of the conflicting factors there.
Yeah, that's the paradox stuff. Always got to take that into consideration. All right, best place to start teaching some. Sorry, best place for someone to start teaching themselves chemistry and understand drug synthesis. How should a physics graduate student approach learning organic chem?
Yeah, so I guess these are kind of the both the same answer. I'd say pick up a textbook, the best introductory organic textbook for learning basic reactivity fundamentals, mechanism, orbitals, all that stuff is I don't remember what it's called. I just call it by the author name. It's by John Clayton and Stu Warren. So just search up like Clayton second edition, Clayden, organic chemistry second edition or something. That's the go-to book for anything undergrad level. It'll take you from not knowing anything to being able to like name compounds, understand how they react, understand why they react, and be able to see, by the end you get down to some pretty modern chemistry in terms of like organometallics and metathesis and couplings and stereoselectivity and synthesis. And just from that book alone, you'll be able to honestly like open a drug synthesis, maybe not modern, but like maybe some modern, but from like 20, 30 years ago, and you'll be able to understand some stuff. After that, I'd say if you're only looking for it, if you're only looking into organic chemistry for like general interest, after you've read that, look into YouTube. There's a couple good channels on there. They're called like Total Synthesis, Simplifying Synthesis. There's a couple more I'll remember, but those do a really good job of like breaking down different drug syntheses, natural products, new developments in the field to a level that an undergrad or someone, honestly, like once you read Clayton, everything else becomes pretty easily digestible based on that fundamental knowledge.
Awesome. Good. I also concur with the recommendation. Like, there's no better way to learn than just opening the textbook. And as a physics student, this is my buddy. He knows already like orbital stuff more in a physics sense than we do, possibly. So I think he's more than ready to tackle organic chemistry if he wanted to. All righty, next question.
I think the benefit physicists and mathematicians have is like organic chemistry is easier for them. It's like less down the fundamental theory rabbit hole.
Next question. Iodine can leach through plastic. Can it also degrade it? So this is something I wasn't aware of. What did you find out in regards to this?
Yeah, I wasn't aware of this either. I did some reading today, and turns out yes. It turns out either iodine, the diatomic molecule, the neutral diatomic molecule I2, or iodide, both under UV light can accelerate the degradation of certain plastics, mainly the poly and perfluorinated alkyl compounds. Essentially, you like homolyze or you induce single electron transfers to get iodine radicals, and then those electrons that are freed end up reducing the carbon-fluorine bonds to get carbon-hydrogen bonds. So there's potential applications to like PTFE degradation or polyfluoro something ethylene, something like that. It's been shown that like UV light with sulfite does it as well, but then combining sulfite with iodine and then also irradiating with UV does it as well. So This is just something that like people have observed empirically. If you like store iodine in a glass bottle and have a plastic cap, the plastic will start to degrade in the cap. So you have to store it in a glass bottle, and the bottle's dark to prevent UV from homolyzing it. But also recent like process and engineering stuff has shown that if you purposely like irradiate under UV in the presence of iodine or iodide, you will start to break down polyfluorinated alkyl compounds and their
Awesome.
plastics.
Beautiful, beautiful answer. I had no idea. All right. Root cause of celiac
Yeah,
disease.
same. I think it's pretty cool. Yeah, so celiac disease is an autoimmune disorder. Essentially, your body reacts to gluten, which is a structural protein from wheat or grains, and produces an inflammatory response. The main root cause that's been identified is a genetic mutation that affects the kind of cell surface receptors on antigen presenting cells, which activate T cells. So essentially, they get these receptors on these cells get mutated. Then they recognize these gluten proteins and peptides as something harmful. Then they go take it to the T cell, and that causes like a cascade of an immune response. And yeah, that's that.
Awesome. Can microplastics be broken down once they're stored in the body? Where are they even stored?
Yeah, so this microplastic topic has been a pretty big thing recently because recent papers about people having credit card levels of microplastics in their system and their blood and breast milk and whatnot. It gets into our body through food sources, mainly through ingestion. Fish, especially, I think like just degradation of stuff in the ocean gets into fish, gets into us. There is evidence that we excrete quite a bit of it in our stool. It can also just like enter our cells as well through endocytosis. And it's been correlated with oxidative stress, inflammation, apoptosis, and metabolic effects. I don't think you can chemically break down microplastics in your body. I might be wrong. I've never seen anything about it though. But what can happen is just like physical abrasion can break the microplastics down into nanoplastics, making them even smaller. So like I like to think that maybe if it can get into cells, it might be able to get back out of cells, get back into your blood, or excrete through urine or stool again. So I just feel like it's just like an equilibrium distribution around, and at least I hope that's what that is. I'm not too sure about this. Maybe you've
Yeah.
looked into that.
Yeah, it gets broken down by CYP enzymes still. And in fact, they use like gene engineering and E. coli bacteria for CYP enzymes to determine how this happens. So without a doubt, same process of PUFA breakdown is how plastics get broken down too. But the distribution, I agree. It's like it depends on the plastic, and because there's like different functional groups, some of them can be amphiphatic. So it's like it can be in any kind of tissue really. So I don't really know 100%, but I do know that they do get broken down. And the real concern is the reactions that occur inside of cells with biomolecules. That's where the plastics become an issue.
Huh? Yeah, I didn't know CYP enzymes break them down. It's pretty insane. I guess they really do react with anything.
Yeah. Awesome. Thoughts on peptide therapy for immunity, pain, and tissue repair?
Yeah, so this is like a super broad question. I'm not gonna be able to like assess it like in detail or anything, but peptide drugs have been on the rise in the past 10, 15 years. There's some benefits of peptide drugs compared to small molecule drugs. Like, they can maybe be more selective. They're a bit easier to make. It's just couplings. They're easier to screen for. You can do high throughput analyses. But there's also a lot of cons. They're less metabolically stable. Your protease enzymes and everything break them down faster. They're less permeable, so they get into cells and they get into your body harder. They have poor oral bioavailability, so typically with peptides, you're not going to be able to just like take a pill. It's not going to really pass through into your bloodstream through the small intestine, through the epithelium and stuff. They're also cleared pretty rapidly and have just poor solubility. There's a lot of issues with peptides. You have to inject a lot of them, but there's been an increasing number of peptide drugs available for immunity, pain, tissue repair, all of those you mentioned. And as with any other drug, it's just going to be like a case-by-case basis, weigh the pros and cons, think about the side effects of the drug, what benefit you're gaining from this, all that stuff. In the early stages of peptide therapy, most of them were like insulin peptides and that type of thing for diabetes. But recently, there's a lot more for cancer, irritable bowel, myeloma, osteoporosis. I looked at a list. There's something like 20 to 30 peptide drugs that have been approved very recently. So
Fascinating.
it's definitely a growing field.
Yeah. There's a mathematician and a bioinformatician in Ireland. Her name is Dr. Nora Caldi, and she does bioinformatic analysis on natural peptide products. So she works closely with synthetic chemists and then make these peptides in the lab. And what she's found is essentially there's more peptides produced in a single apple, for example, than there is all the information on the internet or something like that. So it's amazing how many peptides exist.
That's mind blowing.
Next question.
I think the natural world still the natural world still beats out whatever we've created by a mile.
Yeah, without a doubt. Next question. Are there any safe mercury chelation methods?
This is a funny question. So I think I talked to you about this like a week ago when I saw the question, but when I saw this, I was like, I have no idea. Then I thought about it in my sleep and woke up with an idea. So typically the way like metal toxicity is treated is with some sort of chelating ligand that's typically polydentate. The prototypical one is EDTA. I forget what it stands for. Ethyl something something amine dicarboxylate tetramine. So it's 2 carboxylates and 4 amines. So it's a hexadentate ligand. So most organometallics like octahedral geometries, which means they have 6 coordination sites around them. So EDTA is very strongly chelating because it presents 6 ligands, 2 of which are negatively charged, the carboxylates, and 4 of which are amines. But typically, EDTA is best for hard and early and light metals, since amines and carboxylic acids are hard Lewis bases, which means they pair best with hard metals, whereas mercury is late, heavy, and soft. So I was thinking, okay, you probably still want something that's polydentate to make sure you're chelating it efficiently, but you're also going to want something that's soft. So instead of amine ligands, you're going to want something like a phosphine or a thiol. Then I looked into it, and there's very few drugs that are used clinically for mercury chelation or mercury toxicity. One of them is dimercaprol, which is like beta mercaptoethanol. Like it's like that with another CH2 thiol attached to it, so it's 3. This also works for lead, arsenic, gold, and antimony poisoning. It has to be an intramuscular injection, but it's pretty toxic. It causes like high blood pressure, pain, vomiting, fever. It was made in World War II. It has a pretty narrow therapeutic index, so you can only give a tiny amount before you start to poison the person. There's been some improvements on that. The other drug used is 2,3-dimercapto 1-propane sulfonate. So instead of a alcohol, you have a sulfonate on there. It's a little less toxic, but at the end of the day, it's going to have its side effects and stuff as well. It's not something you're ever going to want to be taking unless you're like about to die from mercury poisoning. So the best method for avoiding mercury poisoning is don't get exposed to mercury.
Right. Awesome. Thanks for that concrete, in-depth analysis on that question. Next question. Why did you choose the organic chemistry path? We went over this in the beginning, but a summarized version.
Yeah, to summarize, I think I started university not knowing what I wanted to do. I liked sciences, biomedical science route is what I started in. Program exposed me to like all the different sciences, from biology, chemistry, physics, math, even got some psychology, anatomy, physiology, whatever. And then basically from out of that, I was like, okay, I like the chemistry the most. And I just happened to have learned the most organic chemistry, realized it was pretty cool at the fundamental theoretical level and had cool applications. So that's what I chose.
Nice. Do you have a specific large-scale, hard problem that you're trying to solve in your field?
I think we remember. I think I know who asked this, but I don't remember who it is. I think it's someone we know. But this is a hard question to address, since a single researcher, a single student can only pick such a big problem. I'd say that like the main thing I'm working towards is trying to make synthesis of complex molecules more efficient and more sustainable, in terms of developing new catalytic methods to create new bonds that haven't been possible before, or to develop synthetic routes towards molecules that are difficult to make otherwise.
Yeah. Fluoride in biological systems, does it cause pineal gland calcification?
So this is something that is also pretty widespread in the Instagram health community, I think. I've certainly seen it talked about quite a bit. I read into it today. So essentially the reason fluoride is kind of put in, toothpaste and water or whatever, is that it gets incorporated into calcified tissues. And that's a natural mechanism. Like ancient skeletons, where end up having a lot of fluoride in their teeth and bones. And the benefit there is that it hardens your teeth and bones. Teeth and bones are made of like apatite, like essentially it's a big complex of calcium and hydroxide and phosphate. And the fluoride basically displaces hydroxide and makes your hard tissues harder. So that's actually the beneficial effect of it. The negative effect of excess fluoride is when it starts affecting your soft tissues, and the main soft tissue it affects seems to be the pineal gland, since it's pretty vascularized and there's no like blood-brain barrier protecting it, and that can have some pretty toxic effects in terms of like neurodegeneration, hormonal issues, since it affects like melatonin and stuff.
Okay. Talk about changes in your lifestyle that you did to be where you are today, DK.
Yeah, so that's
Right
DK,
there.
another one of the lifters in the morning squad. I guess we kind of covered this, but the main changes were like realizing that consistent sleep matters, implementing that, and then realizing that food matters and exercise matters. So essentially everything we talked about earlier, and being consistent
Matters.
with it, and realizing that I feel worse when I don't do it and less efficient. So might as well just do it all and know that it's good for me in the long term.
How to balance a hectic college life and start a fitness journey. Did you hear me? Can you hear me?
Yep, I'm gonna turn off my video for this, just till we get the last question done.
Okay, got it.
How to balance a
Yeah.
hectic college
How
life
to
and start a
how to balance it? Yeah.
yeah. Honestly, just do it, man. Like, you just got to do it. You got to prioritize your sleep, prioritize your food, and prioritize your fitness. Don't skip meals. Don't like skip your sleep that often. If you do things right and you're sleeping a lot and you're eating right and you're getting some, 30 to 60 minutes of exercise a day, um, your brain's gonna work so much more efficiently. You're gonna be able to get the work you used to get done in like 8 hours and 6 maybe, and just by going through and taking care of your health, you're gonna be more efficient, quality over quantity, and it'll be kind of a self-fulfilling cycle, and you'll be able to get it done.
Great. Last one. Favorite muscle group to hit.
Oof, I've got to say back. There's no other answer to this. It's got to be back. What about you?
Yeah, back really does make me feel like big gorilla. I like
yeah.
it. Agree. Yeah. Awesome, man. We got through it all. It
We
was
did
a
it.
long journey, and I'm glad that you stuck it through with me, man. I appreciate everything this week, especially being so busy and going through and being so thorough with everything as well. Where can people find you if they're part of my audience? Where should they look to find Kian?
Bro, first of all, thank you so much for inviting me on. This was an awesome discussion. It was a blast. Honestly, like 5 hours flew. Great opportunity
Yeah.
to discuss some chemistry and health with you. Hoping to meet you soon, eventually, and
Definitely.
keep sending each other science and non-science stuff on Instagram. But yeah, for people where they can find me, my Instagram is just my full name, Kian Mansour. Should be pretty easy to find. And I also have a YouTube channel, but that's mainly for Rubik's Cube solving. So if you're interested in that stuff, or just seeing some of that, then hop on there. But in terms of social media, my main thing is Instagram. I post what I eat, some exercise, some chemistry stuff on my story every now and then, some cubing. So if you just want to keep up with what I'm up to, that's where to find me. Might start doing a bit more educational stuff. We might see, but yeah.
Yeah. Appreciate it, man. Is there any last words in regards to guys that might have like a significant other or somebody special in their life that you want to make sure they realized?
Oh, you're really making me say it, aren't you? Okay.
Let's go for it.
Yeah. So there's a meme where it's my face and the caption is, "Brother, don't let these women distract you, brother." And all my friends have this as their phone lock screen now. Now, this is not some sort of attack on women or whatever, because the exact same thing applies to women. Don't let these men distract you, right? And the idea behind this is that if you have goals in your career, with your health, all that stuff, it doesn't make sense to let temporary relationships distract you, right? If something's not going to be forever, if you're not going to marry this person, don't let it distract you. That's essentially the message of the meme.
Or just be a Sigma male.
Bro, dude,
Done.
I was in lab, right? And people saw me reading Homochirality and like whatever, and they're like, "What are you doing?" I'm like, bro, trust. I have this podcast with Pedro, man. It's gonna be fun. We have to discuss everything. They're like, "What do you mean everything? You're gonna sit there for 12 hours?" I'm like, "I guess so." So, 5 hours. But they're like, yo, this Pedro guy, who is he? I'm like, oh yeah, he's this like genius lifter, crazy. He just reads everything guy. He's doing 3 undergrads. He's like, oh, how old is he? I'm like, 28. He's like, does he have a family and kids yet? I'm like,
Nope,
ugh.
not yet, my friend. Yeah, I got a long way to go. I don't see myself having a family until I'm possibly like after with the master's program, because then maybe I have everything settled out. But yeah, there's still time, especially for you. You're super young, 22, right?
Yeah, I'm 22.
Yeah, you got the whole world ahead, brother. 22 years old, I was nowhere near close to your level.
Thank you, sir. You're going far though, so everyone's on a different timeline.
And we're probably gonna wind up together as scripts if everything goes together. If
Oh
everything
yeah,
goes
we'll
smoothly.
see. We'll see. The weather be nice.
Go
The
surfing.
research be nice.
Yep. Inevitable, man.
Yeah, the Miami
right.
project first though. We got to get the boys
Yeah,
together.
We keep that top secret for now.
Oh yeah.
All right, brother. Thank you for coming on. I appreciate the time, the effort, and the incredible depth that you went through with every question, every topic.
Oh yeah. Thank you for having me, and thank you for listening to me ramble.
No problem. We'll talk later. See you on the gram.
Yeah, bro.